Hello, hi everyone, my name is Deependra and I welcome you all in this one-shot video of matrices. As we have discussed previously that when determinants is clubbed with matrices, it becomes such a deadly combination that it becomes the most important unit of ITG. I'm not saying it is one of the most important units, it is the most important. Because every year in every shift, JEE Mains asks minimum 2 to 3 questions from this combination of matrices and determinants. With 3 questions, I hope you're understanding plus 12 marks. What is the meaning of plus 12 marks? I think I did not explain. Plus 12 marks in JEE Mains from mathematics sections from these 2 units or from these 2 chapters only, matrices and determinants when clubbed together. I hope you're realizing the significance of it, which we'll cover in this one single video. Every single detail, all the concepts, all the loadings, all the methods, along with a lot of short techniques through which you can directly get the answers of the questions within seconds. Of course, in this one short video only, we'll solve a lot of previous year's questions also, through which you will get a complete clarity of all the concepts and you can consolidate this chapter to a great extent. Well, with this one shot, we'll provide you the PDFs, the notes as well, and with them you will get DPPs for your practice. The notes and the DPPs are available on our PW app. The PW app is one of those amazing platforms from where a lot of students are preparing for different competitive exams at a very economical cost. Here, the link to our PW app and this course is already given in the description. If you click on it, you can access this entire material. So I think without further delay, we can get started with this particular lecture. So here is the index of the chapter matrices, what all we'll be discussing in this particular one-shot video. We'll begin our discussion with the definition of matrices, different important terms which are used in questions, and you need to understand that what are the different types of matrices. Along with that, we'll discuss what is the trace of a matrix, what are its properties, how are questions formed on this particular concept, and then we'll come to the multiplication of matrices, what is conformability, and a lot more will be explored here in this section. Well, this particular section is again a very crucial section from where a lot of questions are asked. This is the base which creates the foundation for this particular section, where we'll begin with the discussion on transpose of a matrix. What is the transpose of a matrix, which lays the foundation of adjoint and then the inverse of a matrix. Then of course we'll start discussing some more properties of the determinant of a matrix. As we all know that the determinant of a square matrix can be taken or evaluated, so that is what we'll discuss here. A lot of properties will be discussed, and then we'll come to this part where we'll be discussing adjoint and the inverse of a matrix, its properties, and a lot of questions are asked from this particular section, which also will cover. Not just that, but we'll discuss the Cayley-Hamilton method, the matrix polynomial, the eigenvalues of a matrix, and how do they form questions based on it, and how should you deal with them, along with a lot of properties. And that's how we'll conclude this particular chapter. I hope you have gotten a sufficient clarity that what we'll be discussing, a complete one shot, a thorough one shot, a very comprehensive one shot, through which will take you through everything which is required for this particular examination from this particular chapter. So with that, let's get started, students. First of all, let us understand what do you understand by a matrix. In a very simple language, if I were to make you understand, a matrix is simply a tabular structure where you have certain number of rows and a certain number of columns. For example, if here I'm having, let's say, certain number of rows, so these are the rows. I hope you can see first row, second row, and that's how we are having mth rows. And then certain number of columns. For example, you are having the first column, then second column, then third column, and that's how you're having the nth column. So here in this configuration, I had n number of rows and n number of columns, which meant this matrix was of the order m cross n, which means m represents the number of rows and n represents the number of columns. And what do you mean by m cross n? So m cross n gives me the idea about the number of elements this particular matrix contains. So if I were to ask you how many elements are there, you would say, so there are m into n elements are there. I hope you are getting complete clarity on a matrix. Matrix is basically an arrangement of elements. So a matrix does not have a value, it is simply an arrangement. Whereas if you take a square matrix where number of rows and columns are same, then a matrix which has the number of rows and columns same, which is called a square matrix, then a square matrix determinant can be taken. So determinant is a single value, is a number, but when it comes to matrices, they don't have any values. They are simply an arrangement of elements, an arrangement of numbers usually. So that's how you write a matrix. Along with this, what you also need to understand is matrices are represented by, you know, usually capital letters, for example capital A, capital B, capital C, or capital X, Y, Z, etc. So that's all about the basic understanding of matrices which you need to understand, build, or develop. As we have already discussed, if I were to talk about the positioning, well, if I write A12, it will help me in understanding that this is the element of first row and second column. If I were to write, let's say, A33, well, that will help me in understanding that this is an element of the third row and third column. I hope you are understanding how are we developing the indexing system and how are we positioning the different elements in a particular matrix. Not just that, along with the definition of matrix, we'll start understanding the different types of matrices. What are different types of matrices? How do you understand them? That is what we'll be exploring now. I hope you have gotten a basic understanding of matrices. So here, first of all, there comes a term which is called a row matrix or a row vector. Let's understand it. What is a row matrix? If there is a matrix which has only one row, so it can have multiple columns, but the number of rows are fixed. So it could be of any order, but the order should be fixed like 1 cross n sort of an order, where I hope this particular one is helping you in deciding that the number of rows are going to be 1. So what you have fixed here is that the number of rows, which means columns can be any number of columns, 1 column, 2 column, 3 column, or 4 column, whatever number of columns you can have. But if you have this kind of matrix A11, then you have first row, second element, then you have first row, third element, and you know, so on, finally first row and nth element. So this is how you're writing a row matrix. Well, once you have understood a row matrix, can you not deduce what will be a column matrix? I hope you're understanding. When you say that you're dealing with a column matrix or a column vector, it will help you in understanding that when you talk about a column matrix or a column vector, what is fixed in this case? The number of columns. Here, I'll be having only one column, but the number of rows can vary, of course. So here in this case, I can have certain number of rows, any number of rows rather I would say, but the number of columns is fixed, which is 1. So here I'll say any number of rows could be there, but the number of columns is 1. So here again I'll have this first row, first element, then we have second row, first element, and that's how it goes on up to nth row and then first element. But what is fixed here is the number of columns. I hope no confusion so far. A very basic terminologies we have explored so far. Next, there comes a rectangular matrix. Whenever you deal with a matrix which does not have its number of rows and columns are equal, then such matrix is said to be a rectangular matrix. The definition states it all, that whenever you deal with a matrix which is of order, let's say m cross n, and if you are dealing with certain phenomena where m is not equal to n, then we all say that this shape, this tabular arrangement will look like a rectangle, because here number of rows and number of columns are not same. Well, that helps us in understanding that this will be a rectangular matrix. I hope you're understanding. For example, to give you more clarity, in a better world, I'll say that, let's say if you are dealing with a matrix which is 4 by 3. Now what is 4 by 3? The order 4 by 3 helps you in understanding that it will having 4 rows and 3 columns. I hope you're understanding. So whenever you're dealing with a 4 rows and 3 columns kind of a structure, it will give you the idea that it should be a rectangular matrix. What do you understand by a square matrix then? Again, I hope you are able to deduce from the definition itself that a square matrix will be a matrix where the number of rows and number of columns are same. And as we have already discussed, learned and explored, the determinant of a square matrix can be taken, which means if you are having a matrix which has the same number of rows and columns, so if number of rows and columns are same, then such matrices are called square matrices. For example, a square matrix of order 1 by 1. For example, you can have a square matrix which is of the order 1 by 1, which will have only one element. A square of matrix, a square matrix of order 2 by 2, which will have 4 elements. A square matrix of order 3 by 3, which will have 9 elements. Such kind of square matrix exist. I hope you're realizing it. And that's how square matrix determinants can be evaluated. This is all about, I think, rectangular and square matrices. There our discussion goes further, and there we explore the another sort of matrix which is called a diagonal matrix. Now, what is the meaning of a diagonal matrix? A square matrix is said to be a diagonal matrix if all its non-diagonal elements are 0. So first of all, you need to have a square matrix, so its number of rows and number of columns are going to be same. That's the first condition. Then what you say next is that if you have aij, let me just make a small correction over here, students. Aij here, if aij is equal to 0, whenever I is not equal to j, because I and j are equal for the principal diagonal elements a11, a22, a33. So apart from these a11, a22 and a33, if all the other elements, for example a12, a21, a31, a32, a23, such elements, non-diagonal elements, if they all are 0, if all of the non-diagonal elements are 0, then such matrix is said to be a diagonal matrix. As you all can see here, I am rather representing over here a diagonal matrix where we have this principal diagonal which has the elements -1, 2, but if you look at the other non-diagonal elements, they are 0. If you look at this particular 3 by 3 square matrix, it has this diagonal elements 3, 5, 7, but apart from 3, 5 and 7, the other set of elements are clearly 0. So all the other elements apart from the principal diagonal elements must be 0. Then only you call a square matrix to be a diagonal matrix. Even here, if you look at this particular part, it has only one element, and that element lies on the principal diagonal, so it can be anything. But apart from this, the other elements should be 0, which are not there. So here, one by one will be a square as well as a diagonal matrix. I hope you are able to understand what do you mean by a diagonal matrix. Diagonal matrix, you know, when extended further, gives you more clarity on a scalar matrix. Now, what is the meaning of a scalar matrix? It is even a better subset of a diagonal matrix, or a more specific subset of a diagonal matrix, that whenever you deal with a diagonal matrix, so our diagonal matrix can be called a scalar matrix, if its diagonal elements are equal. So previously, what did we have? We needed to have the diagonal elements to be non-zero and the other elements to be 0. But what I want here is that the diagonal element should be non-zero and equal, and the other non-diagonal element should be 0. I hope you can see it from the definition that aij, whenever I is not equal to j, for example 1, 2, 2, 1, 3, then 2, 3, then this position is 2, 1, 3, 1, 3, 2. So these are the positions where I and j are not equal. Well, in that case, it should be 0, but that's not sufficient. What is more important here is that if I and j are equal, which means we are talking about the principal diagonal elements, then it should be same. It should be a fixed scalar value. That's exactly what they're trying to make you understand by the term scalar matrix. So scalar matrix means the principal diagonal elements should be same, they should be exactly same, and all the non-principal diagonal elements, all the other elements should all be 0. That is exactly what is the meaning of a scalar matrix. How do they represent the scalar matrix usually? For example, if they are writing diagonal 7, it means this is a diagonal matrix of order 1 and its principal diagonal element will be 7. This is exactly what I am trying to make you understand. Whenever I wish to write diagonal 2, 2, so diagonal 2, 2 means a scalar matrix which has the diagonal elements as 2 and 2, and here all the other elements should be 0. If I write diagonal 5, 5, 5, it means all the diagonal elements should be 5, 5, 5 each, and the other non-diagonal elements should all be 0. I hope you are able to understand the meaning of a scalar matrix. Well, proceeding further, what you also need to understand is some more terminologies and things. For example, there comes a very crucial type of a matrix which is called a singleton matrix. Now, what is the meaning of a singleton matrix? If you deal with a 1 by 1 matrix, if you are having 1 cross 1 order of a matrix, then such matrices are called a singleton matrix. For example, matrix which has only one element, 3, k minus 2, whatever you wish to write. If it has only one element, then such matrix is said to be a singleton matrix. Now, there comes another term which is called triangular matrix. Now, what is the meaning of a triangular matrix? This is an even better deduction here when you start understanding square matrices. See, you have a square matrix, okay, that's perfectly fine. Then a square matrix is said to be a triangular matrix if. Now look at this if part. If its each element either above or below or both of the principal diagonals is 0. I hope you're able to digest it, understand this particular part. If not, I'll give you more clarity with an example. For example, here let's talk about the upper triangular matrix. For example, if we are having an upper triangular matrix, now how do you deal with an upper triangular matrix? What is the meaning of an upper triangular matrix? Here, I square matrix in which all elements below the principal diagonal are 0. I hope you can see here, this was a 4 by 4 matrix. This was a 4 by 4 matrix, right? So this matrix had a order 4 by 4. Now, in this 4 by 4 matrix, of course, a square matrix it was. If I am having this principal diagonal elements, these are the principal diagonal elements. So all the elements which are lying below the principal diagonal, even this element over here is not visible, that element was also 0. So here, all the elements below the principal diagonal, if they all are 0, so I am clearly seeing an upper triangular getting formed. With this particular portion, I am seeing an upper triangular getting formed, upper triangle getting formed. And such matrix is said to be an upper triangular matrix. Definition wise, it is very simple. It is very simple. If I is greater than j, if I is greater than j, then aij should be 0. I hope you can see here, this is 2, 1. 2 is greater than 1, it is 0. This is 3, 1. 3 is greater than 1, it is 0. This is 3, 2. 3 is greater than 2, this is 0. This is 4, 1, 4, 2, 4, 3. They all are 0 because 4 is greater than 1, 2 and 3. But if you look at here, 1, 1. 1 and 1 are equal. It should be non-zero. Here, I hope you can see this is 2, 2. 2 and 2 are equal. It should be non-zero. If you see here, it is 2, 3. 2 is less than 3, which means it should be non-zero. So I hope the definition is also very clear to you all, that if you are having a matrix which has all the elements below the principal diagonal 0, then this matrix is called the upper triangular matrix. With that, I am very sure you are able to digest what is the meaning of a triangular matrix, lower triangular matrix. So here in a lower triangular matrix, you will have aij to be 0 whenever I is less than j. So this we didn't understand. This is an even more technical term. Can we have a simpler definition? Yes. In a very easy language, I'll say a square matrix in which all elements above the principal diagonal are 0. So you are having a principal diagonal here, but above the principal diagonal, if all the elements are 0, then this matrix is said to be a lower triangular matrix. Well, what you need to understand is that this all is being discussed in the context of a square matrix. So we are boiling down we are limiting our discussion to the discussion of square matrices now. I hope you are getting it. So here we had this principal diagonal and all the elements above the principal diagonal are 0. In that case, we are clearly seeing a lower triangle getting formed. So such matrix is said to be a lower triangular matrix. Here also you can see that 1, 1, then you have 2, 1, then 2, 2, then 3, 1, 3, 2, 3, 3. All these elements having their row index, the index of their row is greater than the index of the column. I hope you can see, I said opposite of it. I'll say rather what is more clearer here. The index of these elements, if I look at them, the index of all these zeros, if I look at them, any, if you were to choose, for example, this one here, what am I seeing here? This is the first row and fourth column, right? So 1, 4. I hope you can see that 1 is less than 4, which is clearly indicating that this element should be 0. So anywhere in a matrix, in a square matrix, if you see that its row is less than its column, then the element should be 0 if it is said to be a lower triangular matrix. I hope you're understanding why. From its figure also, from its depiction, from its illustration also, it may be very evident and understandable that what is the meaning of an upper triangular matrix, what is the meaning of a lower triangular matrix. Triangular matrix, as we have discussed, there is one more very crucial concept which you should remember, that minimum number of zeros in a triangular matrix is given by n minus 1 by 2, where n is the the order of a matrix. Sir, how did we evaluate this? That's more interesting or important part. What you also need to understand is there will be two sorts of matrices, either upper triangular matrix or a lower triangular matrix. Can I have a matrix which is simply a triangular matrix? Yes. If apart from the principal diagonal elements, I repeat, I'll come back to the original definition first so that we can conclude what we are wanting to discuss. A square matrix is called a triangular matrix if it's each element above or below. Now, what is the meaning of above or below? Or is a conjunction which is understood as either above or below or both. So that is the meaning of or. For example, if I say I like either poha or jalebi, what do I mean by that? I am saying I like it. It does not mean that I like either poha only or jalebi only. It means in mathematics language, mathematically it means I would like to have either poha or jalebi or both. When we understand the chapter sets and relations, there you will understand it more clearly that what do I mean by this particular statement. But I hope you are getting complete clarity that what is the meaning of this particular part. So here, if I get back to this portion where I'm trying to make you understand, see here, if I were to tell you more clearly what are the number of zeros here. So let me just take an example so that you understand it better, that what is the comment I'm trying to make here when it comes to the minimum number of zeros a triangular matrix must have. See, let's say this is a 3 by 3 matrix. So from this 3 by 3 matrix context, let's say what I need to understand here is that the principal diagonal elements should be non-zero. That is something which you all need to understand and remember. But what is the minimum number of zeros I need to have? Now I need to ensure that either these elements, which elements, students? Let me write them as let me write these elements as D, E or F, and here G, H and I. So what I am trying to make you understand here is either this D, E or F should become 0, or this G, H, I should become 0, or both should become 0. But what is the constraint here? I am looking for the minimum number of zeros. What do I mean by minimum number of zeros? Minimum number of zeros means what is bare minimum which is required to ensure that this matrix will be called either a lower triangular matrix or a upper triangular matrix. So what I need to understand here in this case is that I need to ensure either DEF to be 0 or GHI to be 0. If both become 0, that will still be fine. Then also I'll be calling it a triangular matrix. But my concern here is that what is the minimum number of zeros I need to ensure here so that I can call it a triangular matrix. Whether upper or lower, that's not my matter of concern. So here I can very clearly see that minimum DEF, either DEF or GHI could be 0. If I put the value of n here in this formula, I'll get here 3 into, of course, 2 divided by 2. Sorry, 3 into 2 by 2, which will help you in understanding that the number of zeros you should have here, minimum number of zeros you should have here should be 3, which are going to be either DEF or GHI. Now, how did this formula, how were we able to calculate or deduct or deduce this particular formula? That's exactly what we need to understand. See, in an matrix, in an n-ordered matrix, here I was having a matrix of order 3 by 3. Let's say I am having a matrix of order n cross n. So if I'm having a matrix of order n cross n, which means it should be having n square number of elements. Now out of these n square number of elements, what was expected here? The simple part which was expected here to be is that, let's say my condition is to keep it a lower triangular matrix. Now what is the meaning of lower triangular matrix? Apart from all these elements, the other elements should be 0. Let's say that is the requirement. Now either this case could have happened, or what else could have happened is that I could have tried making it an upper triangular matrix. In that case also I would have given the same thought. So here the thought I am trying to give is that I am wanting to make it a lower triangular matrix. So here what am I having? I am having a very simple part here, that the number of elements this particular matrix will be having would be n into n, which will be n square. Out of these n square elements, if I simply subtract, if I first of all half the elements, or rather, first of all, out of these n square elements, I am eliminating these principal diagonal elements first of all. For example, just to make you understand this more clearly, what I am doing here is I'll try to demonstrate with some numbers. For example, here I had 3 into 3, which were 9 elements. Now, out of these 9 elements, what I have done here is I have eliminated these 3 elements. I have eliminated these 3 elements, the principal diagonal elements, which were 3 in nature. Now, out of this, I am left with these ones and these ones. What I have already been trying to mention here is that the very simple part, that either I should have the upper triangular matrix or the lower triangular matrix. In order to have that, I should have either these three should be 0 or these 3 should be 0. So can I not say, if I want to have minimum number of zeros, I'll say from all the elements, if I have removed the principal diagonal elements, which means I'm left with these and these. So either these 3 should be 0 or these 3 should be 0. So half of these elements, either these 3 or this 3 should be 0. So half of these elements should be 0. That's exactly what I'm trying to say here, is that the total number of elements are n square, out of which this principal diagonal will contain n number of elements. So what I have now left with is that either these elements or these elements. Now, out of either these or these, either of them should be all 0. Which means either this set should be 0 or this set should be 0, which means either these all should become 0 or they should become 0, which means this is the minimum number of zeros I should have in an n-ordered matrix to call it a lower or upper triangular matrix or a triangular matrix. But this is simply does not trying to indicate that this will be the number of zeros. This should be ensured in such a manner that either all of them should be 0 or all of them should be 0. It does not mean that some of the elements become 0 from here and some of the elements become 0 from here and then you'll be able to call it a triangular matrix. No. It is opposite. What I'm trying to say here is, I'm not saying that if these are the minimum number of zeros, then this matrix can be called a triangular matrix. No. What I'm saying here is that if you are having, if somebody claims that there is a matrix which is a triangular matrix, which is already said or called or fixed or stated that there is a triangular matrix, then by looking at that matrix you can claim something very crucial here, is that this will be the minimum number of zeros that triangular matrix will have, because this is what is bare minimum required to make it or call it a triangular matrix. I hope you have gotten a complete clarity that from here, from the numerator, if I take this n common, I'll be able to create this particular formula. So very basic permutation and combination we have applied and gotten the clarity on minimum number of zeros. Moving ahead, what do we have next? What we are given next part is the horizontal matrix. Now, what is the meaning of a horizontal matrix? A very simple definition is there, students. If you are dealing with a matrix which has a certain order, but if the number of rows are less than number of columns, then we call it the horizontal matrix. A very simple definition it is. It looks like a horizontal matrix because here the number of rows are less than number of columns. So it will look lengthy in terms of its number of columns. I hope you can see it very clearly. Well, in the same fashion, if I were to define a vertical matrix, what will it be? I hope you can see that if the number of rows are greater than number of columns, I hope you can see it very clearly, then this looks like a vertical, which means this will be called or said to be a vertical matrix. I hope the definition is very well understood by you all. Now, what is a null matrix or a zero matrix? What does it mean? Simple, very simple, straightforward. Order can be anything. It needs to be m cross n, where m could be the number of rows, n would be the number of columns. But if all the entries, no matter what is the value of I or j, all the entries are 0, then such matrix is called a null matrix. This is a null matrix of order 2 by 3. This is the null matrix of order 3 by 3. So these are all null matrices. All you need to ensure is that whatever is the order of that matrix, all the elements should be 0. I hope a null matrix or a zero matrix is also understood by you all. Next is submatrix. Now, what is a submatrix? Submatrix is again another particular part where you need to understand a very basic thing, that if you are given a matrix, let's say a 3 by 3 matrix was given to me, out of which I have chosen a 2 by 2 matrix from this 3 by 3 matrix. So I have taken a 2 by 2 matrix out of this 3 by 3 matrix. The way we have sets and we take these subsets, in the same fashion, if I am having a matrix and if I take a part of this matrix, then that part is called the submatrix. I could have taken any part. For example, let's say I choose 8, 9. So this is a 1 row 2 columns combination. 8, 9, 2 elements are there, right? So in that case also, this could have also been called a submatrix fetched out of this particular matrix. As you all can understand the definition, which is obtained from a given matrix by deleting any number of rows and certain number of columns. Then such matrix which is formed will be called the submatrix of the given matrix. I hope this part is understood by you all. Well, first of all, what you need to understand is a lot of terminologies, definitions are there. So we'll understand these terminologies and definitions first. And then IIT JEE, what they do is they ask you a question by merging these terminologies and concepts all together. And then we'll start discussing questions. So first of all, let us explore all the terminologies, all the terms on which questions are found by IIT JEE. Then in one go, we'll start discussing the questions as well by merging different concepts all together, which IIT JEE does. So first of all, let us understand all the basics, terms, definitions and all. What do we have next? The next part is trace of a matrix, a very crucial concept you all should be aware of, a very simple phenomena. First of all, you should have a square matrix. You should always have a square matrix. Now, what is the meaning of square matrix? The number of rows and the number of columns should be same. They should be same. Now, if you are having a square matrix, and let's say if I take the sum, if I take the sum of principal diagonal elements, if I take the sum of the principal diagonal elements, then for example here this is a 3 by 3 matrix, a square matrix. What is the principal diagonal here? This 2, 3 and 4. With the sign, if I take the sum, so 2 plus 3 is 5, 5 plus 4 is 9. This sum of the elements of principal diagonals is called the trace of a matrix. Mathematically, this is the trace of a matrix A, which is denoted by trace of A, written as summation of AII, where I is ranging from 1 to n. For example, A11, A22, A33, if it was a square matrix of order 3 by 3. I hope you are able to understand this particular part very clearly. What is the meaning of a trace? Sum of all the principal diagonal elements of a square matrix. That's it. A very simple definition. Then why are you saying that this is a very important concept? I am saying that this is a very important concept because a lot of questions are asked from this particular topic. How? Have a look at that. First of all, let us understand what are the different properties which get created based on the concept trace of a matrix. Now, if I were to say that if I multiply a matrix by a scalar quantity, so how does multiplication of a matrix with a scalar quantity happens? Let us understand that part first. For example, if I'm having a matrix over here, which let's say is a 2 by 2 matrix, it could be of 2 by 3, 3 by 3, 3 by 2, any. But let's say I'm taking a square matrix of a 2 by 2. Now, in this 2 by 2 matrix, I'm denoting it by A. Let's say this is having certain elements, let's say A, B, then C and D. Now, in determinants, what did we see? That if I'm multiplying a determinant by a scalar quantity, that scalar quantity will be multiplied to either any row or any column, but to a single row or a single column. But here, when you are multiplying a matrix by a scalar quantity, what is the difference over here is that that scalar goes to all the elements of that matrix. What does it mean? It simply means a very simple thing, students, that if I'm multiplying this matrix by a scalar quantity here. So K is a matrix, a 2 by 2 matrix, but what is K here? K is a scalar quantity. So if I'm multiplying this matrix by a scalar, this K goes to all the elements, so it should be Ka, then Kb, then you have Kc, and then you have Kd. So this is how you multiply a matrix by a scalar. And I hope you can see very clearly that if I were to take the trace of this particular matrix, then would you not say that the trace of matrix A was sum of the principal diagonal elements, which was A plus D? So here you will say that trace of K times the matrix A will be Ka plus Kd, which can be written as K times A plus D, which is equal to K times trace of A. That's exactly what we are given over here. The trace of k times A is equal to k times trace of A. In the same fashion, all these properties can be proven, although I'll not be proving or demonstrating all of them. I'll simply be giving you the idea that this is what happens. You can very easily verify by such algebraic operations. What do we have in the next property? The next property says that if you have this particular part, which part? Trace of sum or difference of two matrices. Now, two matrices can be added or subtracted if they are conformable in terms of addition or subtraction. Now, conformability means if you want to add or subtract two matrices, what does it mean? Let's understand that particular part. Here, if I'm given a matrix A, let's say, which has a certain order, let's say 3 by 2, right? And it has, of course, it will have 3 rows and 2 columns. So if it has, let's say, A, B, C, D, and E, F, these are the 6 elements. There is another matrix. Let's say the other matrix is, let's say, matrix B. Now, the matrix B should also have the same order 3 by 2 if I want to add or subtract matrix B with A or from A. I hope you are understanding this particular part, that matrix B should also have the same order which matrix A had. So matrix B, if has order 3 into 2, then only I'll be able to add or subtract this matrix B with matrix A. I hope this part is understood by you all. What does it mean? It means, let's say if the elements are here G, H, I, J, K, and L. Now, if I wish to add or subtract matrix A with matrix B, then what I do here is that all the elements of A and B, corresponding elements of A and B, are added or subtracted as per the requirement. For example, let's say I am asked to add matrix A with matrix B. So I'm asked to add matrix A with matrix B. So I'll be adding the elements of matrix A with the corresponding elements of matrix B. What does it mean? It means here, I hope you are learning the difference between the addition or subtraction of matrices and determinants. In determinants, what we used to have was that we used to have a square matrix basically, or a square determinant, and in that, if the determinant was of order 3, 2 rows or 2 columns must be identical in both the determinants. Then that third unequal row or column was getting added or subtracted. But here in this case, what is happening, students? I hope you can see it very clearly. Here in this case, I can see it very clearly. If I'm supposed to add A and B, these two matrices, I'm supposed to add all the elements, all the corresponding elements. What does it mean? Here, I'll be adding this particular A with this G. So here I'll be having A plus G. I hope you must have started noticing. Then I'll be adding B and H, corresponding elements basically, and so on. Then I'll have C and I, so I'll have C plus I, and then I'll have D and J, so that will be D plus J. Then I'll be having E and K, so that will be E plus K, and then I'll be having F plus L, so that will be F plus L. So this is how the same order of matrix gets generated, but after this kind of addition or subtraction. I hope you are able to digest this particular part, that whenever I say that two matrices are being added or subtracted, this is how they are to be added or subtracted. Why did we learn that? We learned this particular part because we wanted to discuss this particular property where I'm saying that trace of sum or difference of two matrices is equal to sum or difference of their individual traces. Trace of A plus B will be equal to trace of A plus trace of B. And the same happens with the subtraction as well. Now, what happens when you apply this particular property? As of now, just learn this. I will explain this once we have learned the multiplication of matrices. As of now, my hands are bounded. I'll not be able to explain you how does matrix multiplication happens, although that is yet to come. We'll definitely explore that part in the later stages. But as of now, what you need to understand is that if I were to talk about trace of A into B, we have seen multiplication of determinants. We will now see after some slides how do matrix multiplication takes place. How does matrix multiplication take place? But what you all need to understand is that trace of A into B is equal to trace of B into A. Why? I'll explain this part with utmost clarity. Well, all of this we'll discuss only after we have discussed multiplication of matrices. So as of now, skip this part, but yes, as your cheat sheet, you can Keep this right there in front of you. Remember it, learn it, and start memorizing them. Next, trace of A will be equal to transpose of trace of A. What is it? I will discuss it. But as of now, just keep this particular property with you. What is transpose of a matrix? We'll discuss that whenever you interchange rows by columns. I hope you must have remembered it. While we have discussed the determinants, we had a discussion on transpose of a determinant. That same you do with a matrix as well. So whenever you're given a matrix and if you interchange its rows by columns, so if all the rows become column or vice versa, that all the columns become all the rows, in that case, the trace doesn't change. If you are able to understand my particular part, then you will be able to realize that trace of A will be equal to trace of transpose of A. Although once we discuss transpose, once we discuss multiplication of matrices, then you will be able to understand these particular properties with more clarity. Let's talk about the next part. What is the trace of an identity matrix? Now, first of all, let us explore what is an identity matrix. If you are having a scalar matrix, but that scalar matrix has all the diagonal elements as 1, that scalar quantity, if it becomes 1. For example, if I'm dealing with a 3 by 3 scalar matrix, what does it mean? Its principal elements will be same, which I have fixed it to be 1, and all the other entries are 0. Then this matrix is called an identity matrix of order 3. So we usually write it as I3. What do I mean by I2? A 2 by 2 matrix, diagonal elements will be 1, 1, all the non-diagonal elements will be 0, 0. What will be its trace? Can you help me with that? Yes, its trace is going to be 1 plus 1 plus 1, that will be 3. So I hope you are realizing this particular property as well when I say trace of an identity matrix of order n, because we will be having square matrices. So square matrices on its principal diagonal will have n number of ones, and when those n number of ones are added, I'll get their sum as n. I hope these properties are very well understood by you all. Next property. What you also need to understand here is that there is some confusion over here. Let me just rectify that particular part or mistake over here. See, let me just make a certain correction here. There is some problem. Just give me a second, students. Here, if I were to make you understand this particular result, it means that, let's say if I'm writing trace of A into B, then I cannot, expand it in this manner that I find the trace of A and then I find the trace of B and then I multiply them. No. This trace can be expressed in terms of addition or subtraction in this particular manner, that whenever you have trace of A plus B or A minus B, then you can have trace of A plus trace of B or trace of A minus trace of B, depending whatever was given here. But what you need to understand is, if you are asked the trace of AB, then this trace cannot be taken in this manner, that trace of A times trace of B, that will be mathematically wrong. You will yourself start understanding this once you have understood all the things. But as of now, what you need to understand here is that trace of AB is not equal to trace of A into trace of B. Although this is true for addition or subtraction, but for multiplication, this is not true. Although when it comes to multiplication, you can have trace of AB or trace of BA, both will be same. Why? You will learn and understand once you understand the matrix multiplications. Don't worry about that part. Now, let us talk something really crucial, something really important with IIT JEE, which IIT JEE loves asking. IIT JEE keeps on asking. Again, another very crucial property which will be understood by you with its proof when you understand the concept of inverse. But since we are discussing trace right off as of now, let us understand this particular part as well. What does it mean? This particular property means that trace of A will remain same even if you multiply a matrix with a matrix, let's say pre-multiplication, and that product is multiplied, the post multiplication, by inverse of that matrix, other matrix C. For example, I have a matrix B here, and I have a different matrix C here. Let's say I multiply this B matrix, pre-multiply with that matrix C, and I multiply this B matrix post multiplication by C inverse. And then I wish to take its trace. Although for multiplication of matrices, confirmability should be there, although which is not a matter of concern. So I am talking all of this once the confirmability is ensured. So I know that this product will be confirmable, which means the product will be possible, matrix multiplication will be possible, but let's say I have a certain matrix B and I pre-multiplied with the matrix C, and then I post-multiplied by matrix C's inverse. And then I wish to take its trace. Then what you need to remember is that you need not do all this. Trace of B will be equal to trace of C times B times C inverse. Sir, why are we discussing this result? Why is it important? Please have this thing in your mind. IIT JEE constantly keeps on asking question on this particular concept, where they give you find the trace of a matrix C, B, C inverse to the power 100. So in that case, what you need to understand is you will be asked to find the trace of B to the power 100, because C, B, C inverse and B, C, B, C inverse and B are same when talked in terms of trace. I'm not saying that will be same. I'm not saying B pre-multiplied by C post multiplied by C inverse give you B only. No, that is not what I'm saying. What I am saying here is very clearly that trace of either B or CBC inverse will be same. As of now, even if you are not seeing being used, have faith in me, just have faith in the process and remember this as a result. Later on, once we start doing previous year's questions, then I'll make you realize that this is one of those properties which we have learnt while discussing trace. Now let us apply that. And there you will realize that a category of huge, amazingly lengthy questions can be done within seconds if you remember this particular property. So this is not just a tool which I'm asking you to remember. This is one of those special tools which will help you in reducing your solving time by a huge margin. So remember this particular result. It plays a very crucial role in your problem solving approach. Now, if you have understood all these methods, let us proceed further. Let us proceed ahead with some more conclusions, with some more learnings. What are they? Here, let's say I'm multiplying certain number of matrices. How does it happen? We'll learn that, don't worry about it. But let's say if I am asked to multiply certain number of matrices and then I am asked to take their determinants. Now usually how do we write? Determinant of matrix ABC, this is how we write it. In a different world, determinant can be written with these two modulus kind of a sign as well. Well, here this does not represent the modulus sign. This is not the mod of these matrices ABC or A1, B1, A1, A2, A3. Here this sign represents determinant of A. So A will be a matrix, and if I put these two lines after and before A, then it represents the determinant of A. So determinant will be taken off as square matrix only. So if I'm given a square matrix and if I'm asked to find out its determinant, which we have already discussed, then another property which I'm constantly strictly asking you to remember is that whether you multiply certain number of matrices first and then take their determinant, or you take their determinants individually and then multiply them, will get you the same result. I hope you are understanding this particular property. Which I'm asking you to remember is, let's say determinant of ABC is what I'm asked. So instead of finding the product of A, B and C first and then finding its determinant, what you can also do is you find the individual determinants of A, B and C and then take their products. That will yield the same result. That's exactly what I'm saying very clearly. Did you get that particular part, students? I hope you are having a very good clarity on this particular property. Well, there comes another property, a very crucial property, which has its own application, which I'll explain with this particular part. Please understand, this again is a very, very amazing and a very crucial property, which will play a very crucial role in deciding a lot of properties based on the adjoint. So remember this will be a result which I'll constantly keep using, and IDJE keeps on asking questions based on this property. A very subtle, a very minute, a very simple property it is, but it has its own wide range of applications. Now, first of all, let us understand that minute property here. For example, let's say I have a matrix A, which is a square matrix for a while, A, B, C, D, right? Now, this matrix, of course, looks like a matrix of order 2 by 2. A square matrix is basically I'm taking because I'm going to take its determinant. Now, let's say I multiply this matrix by K. So, what will be KA? I hope you can help me with that. That will be KA, KB, KC, and KD. Did you all get that part? Now, there can be determinant of A which can be found very easily. I hope you know how to find the determinant of A. We have learned the expansion that if there is a matrix A which is a square matrix of order 2, I can find its determinant by having this AD minus BC. We have already learned this part and you have mastered it possibly by now. Now, when I talk about this part, can I find the determinant of KA? Before finding the determinant of Ka, let's write this Ka or determinant of Ka. What will it be? It will be Ka, then Kb, then Kc, then Kd. Now, what do we know about determinants? Do you remember what we know about determinants? From their properties is that from a determinant, from either any row or any column, elements can be taken common. A factor can be taken common. That's exactly what I'm asking you to do here is that here, if you pay attention, can you not see that first row has this K common and second row also has this K common, which can be taken out. Or you could have said that the first column has this K and the second column has this K. So I can take this K common from the first column. I can take this K from the common from the second column. What does it mean, students? It gives me a very simple idea, a very simple result. From first column, I'm taking this K out. From second column, I'm taking this K out, which means I am taking K square out, and then now I am left with A, B, C, D. Determinant of this A, B, C, D, which is nothing but determinant of A. Were you able to understand something very clearly with this demonstration, with this explanation, with this particular illustration? My idea, my intent was very simple, to make you understand something very straightforward, which was if I had a matrix A which was order 2 and I multiplied this matrix A by a scalar quantity, let's say K, and then I took its determinant, then its determinant will be K to the power order of that matrix, which was 2 here in this case, times determinant of A. Did you get that part, students? If you haven't, let me explain it with this particular statement which we are given here. That is very simple. If K is a scalar quantity, A is a square matrix of order n, then determinant of Ka should be equal to, yes, you know it, K to the power n times determinant of A. Why are we having K to the power n? Because that K will be taken common either out of all the rows or all the columns. Did you get that part very clearly, students? I hope you're able to digest these two properties. Trust me, students, these are not just two ordinary properties which I am just saying for the sake of saying or taking this chapter in one shot. These are two of those important properties which are laying the foundation of the upcoming topics which we'll be exploring further in this one shot. So I'm very strictly asking you all to remember these properties. Although with practice you will start understanding them, but I will now start using these properties with a sense that you have understood them and you know them. So I hope that I have this consent from you that I can proceed further with this particular part, understanding that you have understood this. Shall I? Now, let us proceed further. What do we have next? Let us explore the next part. Now, What is the equality of matrices? When do you say that two matrices are equal? Again, a very crucial concept. Questions are asked on it. How do we say that two matrices are equal? Two conditions. First, that they should have the same order. If the matrix A is of order 2 by 3 and the matrix B is order of 3 by 2, then equality has no sense at all. You need not check or delve further. But if A and B are of the same order, then they can be equal, and then for equality there comes another condition. But I hope you're realizing the first condition. If order of A is 2 by 3, order of B is also 2 by 3, then only they can be compared. Then only I'll proceed further and check whether they are equal or not. So our first check will be checking their orders. So orders should be same. If two matrices have the same order, and which means the same number of rows and columns, then I'll check further. What is the second condition? The elements in the corresponding positions of the two matrices are equal. The elements in the corresponding positions of the two matrices should be equal. I hope you have gotten this complete clarity that if I am having a matrix A here which has certain number of elements, let's say 2 by 3 matrix it is. What do you mean by 2 by 3? It will have number of rows 2, number of columns 3. For example, A, B, C and then D, E, F, right? And if there is another matrix, B which is again of order through 2 by 3. So yes, the scope of A and B being equal remains true, holds true. Now what I need to do further, or the next step will be comparing their corresponding elements. Let's say in a question, in a statement, I am given that matrix A and matrix B are equal. Matrix A and matrix B are equal, and I'm given certain values in this, matrix B, for example, 2, -3, 4, 0, 1 and 5. Now, if I were to ask you what could be the values of A, B, C, D and F, without any hesitation, you would come up with a response saying that, sir, if A and B are said to be equal, as we can see, their orders are also equal, which are supposed to be, if they are said to be equal, which means their corresponding entries will be same, which means A will be 2, B will be -3, C will be 4, D will be 0, E will be 1 and F will be 5. So that is what is needed to be true if I am told that these two matrices are equal. So I hope equality of matrices is very well understood by you all. Now, proceeding further, what do we have next? Addition of matrices, as we have already discussed. I don't think I need to explain this part further. Scalar multiplication is also we have already explored, so I don't think we need to discuss this particular part further, because trace of a matrix has already covered this part. Although I'll give you more clarity on this, which you must be able to understand it more clearly. For example, if I have two matrices A and B which have the same order, m cross n, m cross n, and k and l, let's say, are certain scalars, then what holds true? K times A plus B will be equal to K plus KB. What you are all able to understand is whether you add two matrices first and then multiply all the elements of that summation by a scalar quantity, or you first of all multiply that scalar to each of their elements of those two matrices and then add, they yield the same result. In the same fashion, whether you add or subtract two scalars first and then multiply them by a matrix, or you multiply those scalars first to that matrix individually and then add those results, will give you the same result. I hope this distribution and all these properties are very well understood by you all. Whether KLA is being done or KLA is being done or LKA is being done, they will yield the same result because they won't make any difference at all. Similarly, minus KA or minus of KA or K of minus A, that will also give you the same result. Similarly, this here is the minus 1 of A or minus 1 of A will give you, 1 into A will give you A, or minus 1 into A will give you minus A. That gives me one more thing that needs to be, that needs to be explained to you, which I'll explain later, because that comes under the category of matrix multiplication, which I'll do later. But I hope this part is completely understandable. Now, proceeding further, scalar multiplication is understood by you all. Let's understand the next part, where I say multiplication of matrices. Well, this part of this video should now be watched with more focus, with more attention, with more clarity. Because so far whatever we have discussed is very well understood by you all. That is what I'm very much sure of, because that was something really simple and easy. But from this topic onwards, this chapter start getting a little more complicated. It starts getting a little more comprehensive, more detailed, more thorough. So here you should be more focused, more attentive, and more alert. So watch it with being more cautious, because a lot of things will happen now. A lot of properties will be used. A lot of things will be applied simultaneously. And that's where students start giving up. They start getting confused. So I'll try to keep things as simple as possible. My expectation remains very simple. Watch this video completely. Watch this video thoroughly. Do not skip any part now at least, and go through everything in a very, very, very attentive manner. Don't skip any part from now onward. We are beginning our discussion with multiplication now. So let's have a look at this part. How does multiplication of matrices take place? Have a look at that. If A and B, if I'm given A and B, which are basically two matrices, which are said to be conformable for the product AB. Now, what is the meaning of conformability? That is what we'll be discussing. Conformability is a very, very simple, straightforward concept. What is it? Let us have a look at that. Let's say there is a matrix A. There is a matrix A which has a certain order. Let's say this has an order. For example, let's say this is of order 2 by 3. What does it mean? It will have 2 rows and 3 columns. I hope this is very well understood by you all. And if there is another matrix B which has, let's say, order 3 cross 1. This matrix B has the order 3 cross 1. And I am asked to multiply A with B. So here what matters most is this order. A is the pre-factor, B is the post-factor. A is pre-multiplied to B, B is post-multiplied to A. So order is playing a very crucial role in matrix multiplication when both of them are matrices. How? Here, what you need to understand is that you are wanting to multiply A with B. So you are wanting to multiply A with B. Now, conformability comes into picture. When it was about addition or subtraction, the order was supposed to be same. Then only two matrices could be added or subtracted or compared. So for addition, subtraction or comparison, conformability was different, or the parameters of conformability were different. But when it comes to matrix multiplication, conformability is a totally different concept. How and why? Let us understand what, then how and why we'll explore later. First, understand what is the meaning of conformability of the product or for the product. Here, when you are willing to multiply these two matrices A and B, then this pre-factor with which you are multiplying here, this A which is on the left, this B which is on the right. So here A had 2 as the number of rows, 3 as the number of columns. B had 3 as number of rows and 1 as number of columns. Here what you very clearly need to understand is that the number of columns this A has and the number of rows this B has should be same. They should be same. If they are same, then only product AB is possible. Then only multiplication of AB is possible. Then only AB is conformable or possible. I hope you're able to understand this particular part. Why and how, that I'll explain later when I start making you understand how does matrix multiplication takes place and why is it necessary that this condition was applied. That I'll explain later. As of now, just understand what is needed to be done to ensure that two matrices can be multiplied. Along with this, there is one more very crucial result which you all must remember is that after the multiplication, matrix multiplication AB takes place, once the AB happens, how is it done? That I'll explain later, don't worry about it. But once you have done this matrix multiplication, that matrix will have the order 2 by 1. So this AB, when produced, when generated, when this product is done, that product will be of order 2 by 1. So conformability, that when will this happen, whether this can be done or not, that can be assessed by this particular check. And what will be the result, what will be the outcome, what will be the order of that can also be evaluated. A very simple language I'm mentioning here. If algebraically I wish to put, I'll say that I have two matrices X and Y. Let's say X has the order, let's say M cross N, and Y has the order P cross Q. So what we have learned so far, students, here is that if I want to multiply X and Y, if I want to multiply X with Y, X is the prefactor, Y is the post factor. So here we have already discussed that the number of columns of X and the number of rows of Y should be same. So if I wish to multiply X and Y, what I need to ensure is that N and P would be same. The second thing which I can deduce from this particular observation is that product X and Y, if we are able to generate by ensuring the conformability, that product will have the outcome as M cross Q. So I hope this makes a lot of sense. I haven't explained how do you multiply two matrices. I haven't explained that part at all. What is needed to be done? No, that is not explained at all so far. What I have explained so far is that when do you have this complete assurance that two matrices can be multiplied, that check, that validation is what I'm trying to explain in this particular part. I'm again coming up with a very simple conclusion here. The first statement was very simple, students. A and B are two matrices which are said to be conformable for the product AB. So this conformability I have explained so far. I hope there is no confusion on that. Now, if the number of columns in A, called the prefactor is equal to the number of rows in B called the post factor, otherwise non-conformable for multiplication, and then matrix multiplication won't take place. Are you able to get this particular part? My conclusion first of all remains very simple. My question remains very simple. Are you able to digest the conformability of matrix multiplication? Then only we'll proceed further or ahead. Now, let's talk about the next part. When do you say that AB is defined? AB will be, I hope you must have realized by now that AB and BA are not going to be same. Because AB will be something totally different, BA will be something totally different, and BA should be possible. If AB is possible, then it is not necessarily true that BA will also be possible. For BA to be possible, we need its own conformability. I hope you're understanding. So if I want to check whether A into B, where A is the prefactor, B is the post factor, can be done or not, then I hope you know that number of columns in A should be equal to the number of columns in B. And if somebody says then check whether BA is possible or not, then again I'll go with this. B is the prefactor now, A is the post factor now. In that case, I'll say the number of columns in B should be equal to number of rows in A. So AB and BA are totally two different terms, two different matrices now, two different products now. I hope you're getting this particular part. I am again keeping it with myself as of now, matrix multiplication. How? That is not what I'm explaining right now. What is the validation? What is the check? That is what I'm explaining. What are the different precautions you should keep in mind? That is what I'm explaining right now. So I hope a very good clarity is brought by you so far. Now, let us understand this matrix multiplication so that you start understanding these particular properties. For example, I have a matrix A. Let's take a very simple matrix A. Let's say it has the order 2 by 3. What does it mean? 2 by 3 means it should have 2 rows and 3 columns. For example, here it will have 3 columns, right? So let's say 2, 1, 0, 3 columns, and the second has 3, let's say -1 and 4, right? So these are the other number of elements I am having. So these are the 2 rows and 3 columns in this matrix A we are given. Now what about matrix B? Let's say we are given the matrix B as well. Matrix B is, let's say, of order. So if I want to find the product AB, what I need to ensure is that whatever number of columns A had, that same number of rows B should have, so that conformability is ensured. So if A had 3 columns, B should have at least and exactly, not at least, exactly 3 rows. So whatever number of columns B will have, I don't know, but B will have minimum 3 number of rows, and let's say it has 3 number of columns. So B is a 3 by 3 matrix, let's say, for a while. It will have its own elements, for example, 1, 2, let's say -4, then we have 5, then we have 7, then we have 1, then 2, then 3, let's say, and then 0. This is, let's say, matrix B. And now I am willing to find this product AB. So first of all, is it conformable? As we already know, here the number of columns A has and the number of rows B has are same, which means they are conformable, product can be done. Along with this, the product will have the order 2 into 3. That is also can be deduced. Now, that will actually help you in understanding a lot, because when you know that product will be of order 2 by 3, it means I'll be having 2 rows and 3 columns. Why? 2 into 3. I hope this part is very well understood by you all. Now, what will be that 2 into 3? Let's start exploring that now. Here, in determinants, we could have the multiplications row by row or row by column, column by column or column by row. In matrices, that doesn't happen. Matrices have only one way of getting multiplied. That is also row to column. What does it mean? Let me start explaining it one by one. First of all, you begin with this first row. You begin with this first row, 2, 1, 0, and you multiply, and then you multiply the elements of that first row with the first column of this B. So first row of A is chosen, which is 2, 1, 0. First column of B is chosen, which is 1, 5, 2, and then corresponding elements are multiplied. First with first, second with second, and third with third, and then they are added. That will give you the first element of this product AB. I hope you are able to understand this particular part. Here, what I'm trying to make you understand is 2 into 1 will be 2 plus, I'm really sorry, I repeat, this 2 into 1, this will be 2 plus 1 into 5 will be 5 plus 0 into 2 will be 0. Did you get that part, students? And I hope I did not write 2 plus 5 plus 0 should be simply 7. Are you able to get that? Now, what am I supposed to do next? Next portion will be, I'll keep this row as it is, 2, 1, 0, and then I'll multiply this row with this column, and that element will appear here. I hope you're getting it. Similarly, I will still keep this row with myself, and then I'll multiply it with this, and that product will give me this element. So 3 rows will be completed. Now I'll switch to the second row, and then this second row will be multiplied with the first column, and that product will give me this element. This row again will be multiplied with this column now, and that will give me this particular element. I hope you're getting it now. And then finally, I'll multiply this particular row with this column, which will give me this final element over here. So matrix multiplication, how do we do that? I hope that part is also understood by you all. So how do I write the next set of elements, students? I hope you're getting this clarity. This first row I have chosen. Now I'm multiplying it with the second column. So I hope you can see it. 2 into 2, 4. 1 into 7, 7. 4 plus 7 is 11. Plus 0 into 3, 0. So I'm left with 11. So I'll be writing an 11 here. I hope no confusions on that. Are we clear on this particular portion, right, students? Then, what do we have next? I'll fetch you the next conclusion. What do? Now again, I keep this particular row only, but with this row, I'm going to multiply this particular column. Now, I hope no confusions on that. So what is next? 2 into minus 4, that will be minus 8. 1 into 4, sorry, 1 into 1, that will be 1. So minus 8 plus 1 will be minus 7. Minus 7 plus 0 into 0 will be 0. So here it will be 0. That is what I'm supposed to do. I'm really sorry. I think I have said 0. No. I think it was minus 7. Let me check it. 2 into minus 4, minus 8. And 1 into 1 is 1. So minus 8 plus 1 will be minus 7. I'm really sorry. Either I can calculate or write or explain. But I'm doing all these 3 things simultaneously. I'm calculating, I'm explaining, and I'm writing. So I am very much prone to committing the errors. I hope you realize, if by chance if I commit such silly errors, I hope you'll realize that that happened because of this particular part which I'm trying to do simultaneously. So here in the examination also you should remember this as a learning, that don't try to multitask. Do one thing at a time. It is very important that you realize and understand that human brain cannot multitask. We are not wired to multitask. Please understand. And that's the problem. that when we start doing things simultaneously, a lot of things simultaneously, our brain cannot process a lot of things simultaneously. And that's when your brain chokes. That's when you go brain fade. That's when you actually are not able to do a lot of things. So always focus on doing one thing at a time. When it comes to doing such critical things, very simple, straightforward calculations, then also you should stay focused and do one thing at a time. Don't skip any part, because such silly errors will cost you heavily, because you'll do this entire question with utmost integrity and sincerity, but when it comes to calculation, you do it a little bit casually and there you commit the errors and the entire solution goes in vain. So stay aware of this particular part, that you don't commit such silly errors with this advantage of multitasking, which is absolutely not a advantage at all, which if you are able to understand that this is a disadvantage rather. Now let's come back to the discussion we were having, a very straightforward discussion we all were having. Now the matrix multiplication, the second row should be 3 minus 4, 3 minus 1, 4 will be multiplied with this 152. I hope you are understanding why. So this 3 into 1 will be 3, minus 1 into 5 will be minus 5, 3 minus 5 will be minus 2, and then 4 into 2 is 8, 8 minus 2 is 6, so that 6 should be written over here. Next, 3 minus 1, 4 goes to 273. I hope you are able to understand this part now. So 3 into 2, 6, minus 1 into 7 is minus 7, 6 minus 7 is minus 1, and then 4 into 3 is 12, 12 minus 1 is 11, so I'm supposed to write another 11 over here. What is next? This 3 minus 1, 4 goes to minus 4, 1, 0. I hope you are understanding it now very clearly. So the next result will be 3 into minus 4, minus 12, minus 1 into 1, minus 1, minus 12, minus 1, minus 13, and then 4 into 0 is 0, so I'm left with minus 13. I hope everything related to matrices is understood by you all. What? First of all, conformability, then the order of the product, then how do we evaluate that product? What is the meaning of matrix multiplication? How does that happen? How does it take place? Everything related to this, I hope, is understood by you all in a very straightforward manner. Shall we proceed ahead now? Can we discuss some properties related to multiplication of matrices? Well, here we are. That's your first property. As we have already discussed that this matrix multiplication, if I do AB, then BA could be possible, could not be possible. And when it comes to AB being equal to BA, that is not necessarily true. I hope you are understanding why. From the concept of matrix multiplication, I hope you are realizing how much efforts are needed to bring AB, and I hope you are realizing to get BA, conformability, then matrix multiplication, and then I hope you can very easily evaluate in your brain only that AB will not be necessarily equal to BA, even if BA is possible. I hope you are getting this particular result. But there is a catch. Now, let's say if I am dealing with a diagonal matrix. So diagonal matrix, square matrix, and if there are two diagonal matrices of the same order. So we have a matrix A, we have a matrix B, let's say for a while, and these are the two diagonal matrices of the order 2. So both of them are of the 2 by 2. Now, if I am having these two diagonal matrices and if I find AB or BA, trust me, they are going to be same. You do it algebraically or I illustrate it, I explain it within illustration. So if I'm having A and B, now how does AB take place? I hope you know. 1 0 with 3 0, that will be 3, we can see it here. Then 1 0 0 4, I hope that is 0, that will be 0. Then we have 0 2 3 0, that will again be 0. I hope you know matrix multiplication I'm talking about. Then you have 0 2 with 0 4, that will be 4 into, that will be 8. I have done AB. Even if I do BA, what is BA? BA will be, VA will be, I'm really sorry, it should have been B. So this is B over here. I hope you're getting this part very clearly. So if I do BA, now what is the meaning of BA? BA means rows of B and columns of A. So 3 0 into 1 0. Then 3 0 into 0 2. Then you have 0 4 into 1 0. Then you have 0 4 into 0 2. That will again give you the same result, 3 0 0 8. So whether it's AB or BA, that will be same only when you have diagonal matrices of the same order. In that case, commutative A and B will be commutative, which means either AB or BA will be same and equal. But this product is not commutative usually, which means AB will not be equal to BA. That is what I'm trying to make you understand. There is one more very simple fact which you should remember, that in case if you are able to find that AB is equal to minus BA, this will not happen very often, but in case if you are able to find that AB is equal to minus BA, then we say that A and B are anti-commute. Just remember this as a result. Although now this part, if you are all able to understand, let's understand the next property. What does it say? Matrix multiplication is associative if conformability is assumed. So if conformability is there, then they are associative in terms of product. What does it mean? If I do not change their order A, B and C, so whether I find this product BC first and then I pre-multiply that product by BC by A, or I find this product AB first and then I post-multiply that product by C, that will give me the same result. So it is associative in nature. This matrix multiplication is associative. But what you need to understand is that this order must not change. A, B, C, A, B, C. So whether I do this BC first and then this A comes pre, or this AB is done first and then C comes post, both are going to give me the same result. But I hope you are understanding, conformability is another criteria which should be followed. I hope you are understanding why and how. Now let's talk about the next property, property number 3. Matrix multiplication is distributive with respect to addition or subtraction. What does it mean? If you have B plus C pre-multiplied by A, that can be written as B pre-multiplied by A and then C pre-multiplied by A, or plus or minus whatever is there. So over addition or subtraction, distribution is possible in matrix multiplication, but still you need to ensure that pre and post remains different. What does it mean? If here B plus C is pre-multiplied by A, then B and C both individually will also be pre-multiplied by A. So order, this pre or post, plays a very crucial role and you should stay aware of it. Next, similarly, when A is an M cross N matrix, then when A matrix is multiplied by an identity matrix will again give you an A. This is what I was trying to mention when I was talking about this scalar multiplication, but I'll just try to give you this idea that identity matrix is like 1. So for example, let's say if you have a matrix A, if you are having a matrix A, let's say, and this matrix A is multiplied by an identity matrix. So this matrix A and this identity matrix I, conformability is assumed. So I'm not bothering about conformability time and again. I am assuming that product is possible. Product is possible means conformability must be there. So whether I post multiply this matrix A by this identity matrix I, or I pre-multiply this matrix A by this identity matrix I, in both of the cases, the identity matrix won't do any change, won't make any change. You do it by yourself, you can assess that by yourself, that identity matrix behaves like 1. The way 1, whenever multiplied to any number, does not change the product, the number remains same even after getting multiplied by 1. In the same fashion, in the world of matrices, that job is done by the identity matrix. So identity matrix behaves like 1 in that sense, that whenever you pre or post multiply a matrix by an identity matrix, then it will generate the same matrix A. Conformability I am not mentioning, I am assuming that conformability is there. In that sense, I am not giving you time and again. Now, let us proceed further with the next property here. Property number 5. What does it say, students? It says that if product of two matrices is a zero matrix. Now, usually what did we used to conclude? That whenever product of two numbers is 0, either or both of them should be 0. But here in this case, what you need to understand, that product of two matrices can be 0 without either or both of them being 0. Did you get my language? My language remained very simple. I'll try to give you an example through which you'll be able to understand. Let's say there is a matrix 1, 1, 2, 2, and there is another matrix minus 1, 1, 1, minus 1. Now what do we have here is that I take their matrix multiplication. So how do I do? This is pre-factor, this is post-factor. So 1, 1 into minus 1, 1. So minus 1 plus 1 will be 0. Then 1, 1 into 1 minus 1, that will again be 1 minus 1. So that will again be 0. Then 2, 2 into minus 1, 1, that will be minus 2 plus 2, that will be 0. And then again 2, 2 into 1 minus 1, that will be 2 minus 2, that will again be 0. So I got a null matrix because all the elements are 0 here. I got a null matrix. But what I'm trying to make you understand is, despite getting a null matrix, mind you, this is not 0, this is O here. Despite getting a null matrix, we all can very easily evaluate, assess, know, and observe that both of these or neither of them were 0. Are you able to understand this very simple statement that whenever you get the product of two matrices to be a null matrix, then you cannot conclude that either of them would have been 0. No, that cannot be said. Then sir, why are you teaching this to us? Well, there is one conclusion which you can still draw. What is that? Let me talk about that. That conclusion is pretty simple, that let's say if matrix A and matrix B when multiplied gave you a null matrix O. Let's take determinant on both sides. So what does it mean? It means determinant of AB should be equal to determinant of O. So determinant of O, which means null matrix, will be 0. So on the right hand side, I'll have this 0. And determinant of AB, as we have already discussed, whether you take the product first and then you take the determinant, or you take their individual determinants and then multiply, will give you the same result. So determinant of AB can be written as determinant of A times determinant of B. What does it mean? It means now I am not in the matrix world, I am in the determinants world, and in the determinants world they are simply numbers, which means this number into this number is 0, which means either of them should be 0 or both of them should be 0. I hope you're realizing it is helping us in understanding that here either determinant of A will be 0 or determinant of B will be 0. If you don't believe me, you can assess it by yourself by finding the determinants over here. I hope you can see it very clearly that this determinant will be 2 minus 2, 0. This determinant over here will be 1 minus 1, 0. So both of them are 0. I'm not saying both of them will be 0. Either of them will be 0. What I'm trying to make you understand here is, remember a fact. I am saying it is a fact that whenever you multiply two matrices and their product is null matrix, whenever you multiply two matrices and then their product is found to be a null matrix, then what you will be able to conclude is that those two matrices, at least one of those two matrices, determinant will be 0. That determinant of at least one of those matrices will be 0. That's exactly what I have proved mathematically as well. I hope you will remember this as a result, and this will be used at a lot of places if you simply remember this as a result. Now, that's exactly what we are demonstrating here. So whenever you have two matrices and their product is a null matrix, then this should always be learnt and remembered that either of the matrix will have the determinant to be 0. I hope this part is very well understood. Converse is not true. Now, what is the meaning of converse? That if determinant of A or determinant of B is 0, then you cannot say that their matrix multiplication will give you a null matrix. No, no, no. What you should always understand is that what is said by the teacher and what is interpreted by you, and what is also not said by me should also be understood by you, that this is not what I'm trying to say here. What I have said, A into B is a null matrix. If A into B is a null matrix, then either determinant of A or determinant of B will be 0. What some of you may have interpreted it as that if determinant of A or determinant of B is 0, then A into B will be null matrix. No, I did not say that at all. That is the problem. I hope you're understanding that what should you interpret if then result. I didn't say if and only if. I said if then. I hope you're understanding these statements. Mathematical reasoning is basically I'm discussing here. Well, if that part is very well understood by you all, let us proceed further. Let us understand the next property, property number 6. What does it say? Multiplication of matrix A by a null matrix if conformable with A, then of course it will yield a null matrix. So you had a matrix A which had the order 2 by 3. You had a null matrix which had the order 2 by 3. So I can very clearly see, I'm really sorry, this is not 2 by 3. This is mistakenly written over here. It should have been here 3 by, sorry. Number of rows are 2, number of rows are, I think there is something wrong because this, yes, so that was correct. This particular portion was wrong here. This is not 2 by 3, this is 3 by 2. I'm really sorry for that. So here it should have been 2 by 3, right, students? So this is 3 by 2. I repeat, a very simple conclusion that here number of rows are 3, number of columns are 2, number of rows are 2, number of columns are 3. Now, if I am doing this matrix multiplication, is conformability assumed? I can see that this 2 is equal to this 2. So, number of columns A has and the number of rows B has, so O has, are equal. So, conformability is there. So, after finding this product AO, you will yourself will realize that first of all, what will I do? I'll choose the rows from A and columns from O. So 3, 4 with 0, 0, then 3, 4, sorry, then 5, 6 with 0, 0, then 7, 8 with 0, 0 will give me these zeros. I hope you can see here. There is no confusion on that. In the same fashion, this 3, 4 with this 0, 0, this 3, 4 with this 0, 0 will give you these two zeros. This 5, 6 with this 0, 0, 0, 0 will give you these two zeros. This 7, 8 with these two 0, zeros will give you these two 0, zeros. Even without saying all of this, what I'm trying to make you understand is that if I'm given a matrix A, I'm given another matrix O, and these two matrices are multiplied, then what we need to understand is if conformability is assumed, then this product is going to be a null matrix. So in the real world, we have this phenomena, very simple phenomena. If a matrix is multiplied with 0, if a number is multiplied with 0, it gives you 0. In the same fashion, in the matrix world as well, if a matrix is multiplied with the null matrix, if conformability is assumed, then this product will also be a null matrix. I hope this part is very well understood by you all. Now, proceeding ahead, what is next? What do we learn next? The next property. What is the next property? Property number 7, multiplication of matrix by itself. So it simply is same as what we have been doing. So let's say if I'm multiplying a matrix A with itself thrice, so A into A into A, well, this can be written as A cube. Similarly, let's say if I'm given a matrix A multiplied with itself 3 times and then that product should be multiplied with itself 2 times. Well, that can be written as A to the power 3 into 2 as the simple algebraic properties we have discussed, and it will be equal to A to the power 6, which means A should be multiplied with itself 6 times. That will also give the same result, which should be very easily understood by you all. Nothing new is there in my understanding. Now, let's talk about further more details, more learnings, which are again very crucial in understanding matrix multiplication and a lot more. What is that? Let's have a look at that. Here, if I is a unit vector, then I square, I cube, I to the power anything will give you I only. I is like 1. So 1 raised to the any power will give you 1. That's how you can remember it, right? Next property, if A and B are two matrices of the same order, that's where students commit error. It is not now limited to those simple identities which you have been learning. Let's say A plus B whole raised to the power 2 will be A square plus B square plus 2AB. No, that's not what is happening here. What you need to understand here is, I'll give you a very simple example. If you have A plus B whole square, then what does it mean? It means you are basically asked A plus B times whole of A plus B, and that's where pre-multiplication, post-multiplication, conformability, everything comes into picture. And let's say conformability for a while, let's say I'm not concerned about. Conformability is there. So even if you take this assumption in mind that yes, conformability would be there. Can I do matrix multiplication? Yes, let's begin with that. So here A into A. Yes, I can write that as A square. Then A into B, that will be AB. Then I'll have B into A, that will be BA, and we already know AB and B are not equal. So I cannot write it as 2AB. I hope you're getting it. Then you have this B into B, which will be B square. So that's a part where you need to understand that this is how A plus B whole raised to the power 2 should be written. In the same fashion, all these learnings, when you say a minus b square, that will be a square minus ab minus ba plus b square. A minus b, a plus b, it will not be a square minus b square. Again, you need to do a into a square, a into b, ab, minus b into a, minus ba, minus b into b, minus b into b, that should be minus b square. So these are some basic things which you should be aware of while applying such concepts or learnings. I hope we are very much clear on these things which we are discussing here. No confusions on that, I believe. A minus b, a plus b, a into a square, minus b into a, I think minus ba, a into b is ab, and minus b into b, minus b square. Yes, we are going great. And when you multiply a plus b with a minus b, I think it will be a square first, then minus ab, yes, then plus ba, and then minus b square. Yes, it's absolutely right. Or even a times minus b, or minus a times b, or minus of ab. It will be same. I hope minus 1 into this won't make any difference. So these are the properties where you need to understand that matrix world is a very different world. Here you cannot apply those rules as in, you are dealing with some simpler numbers. No, that's not what happens with matrices, because multiplication is not as simple as multiplication used to be, because here you are multiplying matrices, here you are not multiplying numbers, and that's the difference. Matrix multiplication is altogether a different story, and that's where you need to remember these particular properties or understand these properties. You can very easily remember them. There are some more terminologies I'd like to explore now. Then we'll come to the part where we'll be solving a lot of questions, because these terminologies, these definitions, these very basic, minute, simple details are used in questions, and they are clubbed together. So once they are learned, they are understood, then only we'll be able to solve questions based on JEE Mains and Advanced. So let's have a look at some more properties so that we understand them more clearly. What are we given next? Have a look at this. There is another category or type of matrices which is again a very crucial. So far what students are aware of is that what are the different types of matrices. They say row matrices, column matrices, horizontal matrices, square, diagonal, scalar, etc. They are not sufficient. Now comes idempotent, nilpotent, such matrices, and then they don't explain you such terminologies in the examination hall. They simply give you a question that this is an idempotent matrix, and then you are supposed to conclude by your understanding that what is the idempotent matrix. Now let's explore what is the idempotent matrix. So a square matrix A will be called an idempotent. So first of all, what you need to understand is that that should be a square matrix. Then when do we call it? If its square is equal to A, the matrix itself only. So whenever you have a matrix and when it is multiplied with itself, which means A square is basically I'm doing, and if it generates the same matrix, then I'll call it an idempotent matrix. Well, if that matrix, if A square is equal to A, then A to the power anything will be equal to A. Why am I saying so? Because let's say if I'm finding A to the power 5, then what will I do? I can write it as A square into A square into A. I hope you can see it very clearly. Then of course A square will be A square will be A, that will be A into A, then it will be A, because we know that A is an idempotent matrix. Well, in that case it will be A cube. Rather I'll write it as A square into A. That will again give me, what is A square? A square is A, so that will again be A into A. That will be again A square, but A square is A. So what I'm trying to make you understand is that whenever you're dealing with an idempotent matrix, A to the power n is always A, where n should be a natural number greater than or equal to 2. Did you get that part? Did you understand this part? That whenever you are dealing with an idempotent matrix, the basic condition is yes, that A square should be equal to A, but for an idempotent matrix, A to the power anything will give you A. So as soon as you get A square equal to A, you claim that this is an idempotent matrix, and A to the power anything will be equal to A. Now questions are asked on this particular part, that you need to observe certain patterns, and once you have cracked this particular pattern that A square is equal to A, you can conclude that now whatever power A is raised to, it will give me A. And that's how you deal with questions based on idempotent matrix. So first of all, I'm giving you all the basics, all the simple terminologies we are understanding, and then we'll start solving questions. But my concern here is, are you able to understand these particular concepts, these particular properties? Are you able to digest all of them? I hope they are not confusing at all. With that, let us look at the next category. What is it? Periodic matrix. The way we have periodic functions, in the same fashion we have periodic matrices. What is it? First of all, now we are restricting our discussion limited to the square matrices mostly. So again, we will have a square matrix, and then it will be said a periodic matrix when if a to the power k plus 1 will result into a, and here k should be a positive integer, and k should be a least positive value, for which a to the power k plus 1 should be a, and there this k is said to be the period of a. For example, let's say for an idempotent matrix, we got a square is equal to a. You may say, sir, for an idempotent matrix, we get a to the power 6 is equal to a. But no, I am looking for the least possible value. What is the least possible value? That least possible value is a square. I hope you're getting it. So here, that least possible value natural number is 2 here. So I am looking for a number which is the smallest possible number, natural number, right? So for this 2, a square was a, and there is no other number less than 2 for which a to the power k plus 1 will be equal to a. That k is 1 in this case. If that k is 1 in that case, then we say that it will be a periodic function with a period 1. And whenever you say that there is a periodic function with period 1, then rather than calling it a periodic function, which it actually is, I'll call it an idempotent function, idempotent matrix. I'm really sorry. So I hope you are understanding what do you mean by periodic matrix. A very simple concept it is. I'll say, let's say for a while a to the power 6 is equal to a, and 6 is the least value for which it is happening. 6 is the least value for which it is happening, for which means a to the power 5, a to the power 4, a to the power 3, a to the power 2, they'll not be yielding a. I am getting a to the power 6 equal to a, which means it is a periodic matrix. And here a to the power 6 is basically a to the power 5 plus 1 is equals to a. So that means 5 is that least value. So here period of a will be 5. So a is a periodic matrix where 5 happens to be the period of this particular matrix. But if the period is 1, which means k is 1, then a square will be a, which means it will be an idempotent matrix. I hope you are learning the difference, idempotent, periodic. Now let us move ahead with the next understanding, which is called the nilpotent matrix. Now what is nilpotent matrix? Have a look at that. Nilpotent matrix, again we are boiling down our restriction to square matrices usually or mostly now. So first of all, again I'll be dealing with a square matrix. Now this matrix will be called a nilpotent of order m, provided it satisfies the relation that a to the power k should be 0. I repeat, the order here will not be m, the order here will be k. So here just make this a small correction over here, that this should be k over here. A very straightforward conclusion that I repeat, a to the power k. So when a is multiplied with itself a lot many times, and with that a lot many times, after k times, after multiplying a k times, I got a nil matrix. So if I'm multiplying a with itself, and let's say after multiplying a with itself 5 times, a to the power 5 is found to be a null matrix. Then I'll call a to be a nilpotent matrix, where this k, or rather 5 in this particular case, will be the order of this particular nilpotent matrix. I hope you are able to understand this particular part and with no confusion. And of course, this k should always be a positive integral value. I hope you cannot put 1 by 2, 1 by 4 or minus 2 here. It should be a positive integral value. So a to the power 2, a to the power 3, a to the power 4, a to the power 5, and let's say a to the power 10 is found to be null, 0. And that should be the least positive value. I mean, before a to the power 10, let's say a to the power 8 also generated a null matrix, then you won't go with a to the power 10. You're supposed to write a to the power 8 is equal to null matrix, because after a to the power 8, all the results will be null. But here it happened for the first time when a to the power 8 became null. So if a to the power 8 is found to be null, 8 will be that index of that nilpotent matrix. I hope you are understanding this particular term without any confusion. Now there comes another term which is called involutory matrix. Now what is involutory matrix? Let's have a discussion on that. Again a square matrix. Then it will be involutory if it satisfies the relation that a square is I. So previously when a square was a, it was idempotent. But if a square is giving me an identity matrix, if you are multiplying a matrix with itself, and if it gives you an identity matrix, then I'll say that this matrix is an involutory matrix. So I hope you are learning the difference between idempotent and involutory. Any confusions on that? I hope no. What conclusions can be drawn on an involutory matrix? Let's have a look at that particular part. For example, let's say I'm having an involutory matrix. What is an involutory matrix, students? That A square will be A. A square will be A. So, sorry, this is idempotent. If A square is I, then this will be an involutory matrix. So, if A square is I, it is involutory matrix. What I do here is, I, let's say, multiply both the sides by A inverse. What is A inverse? A inverse is basically a matrix with which if I multiply A, then I'll get the identity matrix. So if I multiply A inverse, pre or post, whatever you wish to do. So let's say I'm doing post multiplication by A inverse on both the sides. So what will I get? A square I'm writing as A into A, then I'm writing it as A inverse, and then here I'm writing it as I times A inverse. So what is A inverse? A inverse basically, first of all, as of now, you can understand it as a phenomena that if you multiply A with A inverse, you get an identity matrix. So in numbers world, the way we have reciprocals, for example, the reciprocal of 2 is 1 by 2. So if I multiply 2 with 1 by 2, I get 1. In the same fashion, in the matrix world, if I have a matrix A, there would or there may exist an inverse of it, and if I multiply a matrix with its inverse, it will give me an identity matrix. How do you find the inverse? What are the processes? What are the properties? That is not a matter of concern now. That we'll understand or discuss later. As of now, I am just simply explaining a very straightforward concept that if A square is I, which means if A is an involutory matrix, what you can conclude here is that I'm post multiplying both these sides by A inverse. So here A into A inverse, I into A inverse. So A into A inverse will be I, so it will be A into I, and identity matrix into any matrix will be the original matrix, that will be A inverse, and from here A into I will be A because identity matrix does not bring or make any difference. So A is equal to A inverse. A is equal to A inverse. Now that's a very, very, very important conclusion which you must remember. Now what do I mean by that? A very simple property, students, that whenever you are dealing with an involutory matrix, then either this can be said or this can be said. Both are important results. First result was that if you are having an involutory matrix, A square will be I, or even if you are having a matrix equal to its inverse. So let's say you found a matrix and you found its inverse, and both are same, both are found to be same, the matrix and its inverse, then such matrix is said to be involutory. So there are two definitions of involutory. Either A square is found to be an identity matrix, or the matrix and its inverse are same. In both of the cases, you can claim that such matrix is said to be an involutory matrix. I hope there is no confusion on that front. Let us move ahead with the next concept, transpose of a matrix. Well, now we are moving towards the convergence of the theoretical part. Matrices has a lot of theory, and then they club a lot of questions. They merge all of these concepts all together. In a question, you will see transpose, you will see trace, you might see adjoint, you might see inverse, you might see scalar product of a matrix, you might see two matrices getting multiplied with, then a scalar comes into picture, then their determinant may be taken. So such concepts are merged first, and then questions are framed or formed. So that's what I'm ensuring. In the first part of this video, we are learning all these concepts first. Once you have understood all these basics, the nuances, the definitions, then we'll move to the part where we'll be understanding, applying these concepts through different questions and consolidating them. So yes, questions are yet to come, but first of all, go through all these basics, because without understanding these basics, straight away solving those questions won't make any sense. But once you have mastered these basics, once you have understood all these nuances, the simple details which are huge, which are a lot, then you'll be able to understand questions with a lot of ease and simplicity. Let's have a look at this particular part where we are talking about transpose of a matrix. A very straightforward concept. You might be able to recall that in the determinants, we have already discussed the transpose of a determinant. Well, there is no such thing as transpose of a determinant. It is actually transpose of matrices, which I have tried explaining you in the context of determinants, because there we needed it to understand different properties. Here, it is actually derived from the transpose of a matrix. Now, what is that? Let's have a look at that. Here, A very straightforward concept. Questions are asked on it. What is that? Let's have a look at this. We are given a matrix A which has the order m cross n. And for this matrix, let's say I interchange the columns and rows. I interchange the rows by columns or columns by rows or vice versa, whatever I'm saying, if you're able to understand. Then the attained matrix, the matrix which we have gotten by interchanging, is called the transpose of A, which is denoted by either AT or A dash or A bar. So such words are reserved here. So what I am trying to make you understand is that if you are having a matrix A which had the order m cross n, and if you interchange rows and columns, then you get another matrix which is called the transpose of this matrix, which is denoted by either A dash or AT, and that will have its order n cross n. I hope you're able to get it. If not, let me explain it with an example. For example, let's say there is this matrix A which has the order 3 by 4, which means 3 rows and 4 columns. So these are the 3 rows and these are the 4 columns. I hope there is no confusions on that. There are no confusions on that. How do you find the transpose? Do nothing. Take the rows, call them columns, or take the columns, call them rows. For example, first row I take, convert it into a column. Then I take the second row, convert it into a second column. Then I take the third row and convert it into the third column. When you do so, you get the transpose of the matrix A. And I hope you can observe, if it had the order 3 by 4, the transpose will have the order 4 by 3. Nothing has happened. Simply, you have changed or interchanged rows by columns. That's all you have done. And when you do so, you get the transpose of a matrix. Simple, I hope it was. Now, sir, why or what is the application of it? Trust me, it has its own significance. We have learned the minor and cofactors. That exactly what we'll learn in the context of matrices as well, which I'll not explain again, because we have learned finding minor and cofactor in determinants itself straight away previously in the last lecture. That learning, when applied with transpose, gives you something related to the inverse. We'll discuss that later, don't worry about that. But there is a huge role of transpose in the journey of matrices. As of now, we are building that foundation. I hope you know this concept of iceberg. What is the concept of iceberg? The concept of iceberg is a very important concept, because let's say there is this sea. I hope you know Titanic basically drowned because of this icebergs concept. So here iceberg is somewhat like this. So the tip of the iceberg looks very simple, very tiny, very small, and the captains, the people who are basically, sailing the sea, may feel or think that the ship can basically run over this tip of the iceberg, which is basically very small in nature, and that can be destroyed by the hugeness of the ship, because ship won't get affected by it. But what usually they don't realize is that iceberg has its own huge, amazing foundation, and because of that foundation, that small tip of that iceberg holds great strength. Sir, why are we discussing this right now? I am trying to explain you a very simple concept here, students, that here also this chapter has its own concepts, its own learnings, and those are the concepts, those are the foundations of this particular chapter. Once you have learned those concepts together, then there comes that tip which you will start applying in the questions. And as we have been discussing it a lot, many times, you all have been told this, that matrices and determinants, when clubbed together, give you a lethal combination which will give you the questions. So some more things are yet to come based on matrices, then we'll club it with determinants, and then you'll start facing questions based on. There is no sense of making you doing questions based on what we have learned so far. 2-3 things are more there, then we'll start doing questions based on this merger of matrices and determinants. So first we studied determinants previously in the last one shot. There were certain questions based on solely on determinants. Then now we'll club both of these chapters and start doing questions on it. I hope you're understanding it. Now, going back to what we were discussing, I hope now we are supposed to discuss certain properties of transpose. What is it? Transpose of A will be A. Do I need to explain this? Sir, first you changed rows by columns, then again you changed rows by columns. So doing it twice actually will give you what you originally started with. Are you not getting this particular part? So if you take the transpose of transpose, basically you're getting the original matrix. So if there is a matrix given to you, you take its transpose twice or even number of times, then you'll get the original matrix. If you take its transpose odd number of times, then you'll get its transpose. So I hope you're getting this, that transpose is a very simple concept. If understood, then yes, you can learn these concepts, these properties as well. Similarly, let's say I have two matrices which are either added or subtracted, and then I'm supposed to take their transpose. Then you can do it individually as well, which means you take their transpose individually and then add or subtract them, whatever is required. So either add or subtract them first and then take their transpose, or take their transpose and then add or subtract as per the requirement. So yes, it is confirmable for addition. That is what you need to ensure first of all. So yes, it can be done, but confirmability of addition and subtraction should be there. Otherwise, it cannot be done. Similarly, if you have k a dash, where k is a scalar, if k is a scalar and you're asked to find k a dash, what does it mean? You can take this k out and you find a dash. What is a dash? The transpose of a. Because k being scalar won't have any transpose, so k can be taken out and you can take the transpose of a. That will also give you the same result. So first of all, you multiply a scalar to a matrix, which means to all the elements of matrix A, then you take its transpose, or you take its transpose first and then you multiply it by scalar. That will give you the same result. You can visualize it by yourself. By simply, you will get the conclusion. But here comes a very important property, this one. Product AB is taken and then its transpose is taken. So you are taking the transpose of AB, product AB. Then it will not be equal to the product of transpose of A and B individuals. No, that will not be true. Rather what you need to understand is transpose of AB is equal to transpose of B into transpose of A. I'll try and give you a little bit clarity on it. Not much is needed to be done in this case, but what you need to understand is, let's say A is having an order 2 by 3, B is having an order 3 by 2. I hope you're getting it very clearly. There is no confusion on it. So what will be the product AB here, students? The product AB here will be 2 into 2, because this 3 and this 3 are same. So product first of all is possible. We all understand this. But when this product is possible, what we are also understanding is that product will have the outcome as 2 by 2. Now, let's say instead of this 2, I write it as, let's say 1, right? So let's call it 1 here. Let's say this is 3 cross 1. So I am clearly seeing that confirmability for matrix multiplication is there, because this 3 and this 3 are same, the number of columns and number of rows. But the product, the outcome will be of order 2 into 1. I hope you can see it very clearly. So that will be the product's outcome. Let's say I denote it by matrix X. So matrix X is the product of A and B, where A is the pre-factor, B is the post-factor. Can you help me with the X transpose? I hope you can see that if AB was of the order 2 into 1, the X transpose will be whatever it is going to be, but that will have the order 1 into 2. Because I have taken the transpose, we can see that AB was having the order 2 into 1. I hope I need not explain this part. So when I take the transpose, the order gets changed, it gets swapped. So X transpose will be 1 into 2. I hope there is no confusion on it. There is no confusion on it. Sir, why are we discussing it? Because I'm trying to give you the idea that now when I take B transpose, see what I have done here is I have tried evaluating X transpose. Now let us take B transpose here. What will be transpose? B transpose, it will be 1 into 3. I hope I did not explain this. Into, now I'm taking A transpose. What will be A transpose? Well, A transpose will be 3 into 2. Again, can I multiply B transpose with A transpose? Yes, I can. So when you multiply B transpose with A transpose, this will be 3 into 3. Sorry, this will be 3 and this will be 3, which is again same, which means confirmability for matrix multiplication is possible. Which means if I multiply them, the product will have the order 1 into 2. So B transpose into A transpose, when done, will have the order 1 into 2. This is the part where I'm just giving you the idea on the order, that whether you multiply AB first and then take its transpose, it will give you a 1 cross 2 matrix. Or you find B transpose and then you find A transpose and then you multiply them, where B transpose is the pre-factor and A transpose is the post-factor, and then you find the product that will also have the same order. Sir, why did you tell all of this? My point here is simple, that since you have seen the order, I'm not delving further and giving you clarity on the elements. Trust me, have my words, faith on them. The product will also be turned out to be same. My point remains very simple. I haven't given you the complete proof, but I have given you a little bit of the idea that yes, it is going to be true, because when we found the order of AB transpose or B transpose A transpose, it is found to be same. Even the product, the element wise product will also remain same. They'll be equal matrices. The conclusion which I am very strongly asking you to memorize is that, let's say I am asked the transpose of the product of certain number of matrices. Then you simply reverse the order and take their individual transpose and then take the product. I am giving you a very simple observation here, students, which is, let's say if I have three matrices X, Y and Z. If I have three matrices X, Y and Z and I am multiplying them, confirmability is there, so I'm not worried about that. And then I'm supposed to take their transpose. So rather than doing this, what you can also do is you take their individual transposes, which means transpose of Z, then transpose of Y, then transpose of X. The only thing which you need to observe or pay attention to is they have to reverse the order. If it was X, Y, Z transpose, then Z transpose, Y transpose, X transpose. That is what you need to remember. This is always same. That's a very important property, very widely used. I hope you will remember this as a property. I hope there is no confusion on that. There is no doubt on that. Shall we proceed further here? I dash is equal to I, where I is the identity matrix. What does it mean? What does it mean? Identity matrix. I hope I need not explain this part. If you are having an identity matrix, I'm taking the order to 1 0 0 1, right? So if it is an identity matrix and I'm taking its transpose, can you help me with its transpose? I need to interchange rows and columns. So 1 0 will become the first row, that will again be 1 0. 0 1 second row will become the second column, that will be 0 1. So it will again be a 2 by 2 matrix, and I think they are same. So identity matrix of any order if taken, and if you take its transpose, it will give you the same identity matrix. The transpose of identity matrices are always the original identity matrices only. There is no confusion on that, I believe. With that, let us proceed further towards the next part, where we'll discuss the next portion of our video, next portion of our one shot on matrices, which is the symmetric matrice. With symmetric and antisymmetric, we'll start moving towards the questions. So all what we have learned so far is getting clubbed and combined now. How? Have a look at that part. See here, I square matrix A is said to be symmetric if A dash is equal to A. What is A dash? Transpose of A. So if you have a matrix and if you take its transpose, and if both of them are found to be same, then we call such matrix to be a symmetric matrix. Any confusions on that, students? I don't think there is any problem. With an example, if I were to explain this, let's say there we have this particular matrix where the principal diagonal has elements ABC. These non-principal diagonal elements are HGF and HGF. I hope you can see them. Now what happens when I take the transpose? See, AHG became the first column, HBF became the second column, GFC became the third column. But now when I looked at it, I can see that ABC principal diagonal element, ABC principal diagonal element remained same. This HGF is again found to be there. This HGF is again found to be there the way it was previously placed. Why am I showing all of this in the same manner? I'll come up with that part later, but as of now I'm asking you, does this A, this H, this G, all these elements are exactly same even after taking the transpose. What does it mean? It means if you have a matrix and if you take its transpose, and if both are found to be same, the matrix and its transpose, then that matrix is called a symmetric matrix. Then such matrix is said to be a symmetric matrix. Definition wise, what does it mean? It means, I hope you are realizing a very simple phenomena. I'll just give you an idea with an example. Where do we have this example? We don't have this example. I'll just take it here. Let's say we have this particular matrix. I'll take a 2 by 2 matrix. So I'm taking a 2 by 2 matrix. Let's say there is a matrix A, which I'm calling a 2 by 2 matrix A, B, C, and D, right? Let's write its transpose. So what will be its transpose? So its transpose will be, first row AB will become the first column, second row CD will become the second column, right? Or in a different world, let's say instead of ABCD, I'll take some more examples, some different terminology so that you understand it even better. A11, A12, then you have A21, then you have A22. That will help you in understanding it more clearly. Then when I took its transpose, the first row became first column. So here I have A11, A12, and this second row A21 became the second column, A21 and A22. Let's say if I am told that A is symmetric, I am given this fact that A is symmetric. I am told that A is symmetric. What does it mean? So if A is symmetric, what I know is that A will be equal to its transpose. Because if A is a symmetric matrix, its transpose and this matrix will be equal. They'll be same. So if they are equal, they are same. Their corresponding entries, their corresponding values will be same. Which means A11 will be equal to A11. Well, that will be true because A11 will be equal to A11 because it is A11. But A22 will also be equal to A22. Yes, that is also true that A22 will be equal to A22. But what is next? The next part is more interesting here. That from here, if I observe, then A21 will be equal to A12. Or A12 will be equal to A21. What does it mean? It gives us another conclusion that A12 will be equal to A21. Did you notice something very crucial here, students? That if it is a symmetric matrix, then Aij will be equal to Aji. See, A11, A11, A22, A22, A12, A21, A12, A21. So for a symmetric matrix, Aij will be equal to Aji for all ij. Now, when it comes to, that's why I was highlighting in this same manner when I was saying here a very simple part that this principal diagonal elements, what are they? A11, A22, A33. So A11 will be equal to A11, A22 will be equal to A22, A33 will be equal to A33. Some of you might say, sir, you are not saying something additional or different, but some of you must have noticed that I am following the definition of symmetric matrices. More clarity. See, A12 is equal to A21. A12 is equal to A21. A13 is equal to A31. I hope you can see A23 is equal to A32. So Aij will be equal to Aji for a symmetric matrix. What does it mean? If you want to notice a symmetric matrix, if you want to pay attention and want to observe or check whether it is a symmetric matrix or not, what you need to pay attention to it is that you should not try and find the transpose and then check whether they are same or not. What you need to pay attention to is, first of all, it should be a square matrix. Then only it should be a symmetric or antisymmetric, but symmetric or skew-symmetric. But first of all, for a symmetric matrix, there will be a principal diagonal elements which will remain intact. They'll remain like the way only. We need not look at them. What you need to pay attention to is that if this element and this element are equal, if this element and this element are equal, and if this element and this element are equal, then we say that such matrix is going to be a symmetric matrix undoubtedly, unhesitatingly, because Aij is equal to Aji. So A12, A21 will be equal. A13, A31 will be equal. A23 and A32 will be equal. Even A11 is equal to A11, A22 is equal to A22, A33 is equal to A33. Ij is getting replaced by J, but it is sounding same or similar. But I hope you are understanding what is the meaning of a symmetric matrix. It has its own meaning. Questions are asked on it. I'm not just spending some time on it. There is a valid reason behind spending time on it. Now, let us talk about the next part. There comes another part. Maximum number of distinct entries in any symmetric matrix of order n will be n plus 1 by 2. Where did it come from? Pay attention to it. Pay attention to it. What can you have? What can you have? you can afford to have these ABC, whatever you want to have. But when it comes to having that next set of entries, whatever this number is going to be, this number should be that number only. So if this is chosen by you, this does not have any choice. This has to be this only. If you choose G as per your choice, this entry will be same as this only. So if this has some choices, you cannot have any choices on this. If this F is going to be a number, this element over here should be same as this number to make it a symmetric matrix. My point remains very simple. You have the liberty to choose any elements on the principal diagonal position that you have. But when it comes to choose these entries, whatever you choose for them, this same will be replicated here. So if you have chosen these three won't have any choices. They'll follow exactly what we give here. I am trying to explain it in the context of permutation and combinations if you are able to digest. So the conclusion remains very simple. What is that, students? I'll come up with that with an example here again. What did we have here? Let's say I am trying to make a symmetric matrix of order, let's say 3 by 3. Now, what do I have? If there is a symmetric matrix of order 3 by 3 I'm willing to make, so let's say I have chosen this A, B and C. So the diagonal elements can be chosen by me. So if it was of order 3 by 3, the number of elements I could choose was 3. Apart from these, what else am I allowed to choose? Well, I am allowed to choose now either these 3 elements or these 3 elements. Rest will depend on what? Rest will depend on what we have chosen here. For example, if I have chosen these 3 elements, then these 3 will follow what we have chosen here. Or if I choose these 3, then I'll have to keep these 3 same as these 3. I hope you're understanding, to maintain that this matrix remains symmetric. That's exactly what I'm trying to give you with this formula, that if you want to call or say or figure out that if there is a matrix of order n and you want to check the maximum number of distinct entries it can have, then you will say these 3 and these 3. I hope you are getting this part very clearly. How did we calculate this part? This is basically clubs down as n times n plus 1 by 2. How did I get this n times n plus 1 by 2? That's a very simple phenomena. That's a very simple result. We can evaluate it with a very simple calculation. How? Let's look at that. I'll explain it on a different slide here. I hope you are getting the requirement. That the requirement is pretty simple. We are having certain number of elements. Let's say it is an n by n matrix. I'll take this 3 by 3 also along with this so that you get it more clearly. So in this 3 by 3, what liberty do we have? We can choose these elements for a while. Let's say, right? So if this was a 3 by 3 matrix, we have this A, B, C, and then we have this H, G, F, N. So these many elements we can choose. So these many elements we can keep distinct, right? Maximum number of elements, because after having these many elements, now the remaining elements will be same as HGF only, which will be HGFF. So I hope you have understood the requirement. Now how do I calculate this number? That is what I'm trying to give you the idea here. The idea is very simple. I'll take this example first, then I'll generalize for n, which we have already learned while discussing upper triangular and lower triangular matrix. That logic only I'll apply here. But if you have forgotten that, let me bring that particular discussion again into picture. What is it? Here, the total number of elements here were how many? They were here basically 3 into 3, they were 9 because it was a 3 by 3 matrix. So originally the total number of elements were 3 by 3, which was 3 square. Out of this, if I subtract these ones, I'll be left with those elements, which I can keep distinct, which I am allowed to keep distinct or different. I hope you have understood this particular logic. So I hope you are understanding. This is what we have already calculated, because the minimum number of zeros criteria we have discussed while discussing the upper triangular or lower triangular matrix. That criteria had this result n minus 1 by 2. If I subtract n minus 1 by 2 from n square, I think I'll get the result. I hope you are getting this particular part here. So from all these 9 elements, 3 by 3, 3 square, if I'm subtracting these 3 elements, I'll get 6 entries which I can keep distinct, different. I hope you're understanding this in the context of this 3 by 3. But in the context of this particular one, n by n, I hope you can see these are the elements which I can keep distinct, because these remaining ones I'll say will remain same. So this one includes the principal diagonal as well. So the total number of elements are going to be n square, out of which these elements I'm excluding, which we have already calculated, were n minus 1 by 2 previously while discussing the upper triangular and lower triangular matrices. Now if I combine these two results, I'll be having n square, then of course minus n square, and then I'll be having, I'm really sorry, I'll take this LCM later, but as of now n square minus, I'm multiplying this n inside, so n square minus n divided by 2, right? So I take the LCM, that should be 2n square minus n square plus n divided by 2. I hope we have the result, n square plus n by 2. So that will be n square plus n by 2, which when simplified gives you n times n plus 1 by 2. I hope there is no confusions on that. No problem at all on that. That this is the maximum number of distinct elements you can have. Let's say I have a 2 by 2 matrix and I want to keep it symmetric. So maximum number of distinct entries I can have will be 2 into 3 by 2, which means 3 different entries I can have, because that fourth entry will be same as that non-principal diagonal element. I hope you're realizing that. With that, proceeding ahead, what do we have next? I hope you have gotten complete clarity on it. There was one more very crucial concept I'm supposed to discuss here, which is that whatever square matrix you are given, let's say there is a square matrix A is given to you, and that with that matrix A, if I add its transpose, if that matrix A with A, if I were to add its transpose, I will always get a symmetric matrix. I am bound to get a symmetric matrix. The proof is very simple, students. The proof is straightforward. What is it? Let's say I want to check whether A plus A dash is symmetric or not. How do you check that? I'll take the transpose of it, and if its transpose is found to be the original matrix, then I'll call it to be a symmetric matrix. So let's say A plus A dash I'm wanting to assess is symmetric or not. So I'm taking the transpose of A plus A dash. Now what is the property? Transpose is distributive on addition and subtraction. So this transpose I'll take to here and here. So I'll have A dash like this and A dash dash like this. But we know transpose of transpose is the original matrix. So A dash will remain as it is, but A dash over dash will be A. I hope you are getting it. So it will be A dash plus A, which is A plus A dash, which means the transpose of A plus A dash is A plus A dash only, which helped us in understanding that this was a symmetric matrix. What was the symmetric matrix? The sum of a matrix with its transpose. Always remember this, because this I'm going to use in a question as a fact or a property. Now, let us move our discussion towards the next part of this particular video, where I'll talk about the skew-symmetric matrices, which is another extension of symmetric matrices, but in a different sense. How? Have a look at this part. This time, let's say I have a square matrix, but if this square matrix has this particular property, that if I take its transpose and it is found to be equal to its negative. Previously, when it was symmetric, the transpose was found to be equal to the original matrix. But this time, if the transpose is equal to the negative of the original matrix, then in such case, we call it to be a skew-symmetric matrix. Now, how does it look like? That clarity I'll give to you. Don't worry about that. But are you getting the definition? Are you getting the definition? The definition is very simple, students. Let's say I'll take an example first to give you more clarity here. The part is very simple, students. The definition is very simple. If you have Aij, and if it is equal to negative Aij for all ij, then we call such matrix to be a skew-symmetric matrix. And all of this is being discussed in the context of course, which category of matrices? Square matrices. Don't forget that. Now, let's take a square matrix, a 2 by 2 matrix I'm taking, right? So here we have A11, then we have A12, then we have A21, then we have A22, right? And I'm taking its transpose. So I hope you know how will its transpose look like. Its transpose will look like A11, A12 will become the first column, and A21, A22 will become the second column, right, students? Now, let us say that we are told that this is a skew-symmetric matrix. I am told that if A is equal to negative of A transpose, which means I am told that A is a skew-symmetric matrix. I am told that A is a skew-symmetric matrix. So if A is a skew-symmetric matrix, which means A is equal to negative of A transpose. So this is A transpose. What will be its negative? I need to multiply it by -1. So if I wish to multiply it by -1, this will become this. I hope there is no confusions on that. Now if I compare it, because A and negative of A transpose are equal, because A is a skew-symmetric matrix, which means A11 will be equal to minus A11. So if A11 is equal to minus A11, that implies that A11 should be 0. Because if a number is equal to its negative, that's possible only when it is 0. Now, similarly, if I talk about A22, which is equal to minus A22, well, A22, if it is equal to minus A22, that means A22 should also be 0. Right, students? The next part here is that I hope we are going great. Yes. The next conclusion here is that A12 should be equal to minus A21. And even if you look at this part here, A21 should be equal to minus A12, which is same. So the next conclusion is that A12 should be equal to minus A21. So it is almost same as symmetric matrix, but here the negative sign has come into picture, which will make your skew-symmetric matrix look a little differently. For example, let's say I call them K for a while. I am calling them K for a while. So how will it look like? This matrix A, which is said to be a skew-symmetric matrix of order 2, will now look like, see, A11, A22, we have already concluded to be 0. So their diagonal elements will be 0, 0. And A12, let's say if A12 is K. So if A12 is K, what will be A21? A21 is minus K. So this should be minus K. So that's exactly what I'm trying to make you understand here. For a skew-symmetric matrix, the principal diagonal elements are always going to be 0. So if you want to observe whether a matrix is a skew-symmetric matrix or not, the first check will be its principal diagonal elements. They'll be 0. What will be my second check? My second check will be very simple. It will be very, very simple, very straightforward. If this is H, this will be minus H. If this is G, this will be minus G. If this is F, this will be minus F. Why? Because then only its transpose will be equal to its negative. I hope you're able to digest this particular part. So that is, I think, is all about skew-symmetric matrix. But there are certain properties which I wish to explore along with skew-symmetric matrices. Now let's look at the different properties of skew-symmetric matrix. You all know that whenever you deal with a skew-symmetric matrix, the principal diagonal elements are 0. We all know that. For example, if I'm having a skew-symmetric matrix right there, let's take a 3 by 3 matrix here. Its principal diagonal elements are supposed to be 0. You all know that. Apart from that, we all know that if there I'm having A, I'll have a minus A here. If I am having a B here, I'll have a minus B here. If I have a C here, I'll have a minus C here. I hope you're able to understand this particular matrix is definitely a skew-symmetric matrix. I hope you know the reason. Now, my concern here is to make you understand that, let's say if this is a skew-symmetric matrix, which it is, then do you not think that the trace of this particular matrix is going to be 0? What is trace? Sum of principal diagonal elements. And for a skew-symmetric matrix, all the principal diagonal elements are 0, as we have already discussed. Then will I not say that trace of a skew-symmetric matrix is always 0? Will you remember that? Now, the way we have discussed a property that for any square matrix, if I add it to its transpose, I will always get a symmetric matrix. In the same manner, can I not say that if I have a square matrix and I subtract its transpose from it, if I subtract the transpose of a matrix from it, for example, A minus A dash, A minus A transpose, A can be any square matrix. All you need to ensure is that it has real numbers entries. The elements should be real numbers. Do you not think that the matrix so formed after taking this difference will be a skew-symmetric matrix? If you don't believe me, you will have this proof. How do we prove it? Have a look at this part. Let's say I have this particular matrix A minus A dash, which I'm denoting by X, which I am denoting by a matrix X, right? So I'm taking the transpose of x. Okay, so how do we take the transpose of this x? The modus operandi is pretty simple. I am taking a transpose over a minus a dash. We all know that transpose can be distributed over addition or subtraction, which means I will take the individual transpose of a and I will take the individual transpose of a dash and I'll put a difference minus sign between them. Now, what does it mean? I'll have a dash and a dash over dash. I mean dash over a dash. Now, I hope you know a dash remains as it is, but transpose of transpose gives you the original matrix. So dash over a dash gives you a. Now, if I take the negative sign common, what will I be left with? So if I take the negative sign common, I'll be left with a minus a dash. So basically the simple conclusion remains very simple, that if I took x dash, if I took the transpose of x, what I got was negative of x. And that's exactly what a skew-symmetric matrix does. That if you take the transpose of a matrix and if you get the negative of it, then such matrix is called a skew-symmetric matrix, which is exactly representing, showing or demonstrating a minus a dash. So a minus a dash will always be a skew-symmetric matrix, the way a plus a dash was a symmetric matrix. Did you all get that part? With that conclusion, can we come up with a very important observation, with a very crucial observation? What is that? For any square matrix A, I will be able to express that square matrix A as a sum of a symmetric matrix and a skew-symmetric matrix. This is not just an ordinary property, students. Questions are being asked on this particular property and they love asking questions based on this particular property. This is one of those important properties which you should remember. Questions are asked in JEE mains and advanced. They somehow ask you to convert a matrix into sum of a symmetric and skew-symmetric matrix, and then they ask you certain things related to those two matrices. The dilution of a matrix into two different matrices which are symmetric and skew-symmetric matrix. How? Let's learn that. First of all, you need to understand that for any square matrix, if I add this square matrix to its transpose, I'll get a symmetric matrix. And if I subtract this, the transpose of this matrix from the original matrix, I'll get a skew-symmetric matrix. Now, if you pay attention, if I create this expression over here, what does it mean? Half of a plus half of a, that will be a. Half of a dash minus half of a dash, that will get cancelled. So I will get a only. So can I not say a plus a dash divided by 2 plus a minus a dash divided by 2 is a only? Did you all get that part? I hope there is no confusion on that. But when I say so, when I do so, what conclusion, what new result I get is that here I hope you are paying attention, that this a plus a dash will be a symmetric matrix. A minus a dash will be a skew-symmetric matrix. Half will not affect your result at all. Rather, having this half and this half over here will help you in getting a finally. So what I'm trying to make you understand is that any square matrix can be broken into two parts, basically as a sum of two matrices, out of which one of them is a symmetric matrix and the other one is a skew-symmetric matrix. Well, if you have understood this particular property, let us solve a question and understand it more clearly through this particular scenario. What does this question say? Express A as a sum of symmetric and skew-symmetric matrix where A is given by 3, 5, minus 1 and 2. How do we do that? We know that for any matrix, I can write that matrix as A plus A transpose plus half of A minus A transpose. Why did we do that? I hope I need not explain this particular part, that this particular portion is going to be a symmetric part and this particular portion is going to be a skew-symmetric part. I hope you know this particular definition very clearly. Now, if you know this particular definition very clearly, can we start using or applying this? I hope. Only thing you need to understand is what is going to be the value of A transpose. So I'm evaluating A transpose here separately. I hope there is nothing much is needed to be done in this case. The transpose of A, you interchange rows by columns, right? So 3, 5 being the first row will become the first column, and similarly minus 1, 2 being the second row will become the second column. What am I supposed to do? Can I write A as half of addition of A with A transpose. You know, addition of matrices, equivalent, you know, corresponding terms, corresponding elements are added. So simply I'll have this 3 plus 3, which is going to be 9. Then I'll have this 5 minus 1, which is going to be 4. Then I'll have this minus 1 plus 5, which is going to be 4. And then I'll have this 2 plus 2, which is going to be 4. This is what I have received. Even if you want, you can multiply this 1 by 2 inside. Even if you don't, then also it is fine. Why? Because I hope you are seeing, if you take the transpose of this matrix 9 4 4 4, if you take the transpose of this matrix, its transpose will this only, because 9 4 being the first row will become the first column, which is 9 4. 4 4 being the second row will become the second column, which is 4 4. So are you realizing that this is a symmetric matrix? Did you all get that? Similarly, if I am having half, then what I am supposed to do to get the skew-symmetric matrix? Subtract A transpose from A. So what do I get? I hope you're realizing 3 minus 3 will be 0. No confusions on that, I believe. 5 minus minus 1, that is clearly 6. Then minus 1 minus 5, that is also nothing but what? Minus 6. And then 2 minus 2, that should be 0. Are you all noticing that this is clearly a skew-symmetric matrix? Why am I saying so? Because I hope you all must be noticing that here the principal diagonal elements are clearly 0. And if this is 6, this is negative of it, which is minus 6. So I hope this is very well understood by you all, that here this is a skew-symmetric matrix. So this was a symmetric matrix, this was a skew-symmetric matrix. Even if you want to go ahead further and wish to write the final answer, you can push these 1 by 2 inside. And with matrices, when you multiply a matrix with a scalar quantity, that scalar gets multiplied to all the elements, unlike determinants. In determinants, it used to be either any row or any column. But here, with matrices, you're supposed to multiply this 1 by 2 to all these elements, and here also to all these elements. So if I were to write the final conclusion, my answer will be very simple. Here, 9 by 2, 2, 2, 2, right? So A will be sum of two matrices, which are going to be, first one will be 9 by 2, then 2, 2, 2. That will be your first matrix, which is the symmetric matrix, and here it will be 0, 3, minus 3, 0. So here the next matrix will be 0, 3, minus 3 and 0, and that's your final answer. We were able to write the matrix A as a sum of two matrices, where what I'm able to attain is that this happens to be a symmetric matrix and this happens to be a skew-symmetric matrix. Did you all get that part? Did you all understand this particular part? I hope there is no confusion on it, that what was the question, what have we attained, and what are we able to do with this particular conclusion. I believe there is no confusion on this result. I hope you are able to understand that this matrix over here is clearly looking like a symmetric matrix, and this is clearly looking like a skew-symmetric matrix. Right, students? I hope we can proceed further with that conclusion. Now, let us understand some more properties of symmetric and skew-symmetric matrices. What are they? Let's begin with the first one. What does the first one say? If A is a square matrix, then A dash and A dash A are also symmetric matrices. Now, how do we prove that? The proof is really simple, students. Can I say, let's say X is a matrix. Let's say X is a matrix over here, which is A dash. Now, I want to check whether this is symmetric or skew-symmetric. What will I do? I'll take its transpose. So here, if I take its transpose, or rather I'll call it A dash only, so it will be A dash whole dash, right? Now we know that when you take the transpose of product of matrices, the order gets reversed. So what am I supposed to do here is, I'll take it on a different page so that no confusion is there. So here, let me take a different page here. Let's say there is this matrix X, which is A dash, and I want to check whether it's symmetric or skew-symmetric or none. I hope you're getting it. So how do we do that? I'll take the transpose of it. So if I take the transpose of it, I have taken the transpose of A transpose, right? So when you take the transpose of product of two matrices, the order gets reversed. I hope you know that. So here, X transpose is going to be transpose of A. This first part will appear first. This particular part will come first. I hope you're getting it. Then I'll put a transpose over this A because the order gets reversed. I hope you remember this particular property. So here I'll have transpose of A transpose first, and then I'll have the transpose of this A. Getting it, everyone? And we know transpose of A is A only. So here when I was taking the transpose of X, I got A times A transpose, which was nothing but X only. So if you took the transpose of AAT and you got AAT only, that means this AAT, which means A times transpose of A, is a symmetric matrix. I hope the proof is sufficient. And on the basis of that, can I prove that A dash A will also be a symmetric matrix? So this is something which is needed to be learnt and understood by you. Even if you don't remember it in the examination hall, by using the properties of the transpose, you can prove such results. So first conclusion is A transpose or A transpose A are going to be symmetric matrices. What about A? All I need is that A should be a square matrix. That is sufficient for me. I hope you have understood this first property. Let us focus on the second property. Well, in that case, what does the second property say? It says all positive integral powers of a symmetric matrix are symmetric. What I'm trying to say here is another very important conclusion here, students. Let's say I have this A matrix which is told to be symmetric. So we are given that this matrix A is a symmetric matrix, right? Now, this matrix A is raised to certain power. What you need to understand is the power should be a positive integral value. So A could be raised to any power, 2, 3, 4, 5, 7, any positive integral power, which means a natural number in short. So if I raise it to any power, we know there is a property that either you multiply it n times and then you take its transpose, or you take its transpose and then you multiply it n times. That will yield the same result. That will give you the same result. The property remains very simple. Why am I saying so? Because let's take an example where I'm multiplying A 3 times so that you understand it better. Let's say I'm multiplying A 3 times. So what does it mean? What does it mean? It means A cube transpose I'm supposed to take. So I'm supposed to take the transpose of A cube. Now what does it mean? In simple language, it means A transpose, right? This is what it means. Now we know that when you take the transpose of product of matrices, the order gets reversed. But here, even if I reverse the order, it will not look different because all the three matrices are identical, same A. So in that case also, it will look like A transpose, and A transpose. Are you getting it? First I have written this, then this, then this. And here, if I look at A transpose getting multiplied thrice, will I not write it as A transpose raised to the power 3? My point remains very simple, students. What is my point here? My point is straightforward, that I begin with A cube transpose and what I got was A transpose cube. That's exactly what I'm trying to make you understand here. My point is this, that A to the power n, if I treat it as x, A to the power n, if treated as x, we all know this very clearly, that when I took the transpose of x, it turned out to be equal to, I hope you are getting it very clearly, A transpose raised to the power n. So if this part was equal, will I not be able to conclude that A to the power n will be a symmetric matrix? Because it is following the definition of a matrix being symmetric. I hope you are able to digest it. Even if you haven't, let me come back to this part where you need to understand it, that for any symmetric matrix, if you raise it to a positive integral power, then A n transpose will be equal to, A n transpose means transpose of A to the power n will be equal to A transpose raised to the power n, which clearly is indicating that A to the power n is a symmetric matrix. Why am I saying so? Because when I took the transpose of A to the power n, it turned out to be equal to the nth power of A transpose, which is clearly indicating you that A to the power n was a symmetric matrix. I hope you're getting this part very clearly, that for a matrix, if its transpose is equal to the original matrix, then we call that this is a symmetric matrix. I hope you're able to digest this particular part, that we were already told that A was a symmetric matrix. And if A was a symmetric matrix, then we know that A transpose is equal to A. And here that's exactly what I'm trying to demonstrate or depict, that A transpose is A, then I can write it as A cube. That's exactly what I'm trying to make you understand, that let's say for a while, to make you understand it more clearly, let's say X is A cube. So what I began with was transpose of X. A cube transpose is what? This is the transpose of X, and ultimately what I got was X. In a very simple language, I'm trying to make you understand this particular part here. So I hope you're realizing here also we can prove the same result, we can prove the same property. So if I'm beginning with transpose of A to the power n, and if I'm getting the A transpose raised to the power n, where A is a symmetric matrix, then will I not say that A to the power n transpose is equal to A to the power n? Because A transpose is equal to A. Why? Because A is a symmetric matrix. Then will I not be able to conclude that A to the power n, when its transpose was taken, I got A to the power n only? And if that is so, then A to the power n is a symmetric matrix. So the statement remains very simple. If you have a symmetric matrix and if you raise it to any positive integral power, that is a natural number, then it will always give you a symmetric matrix. Through this particular proof also you must be able to understand, even if not, then this statement should be remembered by you. And as we have already been discussing, if you are not able to remember a statement, apply it, derive it. That is always there with you, because these properties will not directly be asked. You will be given a certain expression and you will be asked to check whether this is symmetric or skew symmetric, and that's where you're supposed to bring that conclusion. And that modus operandi, that process remains this, that you take that matrix, you take its transpose, apply the properties of the transpose, and then check what is it turning out to be. If it fulfills the property of being symmetric, then I'll call it a symmetric matrix. Otherwise, a skew-symmetric matrix, if it fulfills the property of being a skew-symmetric matrix. If not both, then not both. That means it is neither symmetric nor skew-symmetric matrix. It is simply a matrix. I hope you're understanding. It is not necessary that a matrix will be either symmetric or a skew-symmetric matrix. A matrix can be none as well, neither symmetric nor skew-symmetric. I hope you're understanding this particular part. Now let us understand the third property. What does the third property say, student? It says all positive odd integral powers of a skew-symmetric matrix are skew-symmetric. I hope you're getting it. Are skew-symmetric. Okay, that is what we need to check. I think it should be symmetric. Let me cross-check it. And positive even, sorry, they have repeated the same statement here. They have repeated the same statement here. So let me make that correction first. All positive odd integral powers, all positive integral powers of skew-symmetric matrix are skew. Let me check this particular part, then we will make the required correction here. Forget this part, this is more confusing. Let me begin with a skew-symmetric matrix. Let us prove the property first, then we'll make the amendments here. So let's begin with the property here. The property says a very straightforward result. What is the result? The result is very simple. Let's say we are dealing with a skew-symmetric matrix. I am dealing with a skew-symmetric matrix, and then I'll be taking either odd powers or even powers. Now what happens with that? That is the conclusion we are supposed to draw. So let's say I have a matrix. Which is, let's say for a while, a skew-symmetric matrix. Did you all get that? What does it mean if it is a skew-symmetric matrix? If it is a skew-symmetric matrix, then I'll say that if I take its transpose, it will give me negative of this matrix. That is exactly the meaning of a skew-symmetric matrix. Do you all remember that? If you take the transpose of a matrix and if it generates the negative of the original matrix, then such matrices are called skew-symmetric matrices. So this is what I know so far. Now let's say I am taking a to the power n as a matrix. Now there are two cases. Because of this negative sign, now there are two cases. N could be either odd or even. Although it will be a natural number, I know for sure that n will be a natural number, but I want to make a comment on a to the power n. But there again, two cases arise. The first case is going to be when n is even. And the second case is going to be when n is odd. So let's focus on n being even and odd. Now, can we talk about first of all a to the power n? See, let's say that a to the power n is basically a matrix. Let's call it a matrix a to the power n. Now, if I want to check what is it going to be, so can I say a to the power n transpose I'm supposed to check? Because if I take the transpose of a to the power n, then I'll be able to make some comments on it, whether it is symmetric or skew-symmetric matrix. How? Let's focus on that. We know that this transpose and this power n can be interchanged. We have learned this property that a to the power n whole transpose can be written as a transpose raised to the power n. So here I'm interchanging these two. So here if I interchange these two, I'll be having a transpose raised to the power n. Now what is a transpose? We know a transpose is minus a. So if a transpose is minus a, then I'm raising minus a to the power n. Now I hope you're realizing why does it all depend on a rather n. If n is even, do you not think if n is even, I'll be getting a to the power n. So my point is very simple. If n is even, I'll be getting a to the power n. But here when n was odd, and if I were to take the transpose of a to the power n, which I could write as a transpose raised to the power n, and we know a being a skew-symmetric matrix, a transpose will be minus a, so here minus a to the power n. But since in this case when n is odd, minus a to the power n will be minus a, so here I have received it as minus a to the power n. Did you all get that part? Now, why are we discussing all this? I hope the conclusion remains right there in front of you. Here, I took the transpose of a to the power n and I got a to the power n, which meant I got a symmetric matrix. So, a to the power n, when n is even, will be a symmetric matrix. Did you all get that? But, when I took the transpose of a to the power n and I got negative of a to the power n, So, transpose of a to the power n turned out to be negative of a to the power n, which meant this is a skew-symmetric matrix. All because of n being odd. So can I say whenever n is odd, it will be a skew-symmetric matrix. What? A to the power n. So let's make that correction over here. A simple correction will be required. Let's do that very quickly. First of all positive, I'll not say odd. Yes, odd integral powers of a skew-symmetric matrix are skew-symmetric matrix. That is perfectly fine. But when I say all positive even integral powers of a skew-symmetric matrix are symmetric, no, that is perfectly correct. I mistakenly read it as a skew-symmetric matrix and then I thought that it could be wrong, but no, they have written it completely correctly. There is no correction which is needed to be done. So yes, I repeat this particular part, which you are able to digest and understand, that if you are having a skew-symmetric matrix and if you raise it to any odd positive integral power, then we know I'll get a negative. Well, in that case, I'll be getting a skew-symmetric matrix. But when you raise a skew-symmetric matrix to a positive even integral power, then I'll get a positive value. That means it will be a symmetric matrix, all because of this property, as we have already seen the particular proof in this particular slide. I hope this particular slide makes complete sense and you are able to digest what I'm trying to explain here. Well, with that, let us move to the next property. What does the next property say? Have a look at that part. Let A be a symmetric matrix. So we are told that A is a symmetric matrix and B is a square matrix of order that of A. So A is a symmetric matrix and B is just a square matrix, ordinary square matrix, where A and B have the same order. So for example, if A is a 3 by 3 square matrix, B will also be a 3 by 3 square matrix. That is what I know so far. A is clearly a symmetric, but B is a square matrix. In that case, remember this as a property, and I will ask you to by heart it, to memorize it, because they ask questions based on this particular property. What is this property? Read it first very clearly. A is a symmetric, B is just another ordinary matrix of the same order. Now, please understand, whether you take negative of A, whether you multiply A with a scalar quantity, or you take A transpose, or you take inverse of A, or A to the power n, or the most important B dash AB. This is something very crucial, very important. Don't forget this. B dash AB. Please remember, all of these are going to be symmetric matrices. What did I just say, students? You have a matrix A. Which is symmetric. Then always remember minus A, KA, A transpose, A inverse, even this A to the power n. All of them are going to be symmetric, as we have already discussed through these properties. The next learning which plays a very crucial role here is B dash AB, where n is a natural number, will also be a symmetric matrix. Questions are asked on it. Questions are framed on this particular property. If you want the proof, most of you must have cracked it. What I know here is that, let's say there is a matrix X. I'm calling that there is a matrix X which is B A B dash. I think this is exactly what we are supposed to prove. Yes, or rather B dash AB. That does not make any difference. But even if you think that it makes a difference, let me write it like the way they have written it on the property. Now, I want to check whether it will be symmetric or skew-symmetric. The logic is very simple. I'm supposed to take the transpose of it. So what will be the transpose of it? BAB, right? Transpose. Whether you write T or dash, I hope it doesn't matter. So here, if I proceed further, you know that product of matrices, the order get reversed when you take the transpose. So here, this will be very simple, that I'll write this B dash first, then A dash first, and then B dash dash, right? We already knew that A was a symmetric matrix. We were given in the property that A was a symmetric matrix. So here, by following this particular property, I'll be able to write it as B dash as it is, A dash as A, and B dash dash will be B. So this is what I have received. So I begin with the transpose of X and I got X, which means X is a symmetric matrix. And that's exactly what I was trying to convey here with this particular property, that whenever somebody says that B dash A, what was B? B was the same order square matrix as A. So whenever something like this happens in a question, we will directly conclude that this B dash AB will also be a symmetric matrix. Remember this as a result. Questions are asked on this particular result. A lot of questions can be solved very quickly if you remember this as a result. I hope these properties make complete sense. With that, let us proceed further. Let us move ahead with the next set of properties, which is your fifth property. What does it say? Let us explore that part here. So here, let us look at this particular property. If A is a skew-symmetric matrix. Now, if what is it? A is a skew-symmetric matrix. All right. So what I know so far is that A, I'm told or given, which is a skew-symmetric matrix. What does it mean? That if I take the transpose of A, I'll get negative of A, because A is a skew-symmetric matrix. What does it mean? They are trying to say four things about it. A to the power 2n will be symmetric. Did you all get that part? This is exactly an extension of the property we have discussed previously. What they're trying to say is A to the power 2n will be symmetric and A to the power 2n plus 1 will be skew-symmetric. This is exactly what we have discussed. These two properties, I have previously in the previous slide proved them. We knew if there is a skew-symmetric matrix, then there are two possibilities. Its power n will be either even or odd. So whenever the power is even, it will be symmetric, and whenever the power is odd, it will be skew-symmetric. So whenever n is a natural number, 2n will be even and 2n plus 1 or 2n minus 1 will be odd. That's exactly what they are saying, but in a different sense. So I hope the first two properties are very clearly and very easily understandable. They don't make any difference at all. Let's talk about the next property. Ka is a skew-symmetric matrix where K is a scalar. So the way we have discussed, if A was a symmetric matrix, Ka will be a symmetric matrix. In the same fashion, if A is a skew-symmetric matrix, then Ka will be a skew-symmetric matrix. It should be understood by all that multiplying it by K wouldn't make any difference. Rather, it will keep it intact, that whenever you take its transpose, it will still generate negative of that matrix, which means it will still maintain to be a skew-symmetric matrix. So I repeat, if you have a skew-symmetric matrix and if you multiply it by scalar, then also it will remain a skew-symmetric matrix. A very simple observation. I need not prove it, I think. The next property is again a very crucial property. JEE loves it. They keep on asking questions on it. What is that property? Let's have a look at that part. B dash AB is also a skew-symmetric matrix, where B is again a square matrix of the order that of A. What does it mean, students? It is again a very straightforward property. Previously, what we have learned is that if A is a symmetric matrix, B dash AB will be a symmetric matrix. Similarly, if A is a skew-symmetric matrix, B dash AB will also be a skew-symmetric matrix. I hope nothing needs to be proved in this particular case. What you must remember here is a very straightforward conclusion, which is B dash AB does not affect this particular property, that whether A is symmetric or skew-symmetric. B dash AB will also be symmetric or skew-symmetric respectively, depending on what is A. So B does not play any role at all. B can be any square matrix. All you need to ensure is that B should have the same order that as of A. Did you all get that particular part? Did you understand this particular property, students? Shall I proceed further? Now, let us talk about two matrices and let us merge them and let's see what happens. So first conclusion, let's say I call two matrices which are symmetric. So A and B both are symmetric. Now let us draw some conclusions on their sum and their sum of the products. So what I know here is that A and B are two matrices. I have taken the matrices A, which is symmetric, and another matrix B, which is also symmetric. So there are two matrices I have taken, A transpose and B transpose, and they turn out to be same, A and B only respectively, which means A and B are symmetric matrices. Now when you wish to draw a conclusion on their sum, so A plus minus B, I want to check whether it is symmetric or skew-symmetric or none. In that case, I'll take its transpose. So while taking the transpose of it, if I get the original matrix, I'll say the matrix was symmetric. If I get the negative of the original matrix, I'll call it skew-symmetric. If I get none, then I'll say none, which means they are neither symmetric nor skew-symmetric. I hope you're getting the result. So I know on addition or subtraction, transpose can be distributed individually. So here I can write it as A transpose plus minus B transpose. What is A transpose? That is A. What is B transpose? That is B, because A and B are symmetric matrices. So here I'll be writing it as A plus minus B. What does it mean? It means that A plus minus B will be a symmetric matrix. That's exactly what they are trying to say here in the first property. If A and B are two symmetric matrices, A plus minus B, symmetric matrix. What about AB plus BA? Okay, let's work on that. Let's work on the second property. So what about the second property? AB plus BA. Sometimes with the flow, I may use some Hindi words. I hope you are fine with them. You know, that comes naturally because of the mother tongue. But I hope you are able to digest and understand whatever is being explained so far. Now, let's focus on this particular part. Can you help me with this part? AB plus BA. How will you prove whether it will be symmetric or skew-symmetric? The logic remains very simple, students. I'll again take its transpose. So I'm going to take its transpose, right? So we know that transpose goes individually on each term if there is addition or subtraction. So I will write it as transpose of AB plus transpose of BA. Now what I do next is that transpose over multiplication can also be distributed, but the order gets reversed. So AB transpose will be B transpose A transpose, and BA transpose will be A transpose B transpose. Do you get that? Now what I do next is a very simple conclusion, that A and B, since they are symmetric matrices, their transpose will give the original matrix only. So B transpose A transpose can be written as BA plus A transpose B transpose can be written as AB. I hope you can see that BA plus AB can be written as AB plus BA as well if you needed. And this is exactly what I originally began with, which means that this matrix is again a symmetric matrix, because if I took the transpose of it, I got the same matrix. Were you able to understand this particular part? Let us get back to another property. What is the next property here? AB minus BA is a skew-symmetric. So how is that possible? If everything is happening to be a symmetric matrix, why are you calling it to be a skew-symmetric? Because there is this negative sign. AB minus BA I'm talking about, right? So let me take this particular portion only. Let's work on this portion only, where I'm removing this sign from here, this sign from here, this sign from here, and this sign from here. And let's see what result do I get. So now I'm beginning with AB minus BA, right? So AB minus B I'm beginning with. So whether it is addition or subtraction, it gets distributed. So here I'll have AB minus BA, but AB transpose minus BA transpose, because transpose can be distributed over addition or subtraction. Here if I take the AB transpose, it will be written as B transpose A transpose. If I take BA transpose, it can be written as A transpose B transpose, but negative sign will stay there only. We know A and B are symmetric matrices, so B transpose A transpose can be written as BA minus A transpose B transpose can be written as AB. Now, if I take the negative sign common, I'll have AB minus BA. What does it mean? Do you not think that it means when I begin with AB minus BA transpose, I got negative of AB minus BA? Well, that is not a property of a symmetric matrix, rather it is a property of a skew-symmetric matrix. So I took the transpose of a matrix and I got the negative of it, which meant that this matrix over here is a skew-symmetric matrix. Did you all get that conclusion? Did you all understand that part? With that, let us talk about the next property. What is it? AB is a symmetric matrix if AB is equal to BA. I hope you're able to digest this part as well. What I'm trying to make you understand is, let's say I'm given that AB is equal to BA. Okay, so let's work on the third property. I am told that AB is equal to BA. This is what I'm told. And then I'm supposed to draw a conclusion, right? I'm asked to make a comment on AB, whether it will be symmetric or skew-symmetric. Also, additionally, I am told that AB is equal to BA. Now, what conclusion can be drawn? Let's look at that part. See, I am taking the transpose of AB. We all can. So, AB transpose will be, I hope you know, B transpose, A transpose. That is not confusing at all. I hope you're getting it very clearly. Now, what happens next? The next part remains very simple. B transpose will be A and A transpose will be A because A and B are symmetric matrices. Now, we know that AB is equal to BA. That is given. This is not always true. This is a particular thing which is given in this question, that if AB is equal to BA. So if that is true, then only I'll write BA as AB, and what I'll again be able to claim is that AB transpose turned out to be AB, which means AB will be symmetric if AB is equal to BA. Then only we will be able to say or call that AB is a symmetric matrix. Were you able to understand all these properties? If you have understood all these properties, let me move to the next part of this video where we'll delve into further some more properties of these matrices. Now let us bring some more conclusions on this. In this particular scenario, I am told that A and B are skew-symmetric matrices. So if A is a skew-symmetric matrix, I need not say that A transpose will be minus A. And if B is also a skew-symmetric matrix, B transpose will also be minus B. Now let's begin with the first part. A and B are skew-symmetric matrices. A plus minus B, AB minus BA are skew-symmetric matrices. Okay, let us work on it. So first of all, I'm working on A plus minus B and I'm taking its transpose. Let's see what result do I get. Okay, so let's work on it. I know that this transpose can be distributed over addition or subtraction to these individual matrices. So it will be A transpose plus minus B transpose, right? Now what? We know A transpose is minus A, B transpose is minus B. So it will be minus A plus minus B, right? I hope no confusions on that. Now, I'm taking negative sign common. So I am taking this particular negative sign. I hope you can see this particular and this particular negative sign common out of it. So when I do that, do you not think I'll be getting negative of A plus minus B? And what I got was that I took the transpose of A plus minus B and I got negative of A plus minus B. That clearly makes us understand that A plus minus B is clearly a skew-symmetric matrix, because transpose of this turned out to be negative of the original matrix. I hope this property is understood by you all. What about the next one? The next one is AB minus BA. This one I'm talking about, right? So AB minus BA is what we are willing to conclude. What about AB minus BA? Let's work on that. So AB minus BA is what we are trying to work upon. Can you help me with AB minus BA, students? What about that? I hope the conclusion remains very simple. On negative sign, it can be distributed. So I can write it as AB transpose minus BA transpose. What we know additionally is on product, the sign, on product, the transpose can be distributed, but the order gets reversed. So AB transpose can be written as B transpose A transpose minus B A transpose can be written as A transpose B transpose. I hope there is no confusion on B transpose A transpose will be written as minus B minus A. So minus minus plus, that will be BA. And here A transpose B transpose will be written as minus A minus B, that will be AB. So here I'll have BA minus AB. What I do next is a very simple conclusion, students. I take negative sign common out of it. So if I take negative sign common out of it, I'll be left with AB minus BA. So what I got was AB minus BA, but with a negative sign. What does it mean? That AB minus BA transpose was equal to negative of whole of AB minus BA, which means that AB minus BA is going to be a skew-symmetric matrix. Did you all get that part? Now let's talk about AB plus BA. What comment can be made on AB plus BA? Okay, so this time I'll be talking about AB plus BA. So I'll straight away start putting this plus sign over here. So I'm taking AB plus BA this time. Okay, so I'm beginning with AB plus BA transpose. What does it mean? AB transpose plus BA transpose. I hope there is no confusion on it. Then I'll have B transpose A transpose plus A transpose B transpose, which means BA plus AB. This is what I'll get. So what I have gotten is BA plus AB. Can I write BA plus AB as AB plus BA? So if BA plus AB can be written as AB plus BA, what does it imply? It implies that AB plus BA transpose turned out to be AB plus BA, which means transpose of original matrix is equal to the original matrix, which means that AB plus BA is a symmetric matrix when A and B are two skew-symmetric matrices. Are you able to digest all what is being explained so far? These are not just some simple ordinary properties I'm explaining right now. These are all questions asked by JEE mains previously. So all what we are learning is again going to be merged someday, some year in some question, and then they'll be asked. So whatever is being explained as individual properties are actually going to be some questions in JEE mains. I repeat my statement, students. These are not some very simple properties I'm explaining right now. These are the properties which will be asked as it is in terms of questions by JEE mains in advance. Remember that. Now let us come to the next part, the next property. If A is a skew-symmetric matrix and C is a column matrix. C is a column matrix. I hope you remember what do you mean by column matrix? That there will be only one column, but there can be multiple rows. Then C-AC is a zero matrix where C-AC is conformable. So conformability should be ensured. I repeat, a very straightforward property here that is again going to be used or asked by JEE mains. And if you know this particular property, you will be able to directly write the result or the answer. But some of the students, if they don't notice, if they don't pay attention to this particular property, they will solve it thoroughly and they will get answer, and then they'll feel happy that yes, they finally made it and they got the answer. But if you are intelligent enough, if you invest some time in remembering or learning this property or understand it here at this stage, then in the real examination hall or during the tests, if you observe the question and if you observe such things given in that question, you can directly come up with the conclusion in the answer. Are you understanding the importance of these properties? So these are not some simple properties we are trying to mention or put here. No. These are the properties which are the facts, but these are the facts which are constantly and repeatedly used by JEE mains in advanced in their questions. And what students do is that they solve all the questions all the time and then they feel happy after solving the questions. Yes, feeling happy is your right. You are definitely allowed to do that. But what you must understand is that if you could invest some time right now at this stage and understand these properties, and if you could directly apply these properties in these questions and get the answers within seconds without solving them again much, then why should you not do it? That is exactly what you call the optimization. Learning something at this stage, having this tool with you, and then with the help of this tool, you actually enhance your efficiency. You bring more efficacy in your solutions. You get your results more quickly. That's exactly what you do when it comes to optimize things, and that as humans we do, right, students? So that's exactly what I'm constantly mentioning, that if this property can be used, you will get the results very quickly. So you are constantly mentioning this property should be used. What is this property? We are very good to know. Yes, I'm going to explain the property now. The property says if A is a skew-symmetric matrix. So first of all, what you need to understand is that A should be a skew-symmetric matrix. Let's say I take A matrix as of order 3. So let's say A is a skew-symmetric matrix. Now what does it mean? That if I take its transpose, it will be negative of A. And the order of A I am taking to be 3. So A is, let's say, a 3 by 3 matrix. Any confusions on that? I hope so far there are no doubts, queries or concerns. Proceeding ahead, what I know next is if there is a column matrix C. If there is a column matrix C. Now, conformability should be there. So I am taking another column matrix C, and what I'm going to do is I'm going to take C dash AC. So I am going to take C dash AC, right? Now what is going to be the value of C dash AC? Okay, so C dash is going to be a row matrix. I hope you're getting it. If C is a column matrix, C dash will be a row matrix because you're taking the transpose. So column and rows are interchanged, which means if C was a column, C dash should be a row matrix. So C dash will be a row matrix. Then you have this matrix A, right? And then you have this matrix C. We are running short of space here, so I'll just bring it here. So let's write it in this manner, C dash, then you have this A, and then you're multiplying it with C. I'm not writing the whole structure here, just explaining the property so that you get it very clearly. So we have this matrix A, which had the order 3 by 3. Now, let's pre-multiply A with C dash. So C was a column matrix. If C was a column matrix, do you not think the number of rows should be 3 and the number of columns should be 1? So I'll call C matrix as 3 by 1. So if C matrix is a matrix of order 3:1, 3 rows and 1 column, so C dash will be having the order 1 into 3. I hope there is no confusions on that. So here what I'm trying to make you understand is if I multiply C dash with A, what will I get? I hope you know that conformability is assumed that this 3 and this 3 are equal, which means the product will have the order 1 into 3. Right, so when you do this C dash A thing, that matrix will have the order 1 by 3, and you have another matrix C which you are willing to multiply, which is having the order 3 into 1. Now with that, when I proceed further, what will I get? I can see the conformability is still there. This 3 and this 3 are same, so the product will have the order 1 into 1. But when you finally find out the product, which means C dash AC, that matrix which is going to be of the order 1 cross 1, this result over here is going to be a null matrix, a zero matrix. This entry, this element, this value C dash AC is going to be 0. That's exactly what I'm trying to make it. If you don't get this part, I am not giving you the complete proof, but I am giving you the idea, the hint through which you can derive the proof. For example, you take the matrix A as, what is A? A is a skew-symmetric matrix. So you can take A as 0, 0 and 0, and then you can take an H here, then you can take minus H here, you can take G here, you can take minus G here, you can take F here, and you can take minus F here. You can take a matrix C, any matrix C. Let's say you can take matrix C as 3 by 1 matrix. So 3 by 1 matrix, a column matrix, you can take any entries, for example A, B and C. Now if you do this C dash A then C, and when you find the final result, you will get the entry to be 0. This will be a matrix with the value, with the entry as 0. So this will be a null matrix, a 0 matrix of order 1 by 1, and it will have only element which will be 0 if you do that. So algebraically also you can prove it, which I'm not doing at this stage in this one shot, but I'm giving you the complete idea, complete hint, complete result. And if you have learnt this result at this stage, I'm not asking you to re-evaluate this in the examination hall. Use this as a fact, as a property. What is the property, students? The property is very simple, that if A is a skew-symmetric matrix, mind you, A should be a skew-symmetric matrix. Then if C is a column matrix, then C dash AC will be a null or 0 matrix. This is always true. This is always true. Always remember that. Conformability should be there, which I'm not mentioning time and again, assuming that if product is being done, conformability was there. I hope this particular part is very well understood by you all during this explanation as well, through this explanation. But if you didn't get that part, I am asking you to take the screenshot and keep it as a cheat sheet with you, right? With that, let's just go ahead with the next property. What do we have in the next set of rules if we were to explore them? Let's have a look ahead. Then let's talk about few more matrices. Some of you must be wondering, sir, how many matrices should we study? We have understood a lot of already. Are there some more? Yes, there are some more. There are some more, just there are some more. Then we are moving ahead with the questions, of course, but I was supposed to make you understand all these definitions first, then only will understand or start solving questions, because there is a lot of theory, a lot of concepts, a lot of simple terminologies on which a very broader category or a huge category of questions can be formed. And what they usually do is they merge these concepts. So there can be a question which will use the concept of singular matrix, or sometimes symmetric matrix or involutory matrix, and these three are merged together and questions are framed. So that's where you need to understand that first you should have a very good understanding of all these basics, the terminologies, the definitions. Then only we'll be able to solve questions with more confidence and with more clarity, right? So here we have another type of a matrix which is called the orthogonal matrix. Now what is it? Have a look at that particular part. See, we will have a matrix, of course, a square matrix. So mostly all of these classifications are related to the square matrix only. If you have a matrix where if I multiply that matrix with its transpose, so there is a matrix and you're multiplying it with its transpose, a square matrix, and if it generates an identity matrix, so a matrix when it is multiplied with its transpose, and if it gives me an identity matrix, then such matrix is said to be an orthogonal matrix. Remember this. This is again a very crucial result, a very important result. Now, what does it mean? Do you not think it means a very important conclusion that whenever you have A transpose is equal to I, then A inverse will be A? What do I mean by that? Let me try and make you understand this. There is some conclusion here. There is some confusion here, I believe. I am trying to make you understand something very simple, that if you have this A, there is a correction here, mind you students, A transpose is equal to identity matrix, right? Now if I pre-multiply it by A inverse on both these sides, so I'm having A inverse times A transpose is equal to A inverse. Now A inverse times identity matrix will give you an identity A inverse only. So here A inverse into A will give you an identity matrix. So identity matrix into A transpose is equal to A inverse, which means identity matrix into anything will give me the original matrix only. So A transpose is equal to A inverse. So that's the correction over here. What you need to understand is the small correction here, which is that if A into A transpose is identity matrix, which means if A is an orthogonal matrix, in that case what you must remember is that A inverse will be equal to A transpose. That is a very important conclusion we have been able to draw. But this will be true only when A is an orthogonal matrix. So if you were to discover that there is an orthogonal matrix, if you were to discover or explore that there exists an orthogonal matrix, and if you were asked to find its inverse, then don't follow the complete approach of finding the inverse of a matrix. We'll understand the method of finding the inverse of a matrix, which is amazingly huge, lengthy, and of course cumbersome. But if you ever encounter a matrix which happens to be an orthogonal matrix, which you will realize by looking at the matrix, by having this particular property being applied, that A into A transpose is identity matrix, then of course the way we understand that if in the numerical world, in the world of numbers, if a number is multiplied with its reciprocal, it gives us 1. X into 1 by x is 1. So in the world of matrices, if I multiply a matrix with something and if I get the identity matrix, then those two matrices which are getting multiplied with each other are said to be inverse of each other. What I'm trying to say here is that if I could draw this conclusion that A and A dash, their product, A and A transpose, the product of them is generating an identity matrix, then A and A dash are inverse of each other, which means A is the inverse of A transpose and A transpose is the inverse of A, vice versa. What I'm trying to make you understand is that remember this as a result that whenever you see an orthogonal matrix, then you should be able to conclude that A inverse will be A transpose, which means the inverse of this matrix will be nothing but simply evaluate its transpose. I hope you're getting this particular part. Well, let's learn some more properties. If A and B are orthogonal, then AB is orthogonal. That is also something very crucial you should remember. I repeat, what I'm trying to say is that if A and B, these are the two matrices. What kind of matrices are they? That they will fulfill this property that if I multiply them with their transposes respectively, of course, and if they're generating identity matrices, then their product AB or even BA will also be an orthogonal matrix. That is also a property which you must remember. Third property says if A is orthogonal, then A inverse and A transpose are also orthogonal. I need not prove them because A inverse and A transpose are same. A inverse and A transpose are same because if A is orthogonal, A inverse is only A transpose. So if you have A transpose I, which means A transpose into A is also I. So if A is orthogonal, A transpose is orthogonal. And if A transpose is orthogonal, A transpose is A inverse, which means A inverse is also orthogonal. So always remember three things together. Always remember three things, that if you are having a matrix A, and we are told that this matrix A is an orthogonal matrix. This is what we are told. What does it mean? It means that when this matrix A is multiplied with its transpose, it will give me an identity matrix. First learning, first result, first conclusion. Second learning, what you need to understand is that if A and A transpose is an identity matrix, that implies that A inverse will be equal to A transpose. So are you not realizing these three things are going to be orthogonal? A and A transpose are orthogonal because if A into AT is I, that means AT into A is also I, which means if A is orthogonal, then I would say that A transpose is also orthogonal. So if A transpose is orthogonal, which means A transpose is A inverse, then A inverse is also orthogonal. So three things are there. If A is orthogonal, then A inverse and A transpose are also orthogonal. I hope you are able to digest and understand this particular conclusion and result. And if you have understood this particular part, let us move ahead with the next part, which is finally a question. Let's read it, understand it, and then we'll solve it together. By the time I solve it, you can pause this screen and attempt it by yourself as well. Avoid the addiction of looking at the solution always. Avoid it. Even at this stage, I will always emphasize that once you have watched these one shots, practice the DPPs which we are providing you. Those are the hand-picked questions for you, very selected questions for you. We all pick those questions for you and ask you to solve them to master all the concepts which we are teaching you in these one shots. Not just that, if they are not sufficient for you, solve the previous year's questions. They are always the best source you can have. Instead of solving any other material which is basically derived or inspired from the previous year's questions only, we will always emphasize you to go to the main source, which is the previous year's questions. Always focus on the previous year's questions. That is the most important part. Coming back to the discussion we were having, this is a question asked by JEE Mains in 2025. Have a look at this particular question so that we can solve it together. What does the question say? The question says there is a matrix A, cos theta 0, minus sin theta 0, 1, 0, sin theta 0, cos theta. Okay. And if for some theta between 0 to pi, we are told that A square is equal to A transpose. We are told that A square is equal to A transpose. Some of you might have noticed it already. If you haven't, I will make you understand it, but I am still highlighting this part time and again to make you understand that there is something very crucial hidden over here with this hint given that A square is equal to A transpose. Think more. Now, along with that, then the sum of the diagonal elements of the matrix, this A plus I whole raised to the power 3 plus A minus I whole raised to the power 3 minus 6A. And of course, here I is the identity matrix. This I'll work upon later. But as of now, can I start working on this? Even before I start working on this, can I deduce something from here? A square is equals to A transpose. Okay, let us work on this particular result whenever somebody says that A square is equal to A transpose. So if I am told that A square is equal to A transpose, right? I am pre-multiplying both the sides by A inverse. Can we do that? So if I pre-multiply both the sides by A inverse, I'll have A inverse into A is equal to A inverse into A transpose, right? I hope there is no confusion on that. Now, when you see this thing happening over here, can you not see A inverse into A is an identity matrix? So here, if it is an identity matrix, I into A is basically A, which is equal to A inverse into A transpose. Okay, let's keep this result with us. We might need it somewhere, or we may want to use it somewhere. Before I begin with this, let us focus on this result. What are we given as A? So we have this matrix A, which we are given as cos theta 0 minus sin theta, right? Similarly, we have 0, 1, 0, and then we have sin theta, then we have 0, and then we have cos theta, right? So these are the elements of this matrix A. Forget this result for a while. Let's say I am willing to multiply A with its transpose. So what I do here is I am multiplying A with its transpose. So I'm writing A transpose also here. So I'm multiplying A with its transpose. So what I'm doing is I am multiplying A with its transpose. So let's write the transpose of A. What is going to be the transpose of A? So cos theta 0 minus sin theta, the first row will become the first column. So that will be cos theta. Then you have 0, then you have minus sin theta. What is next? 0, 1, 0, your second row will become the second column. So that's your 0, 1, 0. Then what is next? Sin theta 0 cos theta. The third row becomes the third column. Sin theta 0 cos theta. Usually what we recommend to students is that always remember that if something like that is given to you, can you not do something more interesting? What is that? Cos theta, sin theta, sin theta, cos theta, I'm supposed to write a lot many times. So usually what students do to save time is they write cos theta as C and they write sin theta as S. So that's how you can save some time. So while doing this matrix multiplication, you can use such abbreviations. Now, let's begin with the product. What is the product that I'll get? So I hope this part is very well understood by you all. Now let's talk about the product. So the product goes row and column. Confirmability is there, square matrices of the same order. So here, if I'll begin with this particular part, I'll do a little more quickly. I hope we're able to understand the matrix multiplication more clearly now. So here, if I take the first row is cos theta 0 sin theta, and if I multiply it with the first column, cos theta 0 minus sin theta. So cos theta into cos theta, cos square theta, 0 into 0 is 0, minus sin theta into minus sin theta is sin square theta. So cos square theta plus sin square theta is 1. So our first element in this journey of A times A transpose is going to be 1. I hope there is no confusion on that. Now let's talk about the second. I'll take the first row again, but the second column. What does it give to you? Cos theta into 0, 0 into 1, minus sin theta into 0, which means 0 plus 0 plus 0. That gives you 0 here. So here the next entry will be 0. What about the next entry here, students? If I pay attention to the same row, but the third column, what will I have? Cos theta into sin theta plus 0 minus sin theta into cos theta. So sin theta cos theta plus 0 plus minus sin theta cos theta. So sin theta cos theta gets cancelled by sin theta cos theta, which means you are again left with another 0. So again I'll have a 0 here. Did you all get that? Now let's focus on the next part. The next row, second row comes into picture. 0, 1, 0 into cos theta 0 sin theta. So 0, 0 and 0. So that entry will be 0. Let's put that term here. So that will be 0. Now let's focus on the next part here, students. What is the next part? Again, I'll choose the same row but the next column. So 0, 1, 0 into 0, 1, 0. So 0 into 0, 0. 1 into 1 is 1. 0 into 0 is 0. So 0 plus 1 plus 0 will give me a 0 here, 1 here. So that will be 1. Now let's talk about the next part here, students. What is the next part? 0, 1, 0 gets multiplied to the third column, sin theta 0 cos theta. So 0 into sin theta 0, 1 into 0 is 0, and 0 into cos theta is 0. So 0 plus 0 plus 0, that again leaves us with another 0. Okay, so let's focus on the next part here. That is sin theta 0 cos theta 0 minus sin theta. I hope you must have noticed sin theta cos theta plus 0 minus sin theta cos theta. Sin theta cos theta plus 0 minus sin theta cos theta will be 0, as we have already learned this part here previously. So that is again 0. Now I hope most of you must have started getting what are we going to get. Now With the next part, the third row remains there as it is, but I'll move to the second column. Sin theta into 0, 0 into 1, and then cos theta into 0. That will be 0 plus 0 plus 0, which will again be 0. So that's 0. Now let's talk about the next part, where again we have the third row and the third column. What do we get? We get sin square theta plus 0 plus cos square theta. So sin square theta plus cos square theta is basically an identity, and that leaves you with 1. What does it mean? What does it mean, students? Can you see something happening over here? If you still are not able to notice something very important here, A into A transpose is an identity matrix. And if you didn't get that part, look at this part which we have discussed previously, that if you get A into A transpose as an identity matrix, what does it mean? It is an orthogonal matrix. With that, you can draw a conclusion that A transpose and A inverse are equal. Now, let me get back to the discussion we were having. If A into A transpose are equal, I know a conclusion that A inverse is equal to A transpose. Now, let's get back to the discussion. We are told that A square is equal to A transpose. We are given that A square is equal to A transpose, right? Now, let's talk about that conclusion here. I am told in the question I'm given that A square is equal to A transpose, right? But what do we know? We know that A transpose is equal to A inverse. So from there, I can write that A square is equal to A inverse. I hope there is no confusion. On that. If I multiply both the sides by A, so if I am multiplying both the sides by A, what do I get? So I'll have left hand side as A cube, where A into A inverse will be an identity matrix. So A cube is turning out to be an identity matrix. That's our conclusion number 1, that A cube is an identity matrix. That is something very crucial we have been able to draw. How will I use it? Now let us come to the expression which they were asking us to explore. What is that? A plus I whole cube, A minus I whole cube minus 6A. Okay, so let us work on that. What are we working upon now? A plus identity matrix whole cube. I think the next part was plus. Okay, so plus A minus I whole cube, then minus, I think we were dealing with 6A. Okay, so let's have this 6A over here. I hope there is no confusions on that. There are no confusions on that. I hope you know how to expand this identity, but remember, expanding the identity with matrices is a little cumbersome because you cannot apply the properties of identities, but here it will not be a problem. It will not be a problem because the second part is an identity matrix. So identity matrix, whether pre-multiplied or post-multiplied, won't affect the original matrix, whichever it is getting multiplied. So here, if one of the matrices is the original matrix A and the other one is an identity matrix, I can apply those identities. Which identities, students? A plus B whole cube. That can directly be applied. If you don't get it, you multiply A plus I 3 times, A plus I, A plus I, A plus I, and then you get the result. Then also you'll get the same result. So remember and mark my words that A plus I whole cube can be expanded with the formula where I is an identity matrix. Then only you are able to do it. Had there been A plus B whole cube, then I wouldn't recommend you to do that because order matters in that case. But with an identity matrix, whether you multiply it whether you treat it as a pre-factor or post-factor, it won't create any change. It won't create any sense here. It won't make any sense here, and that's why I can apply this identity. So here, A plus I whole cube can be done, which will give you A cube first. Then you will have I cube. Then you will have 3A square I, which is 3A square only. Then you will have 3AI square, which will be 3A. I hope you are getting that part. Now, some of you must have already noticed that some terms will get cancelled from here and other terms will get doubled. But if you didn't, let me write this part also. So A minus whole cube will be A cube. Then you have minus I cube. Then you have minus 3A square. Then you will have plus 3A. I hope there is no confusions on that. And then you have minus 6A. Minus 6A is also there, which I'm writing here. I hope this is properly and perfectly visible to you all. Great. Now, the next part remains very simple, students. How do I begin with that? I hope you can see I cube and I cube are getting cancelled. And then you have this 3A square with this 3A square getting cancelled. Even this 3A with this 3A and with this 6A is getting cancelled. So everything is cancelled except for the two terms A cube and A cube. So A cube and A cube leaves us with 2 times A cube. So that is what we have gotten. But what I know is that A cube is an identity matrix. So if A cube is an identity matrix, 2A cube will be 2 times I. So the expression we were asked is 2 times I. So what is it becoming? It is becoming 2 times I. I is 1, 1, 1 and the diagonal, and the other elements are 0. But if I multiply it by 2, it will become 2, 0, 0, 0, 2, 0 and 0, 0, 2. I hope there is no confusion on that. Now what were we asked? We were asked the sum of the diagonal elements. See, JEE 2025 was kind enough to write the sum of the diagonal elements, but if it writes that find the trace of this matrix, then what will you do? In that case, you should be aware of the meaning of the trace, and that's where I'm constantly emphasizing that these small terminologies, these very basic definitions, all these things you should be aware of. We could have used the term trace. In that case, you should know this particular thing. So basically, they are asking you the trace of this, because all what we were asked is boiling down to this particular expression, this matrix, and the trace of this matrix, I hope I need not explain, is basically sum of its principal diagonal elements, which is 2 plus 2 plus 2, which is nothing but what, students? That is, the trace of this matrix is going to be trace of what we were asked in the question, right? I'm writing it as Q basically to make you understand. It's going to be 2 plus 2 plus 2, which is nothing but 6. So were you all able to understand that the answer to this question will be 6? How simple it is. How did we crack it? You should be able to understand this particular learning, that here, if I simply pay attention to some things, and when that learning is clubbed with this learning, creates something really important. This part did not play much crucial role, although I should have used it somewhere, but we did not. We were not required to use this, but still, if this learning with the learning we know about the orthogonal matrices, if clubbed together, gives you some amazing results. I'll tell you what students may do in the real examination hall. They will find A cube first by multiplying A with itself thrice, and then apply this particular result. And there they will come up with this conclusion that after simplifying that expression, they'll also get the same result. We are perfectly fine and okay with that. But if you pay some more attention, if you are a little more observant, then will you not be able to crack it with this much ease? And that's exactly what we are emphasizing, that if you pay attention to the details, you can crack these questions with a lot of ease. Well, if this part is understood by you all, let us move ahead, let us proceed further, and let us understand a few more things. There are certain properties which are related to the determinant of matrices. Few things we have already learnt in determinants, but there are certain things which should be understood in the context of matrices. That's exactly what we'll explore in this particular part. Have a look at that. We'll begin with the first part. So we are rediscussing determinants, but in the context of matrices. So there is something new, there is something very interesting, there is something very important we'll discover, and these properties as it is used in the questions. So at a broader level, you may think that this has no use, but at minute level, at very macro level, if you see, you will start seeing that such small details play a very crucial role. Trust me, it is not about looking at it from a broader perspective. It is never about it. It is more about it that how closely, how minutely, how attentively, how cautiously, how alertly you look at things. That observation, that analytical skill matters the most in this examination as far as especially JEE mathematics is considered, and you should stay aware of it. What I'm trying to say here is that if A and B are square matrices of the same order. So first of all, to understand it, let's take two square matrices, because we'll be taking the determinants, and determinants can be taken of the square matrices only. These two matrices are of the same order, so if in case I were to multiply them, I would be able to, right? So I have two matrices, the square matrices of the same order. Now, if determinant A exists, then A should be a square matrix. That's exactly what they are trying to say, what I have just said. So if I were to find the value of the determinant of a matrix, well, that will be possible only when it is a square matrix. Otherwise, you cannot find the determinant of a matrix. Otherwise, it will be a matrix only. It will have its own elements, nothing else. Now, what is the next part? This I think we have already discussed while discussing the chapter determinants, that whether you take a determinant or you take its transpose, both will have the same determinant. So a matrix and its transpose will have the same meaning. So that property is understood in the context of matrices, but there we needed indeterminate, so we used this property that you will have a matrix, a square matrix of course, or you can take its transpose. In both the cases, the determinant of these two matrices will be same. Remember this. Next is, we have already explored this part. We have already explored this part that what is it? Determinant of AB can be written as determinant of A into determinant of B, and if that is so, I can write it as determinant of B into determinant of A, which means I can write it as determinant of BA. Now that is something very crucial, remember it. So determinant is not always written as det, it is written as this modular sign as well, but this is not that modular sign, this is determinant of A. This looks like a modular sign, but this is the determinant of A. So determinant of AB is equal to determinant of BA, which is equal to determinant of A into determinant of B. That is a very, very crucial property. Remember it. We will use it at a lot of places, at lot many times. Remember it. It is used at a lot of places. Well, as we have already discussed, if you are having an orthogonal matrix, then its determinant is going to be either +1 or -1. What I'm trying to make you understand is that here, as you must have seen in the previous question here, this A we have already concluded was an orthogonal matrix. I'm trying to make you understand that even if you expand this matrix, either by Sarah's rule or some standard expansion of determinants with respect to any row or any column, you will get its value as either +1 or -1, which can be proved algebraically as well. So whenever you are given an orthogonal matrix, it will have its determinant equal to 1. If you don't want to see it like this, there is another proof which can be given here. That proof is even simpler. See, what we know so far, what we know about an orthogonal matrix. So we know that if it is an orthogonal matrix, its square is equal to basically its I repeat, its square is equal to an identity. Sorry, I'll come to the basic definition before square. I hope because we don't need this definition, we need this particular definition, that whenever you're dealing with an orthogonal matrix, square is not something which I'll get later, but what I know is that A into A transpose is I. I'll begin with this part. A square is what I'll get after taking the determinant here. So I'll begin with this particular definition, that whenever I have an orthogonal matrix, remove this particular part A square. Let's say I have this A into A transpose, which I know is an identity matrix. This is true for an orthogonal matrix. I repeat, if A is an orthogonal matrix, we know that A into A transpose will be an identity matrix. Now, let's say I take determinant on both the sides. So determinant of A into A transpose will be equal to determinant of I. Now you must remember, determinant of I will be 1. The determinant of identity matrix is always 1. So here it is 1, and I can write it as determinant of A into determinant of A transpose. What we know is that determinant of A and determinant of A transpose is always same. So I am writing it as determinant of A into determinant of A, because determinant of A transpose can be written as determinant of A. And here we have this 1. Now, what I have next is that determinant of A into determinant of A can be written as determinant of A square, which is 1. And from here, I can conclude that determinant of A will be +-1. I hope the conclusion is very simple. What you need to understand is that whenever A is an orthogonal matrix, you should remember that its determinant is going to be +-1. Any confusions on that, students? Let me get back to the properties here. That is again a very important, a very crucial, a very amazing property. Whenever you deal with a skew-symmetric matrix, and if it is having order odd, if it is of, sorry, let's talk about this property first. If you are having a skew-symmetric matrix and if its order is odd, then its determinant will always be 0. I repeat, for a skew-symmetric matrix, if its order is odd, then its determinant will always be 0. How? Let's look at that. See, if you are given a skew-symmetric matrix, which means A transpose is equal to -A, I'll take their determinant on both sides. So if I take determinant of A transpose, it will be determinant of A transpose. And here if I take the determinant of -A, it will be determinant of -A. But we have understood this particular property previously, that if you are asked to take the determinant of Ka, where K is a scalar, A is a square matrix of order n, then we know it can be written as K to the power n times determinant of A. What is n here? N is the order of the matrix A. Do you remember that? Now, if I were to use the same property, will I not say A transpose or A, whatever I take, the determinant will remain same. So I'm writing determinant A here. But here, if I take this minus 1 out, I know that this is a matrix A which has order n, which is, let's say, odd first of all, which is of odd order. So if it is having odd order, minus 1 to the power n minus 1 to the power odd will be minus 1 times determinant of A. So here I'm having determinant of A, this will be minus 1, and this is determinant of A. Why? Because n is odd here. So if a number is equal to its negative, the number should be 0, or minus 2A will be 0, which means determinant of A will be 0. That's exactly what I'm trying to convey here, that whenever you deal with a matrix which is of order odd, then such matrix, which was a skew-symmetric matrix, my dear students, will have its determinant 0. Now that's again a property which you should remember. For example, in a question, you encounter a skew-symmetric matrix and you are supposed to deal with its determinant. And what you also see is that it is having an order odd. Let's say 3 by 3 matrix, and it is a skew-symmetric matrix. And if I require the value of its determinant, then I won't think much. I'll directly use this result that, sir, since it is of order 3 or odd and it is a skew-symmetric matrix, which by observation you can conclude principal diagonal will be 0 and the other elements will be negative pairwise. I hope you know that 2 1 2 3 3 2 like that. In that case, that determinant will have that matrix determinant will be 0. Always remember that. Not just that, there is one more conclusion, that if you are having a skew-symmetric matrix of even order, well, in that case, its determinant will be a perfect square. So skew-symmetric matrix odd order 0, skew-symmetric matrix even order perfect square. What? The determinant I'm talking about. Next thing, as we have already learnt and discussed in the determinants as well, that determinant of a scalar into a matrix is equal to scalar raised to the power the order of the matrix times the determinant of that matrix. As we have already discussed here in this part as well, while discussing this conclusion, this is exactly what I'm talking about in this particular part. So I hope there is no confusion on that part or that portion. Now let us proceed with some more properties that again we deal with this particular thing, that whether you multiply some matrices and then take their determinants, or you take their determinants and then multiply those determinants, they'll give you the same result. The property is very simple, it is very evident. If you pay some attention to it, you will understand it by yourself. Let's say I'm multiplying certain matrices, right? So what do you mean by that? I'm multiplying A thrice, so A into A, and then I'm taking the determinant. I hope you're realizing what does it mean. It means I'm asking you to find the determinant of A cube. Or vice versa, what I know is I can take their individual determinants, because on product determinants can be splitted or distributed. So it will be determinant of A into determinant of A into determinant of A, which is what? Which is the cube of determinant of A. That's exactly what I'm trying to make you understand. If you multiply A n times and then you take its determinant, or you take its determinant first and you raise it to the power n, it will yield the same result. What you must remember is that product should be a natural number. I mean, you should multiply it natural number of times, which means that n should be n natural number. Did you understand this particular property? Well, there comes a very crucial property which you should remember, and if you could remember this, again by observation, you can deduce a lot of results. Let's say if you encounter a diagonal matrix, let's say there is this matrix A and it is a diagonal matrix which has the entries 2 0 0 0 3 0 and then 0 0 minus 1. Then if I were to ask you its determinant, let's say I'm asking you to find the value of this determinant, so you need not do much. What you could notice was that it was a diagonal matrix. Determinant will be the product of its diagonal elements. Product of its diagonal elements means 2, 3 and minus 1 are to be multiplied. So 2 into 3 into minus 1, that is nothing but minus 6. That's exactly what they are trying to say. If there is a matrix A which is a diagonal matrix whose diagonal elements are A1, A2, A3 and so on, so its determinant, the determinant of matrix A will be the product of its diagonal elements A1 into A2 into A3 up to An, whatever number of elements are there on its principal diagonal. I hope no confusions on that. With that, let us proceed further and let's see what is singular and non-singular matrix. Students treat this chapter as a confusing chapter, not because of its, confusingness. I don't know whether this kind of word exists or not, but I hope you are understanding my intent. This chapter is not a very complex chapter. What you need to understand is things are very simple in this particular chapter. The problem is there are a lot many things in this chapter. Now, for instance, look at this particular case. This is a very simple thing that if you are having a matrix and if its determinant is 0, you will call it singular, and if its determinant is non-zero, then you'll call it non-singular. How simple it is. But it becomes very amazingly huge or cumbersome process for students to remember all these terminologies. Even as teachers, we tend to forget these things at times because of a lot many terminologies: involutory, idempotent, nilpotent, Hermitian, skew-Hermitian, symmetric, skew-symmetric. A lot of types of matrices are there. But what you need to understand here in this particular case is that remembering them and knowing them and applying them at the right time in the right question is more important. Orthogonal matrix, how easy that question was if you were aware of that. That's exactly the next part plays, where the next part plays a very crucial role, where you start understanding singular and non-singular. How simple it is that if the determinant of the matrix is 0, it will be singular. If the determinant of the matrix is non-zero, it will be non-singular. But the challenge now is that you should remember all these terminologies. You should learn the definitions of these terminologies. You should have the understanding of all these terms which we are exploring in this particular one-shot video. Whereas if you can see here, you'll have a square matrix, you will take its determinant, so it will be singular if its determinant is 0, and it will be non-singular if its determinant is non-zero. That's it. For example, we had a determinant, we had a matrix, we found its determinant either by expansion or Sarus rule, and if it is found to be 0, I'll call it singular. If it is non-zero, I'll call it non-singular. That's it. Singular means the determinant of that matrix should be 0. As simple as that. Moving ahead, let's solve a question. What does it say? Now, understand this question by using this simple definition and by merging the combination, chapter permutation combinations. They have brought a very good question here. What is the question? Asked by JEE Mains in 2024. There are 4 elements in a set. Now, what do they ask? The number of singular matrices. Now, a student will be able to solve this question only when he understands the meaning of singular matrix. If you don't know the meaning, you won't be able to, and that's exactly what I have been emphasizing upon, that first you should have the understanding of all the terminologies, then only you'll be able to solve the questions based on matrices. Now, what are they saying? That what will be the number of singular matrices of order 2? Okay, so the problem is a little simpler for us because with order 2, you know a lot of things. Whose elements are from the set 2, 3, 6, 9? Since there is nothing nothing related to repetition is mentioned, which means I'm allowed to do that. What does it mean? I'll have a 2 by 2 matrix. Okay, so I can have a 2 by 2 matrix. Let's say I can have a 2 by 2 matrix like this, and it will have 4 elements. Of course, since it is a 2 by 2 matrix, it will have 4 entries: 1, 2, 3, 4. Now let's say this is a matrix A. For a while, let's call it a matrix A. And what are we told? That this matrix A is a singular matrix. What does it mean? It means that determinant of this matrix should be 0. This means that if we are asked to keep this matrix to be a singular matrix, which means the determinant of this matrix should be 0. Now, what am I asked? I can have 2, 3, 6 and 9 as many number of times as I want to have at these places, and I now need to ensure that that determinant should be 0. Now, what are the different ways? So while solving questions based on this particular category, where we are asked to use permutation and combinations basically indirectly, we should have a structured approach. We should follow a systematic approach. Now, what is that systematic approach? I'll begin with this thing that, sir, let's say all the elements are same. What do I mean by that? My point is very simple. If all the elements are, let's say, 2 for a while, 2, 2, 2, 2, do you not think I need not think much? The determinant of this particular matrix will be 0. Why? Because 2 into 2, 4. 2 into 2, 4. So if all the elements are same, then the determinant will be 0, which means this matrix will be singular. So do you not think the first case, If I talk about the first case means when all the entries are same. Let's say these entries are A, B, C, D. So if all the entries are same, so when all the elements are same. I'm writing all this to make you understand this, but you need not write this in the real examination hall because you're not supposed to write a board examination's answer. You're writing JEE's answers, which you're finding actually, so you need not bother about the approach or the solution or the steps. You should directly find out the answer, but to make you understand it in a more clearer manner, I'm writing it in a more systematic manner. So when all the elements are same, I'll have the first conclusion, which means if either I have all the 2s, all the 3s, all the 6, all the 9s, then I have the value of the determinant to be 0, which means it will be a singular matrix. So in how many ways can that be done? Sir, you have 4 choices. Either you have 2 at all the places, or 3, or 6, or 9. So the number of ways in which this can be done will be 4. So I have 4 choices. So 4 ways. In 4 ways I can do this. What about the second approach? What can I do next? Now, can I have this thing in mind that I choose one element, one element, and then I choose one element thrice at these 3 places, and the fourth element remains unequal. So I'm basically using 2 elements, but previously in this case what I did was I kept that one element at all the 4 places. But here in this case, is that a possibility that I use one element at 3 places and the other element, the second element, at one place? And can I have that matrix, that determinant to be 0? I don't think so, because if I am using one element at 3 places, for example, I'm choosing 2 and 3. Let's say. So I hope you're realizing 2 and 3 won't create this kind of a combination, because 2 into 3 will be 6, 2 into 2 will be 4. So this case is not possible. Let's say I choose 2 and 6. So with 2 and 6 also, I cannot have this possibility, because 12 and 4. Even with 2 and 9, if I start looking at this directly, 2 and 9, 9 into 2, 18, 2 into 2 is 4. So this case will not be there. This case will not get created. Not even with 3, 6, because 3 into 3, 9, but 6 into 3 is 18. Not even with 6 and 9, because 6 into 6 is 36 and 6 into 9 is 54. So this will not be a possibility. So the second case which we were thinking of is not possible. What about another case? Let's take another case where I say, let's say that we still choose 2 elements, but they appear at 2 places. I mean, they repeat twice. What do I mean by that? Let's say I choose 2 and 3. So I choose 2 and 3, but I choose them like this. I choose 2 and 3 like this, and then I choose 2 and 3 like this. And I think there is a possibility. 2 is appearing twice, 3 is appearing twice, and with this 2, 3 and with this 2, 3, the product will be same, 6, 6, and 6 minus 6 will be 0. And that's how I can get the value of this determinant to be 0, which means this matrix will be a singular matrix. But how can I arrange it? So first of all, I have cracked this formula that I need to have 2 elements out of these 4 elements. So what I'm saying here is that 2 elements appear twice, right? So this is the case when two elements appear, and they appear twice, right? The language may not be very clear, but I hope you're able to understand the intent. What I'm trying to do here is that out of these 4 elements, I'm supposed to select 2 elements. Well, in how many ways can that be done? So out of 4 elements, 2 elements can be selected in 4C2 ways. And means I'm supposed to use a multiplication sign here. The basic principle of counting, and means multiplication, or means addition. That's exactly what I'm doing here. Now what I do next is, please pay attention, and how many ways can I arrange it? See, I have chosen, let's say, 2 and 3. Now what are the different possibilities? See, the different possibilities are very simple. What can I do here is, let's say I have placed this 2 and this 3 here. Let's say this 2 and this 3 is placed here. Now what are the 2 choices I have for other 2 and 3? There are only 2 choices I have. See, I will place 2 and 3 like this, or the other choice I can have is I can place 3 and 2 like this. Did you get that? Because vice versa, I'll have the product to be 6. So these are the 2 choices. But this 2 and 3 can also be arranged in 2 ways. Why? Because here, if I could arrange 2 here and 3 here, I could have arranged 3 here and 2 here. In that case also, with this 3, 2, with respect to this case, I have 2 more possibilities, because again, I could have 2 and 3 here, then also the product is 6. Or I could have had 2 and 3 like this, then also the product is 6. So basically, if I could conclude, what is the final conclusion? At these two places, I have two choices. For these two places, I have two choices. And for each of those two choices, I have another set of two choices. First of all, out of these four elements, I'll choose two elements. Then at these two, at this principal diagonal, I can place those two elements in two ways. And then the other, that other pair, 2, 3, I'm able to arrange at two ways, 2, 3 or 3, 2. And then 2, 3 or 3, 2 can be arranged again in two ways, which means 2 into 2, there are 4 possibilities. I hope this part is very well understood by you all. Now 4C2 has its own way of expansion. 4C2 in a short manner can be expanded as 4 into 3 divided by 2 into 1, and then you have 2 into 2, where this 2 gets cancelled by this 2. What are you left with? 4 into 3, which is 12. 12 into 2 is 24. So total number of ways are 24 ways. So from here, I could find 24 ways. I hope there is no confusion on that. 4C2 is 4 into 3 by 2. I hope that part is understood by you all. Into 2 into 2. Right? So that gives you 4 into 3, 12 into 2, 24 ways. So here 4 ways, then I could get 24 ways. What next? Now, the next part. What is the next part? Can I have 3 distinct elements? I mean, now here, what did I have? I could see initially I started with one element appearing at all the 4 places. Then I thought of two elements. Now, can I have 3 elements? I mean, out of these 4 elements, can I choose any 3 and have their product? I mean, I can ensure that such that the determinant becomes 0. Can I have that in that sense? Let us try and do that. If that is possible, we'll explore that possibility. See, I choose any 3. I am going to choose any 3. Let us choose any 3. Let's say I have chosen 2, 3, 6. So if I'm choosing any 3, one should be repeating because I am supposed to fill 4 places. So let's say I have chosen 2, 3 and 6. So with 2, 3 and 6, can I have this? Let's say I'm repeating 2. So 3 and 6 will be 18. 2 into 2 will be 4. No, that's not a possibility. I need that difference should be 0. Let's say I choose 3 twice. So 6 into 2 is 12 and 3 into 3 is 9. 12 minus 9 is not 0. So that is not again a possibility. So 2, 3, 6. One more possibility is left, which is again not going to work because 6 into 6 will be 36 and 2 into 3 will be 6. 36 minus 6 is not 0. So 2, 3, 6 doesn't fulfill that criteria. Let's say after 2, 3, 6, let's choose 9. I hope you're realizing that is again not a possibility because 2 into 3 will be 6. 9 into 9 is 81. No. 3 into 3 is 9. 9 into 2, 18. 9 and 18. Difference is not 0. Even with 2 into 2 is 4. 9 into 3 is great, which is again not 0. So 2, 3, 9 does not work. The next triplet if I were to choose could be 3, 6 and 9. Again, I'll choose it. Whatever I do, I won't have it. I cannot have it. I hope you are seeing it very clearly because 3 into 3 is 9. 6 into 9 is greater. 6 into 6, 36. 9 into 3, 27. No, that doesn't work. And the last possibility will be 9 into 9, 81. 6 into 3 is 80. No, that doesn't work. So the only possibility, the third case now, which I'm left with is that I have all the 4 elements distinct. If I take all the 4 elements distinctly. So the third case will be if I keep, I'm writing the third case here, students. I hope you don't mind that. So the third case will be if all 4 elements are distinct. Now, what are the possibilities first of all? Can I pair them? Can I actually generate a determinant which will give me a value 0? Can I get a singular matrix? Let us try and see. So 2 into 3, 6, 9 into 6, no, that doesn't work. 3 into 6, I hope you can see 3 into 6 is 18, 2 into 9 is also 18. Is there any other possibility other than that? I don't think so because apart from that, there is no other possibility. So the only pair I'm getting is 2, 9 and 3, 6. Now, again, I'll begin with 2, 9. Can I place 2 and 9 here? In how many ways can that be done? So either I place 2, 9 like this or I place 9, 2 like this. But do I have only this choice? No. But let's explore this possibility first. Although with PNC also you could have done it. But let's say that for this place I have 2 choices. Either I choose pair 2, 9 or 3, 6. See, either I could have placed 2, 9 or I could have placed 3, 6. So I have 2 choices at this place. Either 2, 9 or 3, 6. So out of these 2 pairs, I'll choose a pair which can be done in 2C1 ways. But with that pair also I have 2 choices. See, when I chose 2, 9, I could place it like either 2, 9 or I could have placed it like 9, 2. So for that pair also I have 2 choices, 2, 9 or 9, 2. But again, whichever pair I were to choose, whichever arrangement I were to choose, let's say I have chosen an arrangement 9-2. With respect to that arrangement also, I have two choices here for this 3 and 6, because either it could be like 3 or 6, or it could be like 6 or 3. In both of the cases, 18 minus 18 will give me a 0. I hope you're understanding. So with each of that arrangement, I have again two possibilities with 3 and 6. 2C1 is 2. So 2 into 2 into 2, which is clearly nothing but 8. So these are the three different cases I'm able to generate. I hope you are understanding. Either this will be possible, or this will be possible, or this will be possible, which means I'm supposed to add all these results. So when you add all these results, 24 plus 4 is 28. 28 plus 6, I hope you can clearly see, is 36. So if I'm asked how many singular matrices can be made, so I'll say 36 matrices will exist such that their determinant will be 0, or they will be singular matrices with the 4 entries 2, 3, 6, 9, so that the matrix will be singular. The error students commit is that they straight away think of this particular case, they get the answer as 8 and they mark and move ahead. They don't think of these two cases. So what was the catch here? The problem students commit is they don't think that the terms, the elements can be repeated, and that's a problem. And when elements can be repeated, different possibilities arise. So it is not just about this first and second possibility which we thought of. We explored two more possibilities which didn't work, but rather had they worked, we should have brought 5 cases into this picture. I hope you're realizing this question is not as simple as it looks or as it appears from the language of the question. It was a little more complicated, but with this a little more complicated or a tough or a simple moderate level of question, we were able to understand two things: singular matrix, how do you ensure that the determinant of a matrix is 0, and the third part, that how do you apply the concepts of permutation and combinations in this category of questions. So look at this particular question, understand all the cases, and then we'll move ahead. From here, let us move to the next part of our video where we'll discuss adjoint of a matrix. So with adjoint, we'll move to the inverse of a matrix, and then we'll discuss matrix polynomial, Cayley-Hamilton, eigenvalues, and that will be the culmination of this chapter. But this is not the final part of the chapter. This is the beginning of the climax of this chapter, which is huge in itself. And this is such a crucial part that it plays an amazingly greater role in your JEE journey. JEE means loves this particular topic, adjoint of a matrix. A lot of properties are there. How should you apply them? What can be interpreted? What can be learned? And what kind of questions are asked? That all will be discussed in this particular section. Then there comes inverse, and then a lot more, which have patience. We'll focus on one ball at a time. So let's focus on adjoint first. Let us not worry about all what is yet to come. Okay. So let us focus on adjoint of a matrix. What do they say about adjoint of a matrix? Let us look at that. A very simple concept, students. It is not a difficult one, but the terminologies confuse you, because now adjoint is going to be something really simple if you understand it step by step. What is it? If there is a square matrix, of order n, let's say, and Cij be the cofactor of this matrix. We know what is cofactor in the chapter determinants. We have already learnt that, so I need not explain that part again. You find the minors and then cofactors. Do you remember that? I hope it was taught so well, so profoundly, that you must not have forgotten it. I am sure of it. So with a matrix, which is a square matrix, I'll found the cofactor of it. And once you have found the cofactor of it, what is the next step? Then the transpose of that cofactor matrix. If you take the transpose of that cofactor matrix, then that matrix is called adjoint of. Now some of you must be wondering, sir, how much is needed to be done? I mean, up to what extent should we remember all of this? Well, we'll practice a lot. You will solve a lot of questions through which you can remember all of these things very clearly. So what is the step? The step involves very simple things. For example, I am given a square matrix A. What have I done here is, I have found the cofactor matrix. What is the cofactor matrix? Cofactor matrix is C11, C12, C13, C21, C22, C23, C31, C32, C33. These are the cofactors of these elements: A11, A12, A13, A21, A22, A23, and then A31, A32, and A33. Now, the job is not done yet. Now, once you have found the cofactor matrix, you take the transpose of it. What is the transpose? Interchanging rows by column. So first row becomes first column, second row becomes second column, and the third row becomes third column. And that's how you get the adjoint of A. So 3 steps. First step, you find the cofactor and then the transpose, and that's the job done. You will get the adjoint. So what is the adjoint of A? Adjoint of a matrix is the transpose of cofactor of a matrix. Simple, isn't it? I hope you're understanding it very clearly. Sir, you are saying simple with so much ease and you are not realizing what all is yet to come. Trust me, a lot is yet to come. But don't worry, we'll discuss everything in a very structured and systematic manner that you will get to know everything in a very detailed format. We'll solve a lot of questions as well so that you get a lot of clarity on it. Basically, adjoint has its own properties. And JEE Mains and Advanced ask questions on those properties. So we'll explore the properties once you have understood the concept of adjoint. So let me proceed further and start making you understand these properties. Before we understand these properties, let me take an example and give you more clarity that how do you find the adjoint. Let me take a very simple example. Say that we are given a matrix A and it has certain elements 2, 3, 4 and 6, right? Now, what am I supposed to do? Find the adjoint of A. I'll write its cofactor. I hope you know that we know how to write its cofactor. If you have forgotten, I'll make you revise one more time. Otherwise, then I'll not do it. So how do you find the cofactor? Here, there is a shortcut as well. But even if you have forgotten that shortcut, to make you understand the concept of cofactors, let me write it more clearly. I'm writing the cofactor of A, right? So I'm writing the cofactor of A here. So how do you write the cofactor of A? So cofactor of A will be having here. What is the cofactor of 2? If I talk about the minor of 2, I'll remove the row in column which contains 2. So I'll be left with 6. So minor of 2 will be 6. Minor of 3 will be 4. Minor of 4 will be 3. And minor of, I hope I'm going right. Yes. Minor of 6 will be 2. But this is the minor of A. What about the cofactor? I hope you remember. Plus, minus. Why? Because this is 1, 1. This is 1, 2. 1, 2. 1 plus 2 odd. This is 2, 1 odd, which means negative, and this is 2, 2 even, which means positive. So what have I written over here is I have written the cofactor. I have written the cofactor of A, but the job is not done yet because what is the adjoint of A? The adjoint of A is given by transpose of cofactor of A. So I'll take the transpose of cofactor of A. So if I take the transpose of cofactor of A, I think I'll get the result. So what will be the final result? I'm supposed to take its transpose. First row 6 minus 4 becomes the first column. 6 minus 4. Second row minus 3, 2 becomes the second column, which is minus 3, 2. So that is nothing but the adjoint of A. Did you get that part, students? Were you able to understand this? I think the job was simple. Let me tell you the short technique as well, which you all must be aware of. What is that short technique which you can directly apply in a question based on 2 by 2 matrix? So whenever you're given a 2 by 2 matrix and you're asked to write its determinant, how will you write its determinant? Let us observe and analyze that. The result is very simple. Can you not see the first thing? If it is a 2 by 2, then only this short technique is applicable. That's the limitation of this short method. So I hope you can see with the matrix A, I had 2, 6 in the principal diagonal. In adjoint of A, I had 2, 6, but they were interchanged. So first of all, whenever there is a 2 by 2 matrix and you are asked to write its adjoint, you will interchange the elements of the principal diagonal of the 2 by 2 matrix. That's it. So 6 and 2 are interchanged. So 2, 6 became 6, 2. What about the other part? Other part was 4 and 3. It will remain as it is 4 and 3, but with negative signs. So for example, if to give you more clarity on this, let's say I'm given a matrix X which has the elements A, B, C and D, and I am asked to write the adjoint of X. What will be the adjoint of X, students? I hope you know how to do that. First of all, interchange the principal diagonal elements. So A and D are interchanged, so I'll have D and A. Did you get that part? Then the non-principal diagonal elements will remain at their places only. So B and C will remain at their places only, but they will come with negative signs. That's it. That's it. That's what you do with a 2 by 2 matrix if you were asked to find its adjoint. This is not something I have told you regarding the 3 by 3 matrix. There you'll have to follow the steps. First you'll find the cofactor, then you'll find the adjoint. There are certain short techniques available on internet, you can find them, but trust me, when it comes to solve them through whichever method, they call it short methods, through whichever method you find the cofactor and then adjoint, you will end up spending the same amount of time. So there is no short technique as such when it comes to finding the adjoint of a 3 by 3 matrix. The standard method takes the same amount of time, which is taken by a short technique claimed by a lot of other teachers on the internet. So don't fall into the trap of a lot of short techniques. They consume a lot of time. Remember, this can be learned. This is a general result which should be learned by you all, but something related to a 3 by 3, a lot of short techniques are there, but stick to that original standard authentic method. That will actually take the same amount of time which is consumed by other short techniques as well. So don't worry about that part. Now let us work on the next part, where we'll discuss a lot of properties related to the adjoint. This is the section of the video from where a lot of questions are asked by. There are amazingly huge amount of questions asked on adjoint and its properties, because adjoint is merged with transpose, inverse, determinant, and a lot more. Scalar multiplication and then matrix multiplication, a lot of things are merged together with the concept of adjoint, and then questions are formed and framed. An adjoint is that foundation from where the inverse is getting generated. The concept of inverse comes into picture. So this is one of that most important concepts from which questions are asked by JEE Mains and Advanced. So remember this, that this is something where you need to pay a lot of attention, and a lot of questions are asked from this particular chunk, from this particular section. Now what is it? Let's begin with the first property. If A is a square matrix of order n, then A into adjoint of A or adjoint of A into A will be equal to determinant of A into an identity matrix. I repeat, the very simple part I'm trying to make you understand is that if you multiply a matrix with its adjoint, then it is commutative, which means either you multiply the matrix with its adjoint or you multiply the adjoint of a matrix with its matrix. Pre-factor and post-factor, if you were to interchange, that can be done here in this case only, and that will give you determinant of A into the identity matrix. That is what I'm trying to make you understand with this particular property. Property number 1. Here in this one shot, I'm not explaining all these properties. Most of the properties are directly learned and understood by you all. So this is the first property which you should remember, that if a matrix is multiplied with its adjoint, the reason is very simple. I'll give you a very simple clue with the 2 by 2. If I could explain, if you could get it very quickly. Let's say this is a 2 by 2 matrix. Here, let's say A11, then we have here we have the A12, then you have A21, then you have A22, right? And you are multiplying it with its adjoint. So first I'll write cofactor, then I'll write adjoint. What is the cofactor? A11 will have its cofactor as C11, A12 will have its cofactor as C12, which will come here because this is the adjoint. Then A21 will have the cofactor as C21 and A22 will have the cofactors as C22. So I have written the adjoint of this matrix. So let's say this is the matrix A. If this is the matrix A, I'm multiplying it with its adjoint, right? Now, how does matrix multiplication take place? I hope you know that. The idea is very simple, students. I hope you know how to multiply matrices. So A11, A122 with C11, C12. Do you remember in determinants we have learnt that if any row or any column of a matrix or a determinant is multiplied with the corresponding cofactors of those elements, then it gives the value of the determinant. So A11 into C11 plus A12 into C12 will give you the value of the determinant. So can I write here determinant A as the first element? Then any row with other rows cofactors will give you 0. So A11 into C21 plus A12 into C22. So here I'm having the first row's element, but I'm multiplying them with the cofactors of the second row, which means it will give me the value 0. Same, A21, A22 when multiplied with C11, C12. Second row, but the cofactors are of the first row, which means the value should be 0. But here A21, A22 when multiplied with C21, C22, which means A21 into C21 plus A22 into C22. That is multiplying second row with their corresponding cofactors, which means it will give me the value of the determinant. So it will give me the value of the determinant, which is determinant of A. Now, what does it mean? I hope I need not explain this part. After this matrix multiplication, determinant A is a scalar quantity which can be taken common from all the entries because they are 0. So I'll be left with determinant of A, then 1, 0, 0, 1, which means I'm left with an identity matrix of order 2. That's exactly what this property is trying to convey here, that A into adjoint of A or adjoint of A into A will give you determinant of A into identity matrix. And that lays the foundation of inverse of a matrix. We'll discuss that part later, but I hope this part is very well understood by you all. It has its own corollary, it has its own deduction. What is that deduction? Let's have a look at that. The deduction says if A is a square singular matrix. What do you mean by a singular matrix? Its determinant will be 0. If A is a square singular matrix, which means its determinant will be 0. So if you multiply A with adjoint of A, or if you multiply adjoint of A with A, determinant of A is 0 because A was a singular matrix. So 0 into an identity matrix will be a null matrix because 0 into an identity matrix will be 0, 0, 0, 0, which means I'll get a null matrix. That's your deduction number 1. So always remember, if you have a singular matrix, which means if its determinant is 0, then if you multiply that matrix with its adjoint, or if you multiply the adjoint of a matrix with that matrix, it will always give you a null matrix. Did you understand these two properties? Do they make complete sense? Are you able to digest all what is explained so far? Now, with that, let us come to the part where I'll explain how do you find the inverse of a matrix. The point is very simple here, students. I'll come up with this conclusion only. A into adjoint of A is determinant of A into identity matrix. This is what we have explored from the property number 1. Now, if I take determinant of A here, the denominator, so will I not be writing it as, I'll come to this particular property later. Before I discuss this property, let me bring a conclusion from here only. Let's say I write it here. What I know here is that A into adjoint of A is equal to determinant of A times that identity matrix of that same order. A is a square matrix, we all know that. Now, what I do next is I bring this determinant of A here. So what do I have here is A into adjoint of A divided by determinant of A is equal to an identity matrix. Now, here I'm trying to make you understand that if let's say for a while I'm calling adjoint of A divided by determinant of A. This is going to be a matrix basically because adjoint of A is a matrix, 1 by determinant of A is a scalar quantity. So this will be a matrix basically. So I am calling it a matrix B. So what I'm getting here is that A into B is an identity matrix. So if I'm multiplying A with the matrix and if I'm getting an identity matrix, which means they are inverse of each other, which means the inverse of A is B and the inverse of B is A, which means if I were to write, then I will say that the inverse of A is B. What was B? B was adjoint of A upon determinant of A. So if I were to ask you the inverse of A, you will come up saying, sir, it should be adjoint of A upon determinant of A. What does it mean, students? It means whenever I ask you to find the inverse of a matrix, you will say, sir, find its adjoint and then divide that adjoint by determinant of that matrix. That will be the inverse of that matrix, because if I multiply a matrix A with adjoint of A upon determinant of A, I'll be getting the identity matrix, which means A is the inverse of adjoint of A upon determinant of A, or adjoint of A upon determinant of A is the inverse of A, vice versa, because inverse are unique. And for the existence of inverse, do you not think that there comes a clause that determinant of A must not be 0? Because if determinant of A becomes 0, A inverse will not exist. So if you want to claim that inverse exists, then you should have this thing in mind, that that matrix should be a non-singular matrix. So all of this is possible if A is a non-singular matrix. So A should be a non-singular matrix, which means its determinant should not be 0. Then only you can find its inverse. Did you all get that particular part? Did you understand this property? With that, let me come to the next property. This property number 1, I hope, has made complete sense. Now, let me bring the second property into picture. What does it mean? It means, let's say, if I'll come to the conclusion. Let me talk about the derivation first. See, what we know is that A into adjoint of A is determinant of A into identity matrix. I'm taking determinant on both these sides. So here I'm taking determinant and here also I'm taking the determinant. So determinant of A into adjoint of A, determinant on product can be splitted. So I'll have determinant of A into determinant of adjoint of A. This is what I've written over here. And here if I take the determinant of A into identity matrix, what does it mean? Let's say I'm taking the determinant of A into this identity matrix. We know determinant of K into a matrix is equal to that K, that scalar quantity raised to the power n times determinant of that identity matrix. And determinant of identity matrix is 1, which means it leaves us with determinant of A to the power n into 1, which means determinant of A to the power n. So here on the left hand side we have determinant of A into determinant of adjoint of A, whereas on the right hand side we are left with determinant of A to the power n. Now in the next step, if I take this determinant of A on the right hand side, am I not left with determinant of A to the power n minus 1? Which is exactly I'm trying to make you understand that determinant of adjoint of A is equal to determinant of A to the power n minus 1. It is not just another property I'm trying to make you understand. I'm trying to give you the conclusion from here is a very simple part. Let's say I am told that there is a determinant A. There is a matrix A. So if you are given the matrix A, can you find its determinant? Yes, we can find its determinant. Let's say I am given this matrix A. This matrix A we are given in the question, right? Now, if we are given this matrix A in the question, I can find the determinant of A. So I know this value of determinant of A. And if somehow, if I need to find the value of the determinant of adjoint of A. So despite finding the adjoint of A, I hope you know how cumbersome this process is, finding the adjoint of A. You find the cofactors first and then you take the transpose and then finding the determinant. No, that is not what you're supposed to do. Let's say I'm asked to find the adjoint of A. I'm asked to find the adjoint of A. Rather, I'm asked to find the determinant of adjoint of A. So with the help of determinant of A only, I can find it. All I need to do is determinant of A should be raised to the power n minus 1. What is n here? N is the order of the matrix A. So A was a matrix of order n. So if it was a matrix of order n, and if I'm asked to find the determinant of adjoint of A, all I'll do is I won't find the matrix adjoint of A. No, I won't waste time in doing that. What will I do is I will write determinant of A raised to the power n minus 1. So that is the advantage of knowing the properties, and these are called short techniques. People call them shortcuts. No, they are not shortcuts. They are not just abruptly developed by someone. They are standard theorems, they are standard properties, they are the basic concepts. These are the nuances. If you know them, you can crack the questions with a lot of ease, and that's exactly what we are investing time upon. So we are investing time on learning the core concepts, the nuances, the basics, the methods. And the more you know them, the easily you can get the answers. With a lot of ease you can get the answers. So I hope you're understanding. We are actually working on increasing our efficiency or the efficacy. And JEE is not an examination which actually checks your ability to comprehend. It is an examination which checks your depth, which checks your understanding of concepts. And that's what I'm trying to make you understand time and again, constantly, that learn all these concepts. And once you have learned all these concepts, these are called the short techniques. So they actually are not short techniques, they are the methods, the theorems, the concepts. The more you know them, the better you get at them, and that's how you find the answers, right, students? Well, if this property is understood by you all, you must have learned its application as well, that how and when and where you should apply it. Now let me come to the next part where we discuss the next property. The generalization here is very simple. Before I come to the generalization, the part which I'm trying to make understand is, let's say if I have this particular portion, this I'm coming up with, I'll explain it later, but as of now, remember this as a result. Let's say in a question I'm given adjoint of a matrix A, right? First bracket, then second bracket, right? and then I'm asked to find its determinant. I am asked to find its determinant. Then again, some of you may think, so then you need to find the adjoint of A, then find the adjoint of that determinant matrix, and then find the adjoint of that matrix. No. And then you find the determinant. No, you're not supposed to do that. You should use these properties. Now, what is that property? This expression. A lot of questions are asked on this particular single property. I am constantly saying this is not just an ordinary property. I'll show you. If you just pay attention to the questions asked by JEE Mains in these previous years, you will ask an amazingly huge quantity of questions based on this particular property. They ask you questions based on this property, and this one I am showing it to you here. This property over here, that determinant of a scalar into a matrix is equal to scalar to the power n into determinant of that matrix. These two properties are clubbed together at a lot many times, and they ask you questions based on that. Now, this property says here, if I am seeing adjoint is getting repeated 3 times. How many times, students? I can see adjoint is getting repeated 3 times. So all I need to do is I need to write determinant of A raised to the power order -1. What is order here? So let's say order, the matrix A has the order 3. So A is, let's say, a 3 by 3 matrix. To make you understand, I'm taking this example. So let's say if A was a 3 by 3 ordered matrix. So I'll use 3 minus 1. So 3 minus 1 is 2. And then this 3. What is this 3? This 3 is the number of times adjoint has repeated. The number of times adjoint has repeated. This 3 is raised to the power of this 2. I'm not saying this 3 is the whole power of determinant A to the power 2. No. This 3 is the power of 2 to the power 3. 3 is the power of 2. So here, this means determinant of A raised to the power 2 into 2 into 2, that is 8. This is not 2 into 3, which would be 6. I hope you know the difference. Here it is the power of 2 only. This is not the power of determinant of A to the power 2. No. I hope you're learning the difference. So that's a formula which is very widely used by JEE Mains, and that's how you apply it. Although we'll solve a question on it, of course, don't worry about that. But I hope you're understanding this particular property and how is it used. Now, let me switch to the next part here, where we discuss the next set of property. Always remember that if you have two matrices, A and B, if you have, I hope I haven't skipped any part so far. Let me just check all what we have discussed so far. So yes, this property, all of this is understood. Yes, this has gone well. Now let's work on it. See, if A and B are square matrices of order n, and if I'm asked to find adjoint of AB, then also the order changes, and it is all happening because of the transpose. You have seen it in the transpose. If I'm asked to find the transpose of A into B, I find the transpose of B into transpose of A. That's exactly what happens here, because adjoint internally uses the concept of transpose. So I'm not coming up with the complete explanation of the derivation here. I'm giving you the direct result. So whenever I'm asked to multiply two matrices and then find their adjoint, don't do this, that you find adjoint of A into adjoint of B. Adjoint is not distributable on this product. Rather, the order gets reversed. For example, if I'm asked adjoint of ABC, then I'll write it as adjoint of C into adjoint of B into adjoint of A. The order matters with matrix multiplication. I hope you know that. That's exactly what we'll do. So if A and B are square matrices of order n, and I'm asked to find adjoint of AB, then it will be adjoint of B into adjoint of A. I hope you will remember it, and I hope you are understanding the reason as well. Well, there exists another property. If you are asked to take the transpose of adjoint of A, then what you can do is you can interchange the adjoint and transpose, which means you can take the transpose first and then you take the adjoint. Both will have the same result. Then what is the next property? These are the properties which we'll be using in the question. So don't treat them as just some simple properties. Rather, these are the properties which will be used in questions time and again repeatedly. Now, if A is a square matrix, a non-singular matrix, which means its determinant is not 0, of order n, then adjoint of A is equal to determinant of A to the power n minus 2 times A. I'll give a better version of this property here. Let me explain this particular property first with the explanation, and then I'll come up with the generalized conclusion here. Let's look at this. What do we know? That A into adjoint of A is determinant of A into I, the identity matrix. We have learned this conclusion. We have derived this conclusion. Let's keep this conclusion. What I do is here, A, and this A, I'm replacing by adjoint of A. What will I get? I'll get adjoint of A. Then I'll get adjoint of A. and here I get adjoint of A's determinant. So determinant of adjoint of A into identity matrix. Now, what do we know? What I know so far very clearly is that determinant of adjoint of A, we have already explored. It is determinant of A to the power n minus 1. This is a property which we already know. This is a property which we already know. Now, I am pre-multiplying both the sides. Which both sides? This sides. This equations, this expressions, both sides are multiplying by A. Pre-multiplication. So this is A into adjoint of A. I hope you can see here. Then this remains as it is, adjoint of A, and then you have A into determinant of A to the power n minus 1. So there is this matrix A, then you have this identity matrix which does not play any role at all, and then you have determinant of A raised to the power n minus 1. So here I have this part, I have this part. Just look at these parts. I have this particular portion here, left hand side, and this as the right hand side. Since it is a one shot, we already have very limited time, hence I'm not writing this entire derivation. I'm using this pre-written format so that we can understand the derivation and we can use this conclusion in our questions. But derivation is important. You will understand how are they applying these, and with these approaches you can apply these approaches in your questions as well. The derivations give you the idea that how were they able to think all this. Now can you apply such learnings in your questions? That's exactly what derivations do, so you should learn them. Now let us work upon our learning here. A into adjoint of A, do we know something related to it? Yes, we know that A into adjoint of A is determinant of A into identity matrix. So this thing I'll replace by determinant of A into identity matrix, and here I'm already left with adjoint of A, and here this is A into determinant of A to the power n minus 1. So if this determinant of A is brought on the left hand side, I'll have determinant of A to the power n minus 2, because previously determinant of A to the power n minus 1 there. If I further divide it by determinant of A, I'll be left with determinant of A to the power n minus 2. So I think we have the conclusion that adjoint of A is equal to A times determinant of A to the power n minus 2. That's exactly what this property says. This is exactly this property means. I hope you are able to digest this part, that adjoint of A is equal to determinant of A to the power n minus 2 times A. Now there is a generalization of it. There is a general result of it which you should remember, which will bring into picture. But before that, I hope this particular result will be remembered by you. This is not just an ordinary result, you should remember it. And the application of that result we have already discussed, that if you are having adjoint of A m times and you are asked to take determinant of it, then you write it as determinant of A to the power n minus 1 to the power m. So m is the power of n minus 1, as we have already discussed. I'll prove it with this particular simple example or simple derivation or simple result. What is it? What we know so far is adjoint of A is determinant of A to the power n minus 2 times A. This is what we know. Let me take determinant on both the sides. So if I'm taking determinant of both the sides, what will I have? Determinant of adjoint of A. This is what we are trying to find. But here it will be determinant of, this part you need to understand, it will be determinant of, let me write it here separately. Let me write it here separately so that you understand it better. I am finding the determinant of this scalar quantity, which is determinant of A to the power n minus 2 times this determinant A. I hope there is no confusion on it. There is no confusion on it. Now I'll use this property that determinant of K is a scalar, is equal to K to the power n times determinant of A. That's exactly what I'll do here. So what I get from here is that this determinant A to the power n minus 2 being scalar comes out. So when it comes out, it comes out as determinant of A to the power n minus 2 to the power n, which is the order of the determinant A, into determinant of A, which is written over here. And when you look at this particular part, determinant of A to the power n square minus 2n into determinant of A to the power 1, which means bases are same, powers will be added. You'll have determinant of A to the power n square minus 2n plus 1. I hope there is no confusion on it. N square minus 2n plus 1, if I look at that, becomes n minus 1 whole square. And that's exactly what I'm saying, that if adjoint appears m times, this 2 will become m. That's exactly what I'm saying. So remember this as a result. It is not just an ordinary result. This is a very crucial, very important result which you must memorize and keep with you during your journey. Now, Let us move to the next part of our video where we discuss the next property. If you are having a square matrix of order n and k is a scalar, then adjoint of Ka, this thing is not here. Let me just remove this so that you don't get confused with this part. This part is not here. So adjoint of Ka is equal to k to the power n minus 1 times adjoint of. This is again a property. How do we prove it? We have this result. What we know is this particular result where I say that A into adjoint of A is equal to determinant of A times I. This is a result which we'll use as a base here. If I replace A by Ka, so I'll replace A by Ka here, here and here. So this A remains, this A becomes Ka because I have done that replacement. Here I'm dealing with adjoint of Ka, which is exactly I'm trying to figure out. And then I have Ka here, determinant of Ka. We know determinant of Ka, this will be k to the power n times determinant of A. We know this particular property. We have discussed it a lot many times. Then what do we have here? See, here we have k to the power n. This k to the power n when divided by k leaves you with k to the power n minus 1. I hope there is no confusion on it. Then what you have next is, A into adjoint of Ka. I hope you can see it here. Now, what do we have next? The result is very simple, students, that this particular part, determinant of A into I, determinant of A into this identity matrix. Can I replace it by A into adjoint of A? Because we know that A into adjoint of A is determinant of A into the identity matrix. So from here, can I not say that this A into adjoint of Ka is equal to k to the power n minus 1 into A into adjoint of A? From here, if I pre-multiply both the sides by A inverse, what I'm saying here is I have gotten a result. Let me write that result first. The result is A into adjoint of Ka. This is what I have on the left hand side. On the right hand side, this is the result I have, which I have replaced by this, which is k to the power n minus 1 times A into adjoint of A. Now what I'm doing is I'm pre-multiplying both the sides by A inverse. So when I pre-multiply both the sides by A inverse, what is the result I'm getting? The result I'm getting is A inverse into A will give me an identity matrix, which will be I, and I into any matrix will be that original matrix. So on the left hand side, I'll be left with adjoint of Ka, right? On the right hand side, I have multiplied by A inverse, pre-multiplication from the left hand side. So K is a scalar. A inverse into A will again be an identity matrix. So here I into adjoint of A, which will be adjoint of A. So on the right hand side, it will be k to the power n minus 1 times adjoint of A. Again, it's my strong, humble, straightforward request that remember this as a result. Again, not just another property which we are asking you to learn. This is a very crucial result which is used by matrices. What is it? I hope that learning is understood by you all. Let us come to the next learning. What is that? Let us look at the next result. What is it, students? Let A be a square matrix of order n. So we have a square matrix of order n, and m is also a natural number. Then adjoint of A to the power n. Again, there is a small correction here, students. Let me make that so that you don't get confused. Let me remove this determinant sign here. So here, if I am told that you are asked to deal with an expression where you are asked to find the adjoint of a matrix raised to the power m. So the way we could interchange transpose and adjoint, the same fashion, the power and adjoint can also be interchanged, which means I can find the adjoint first, and then I can raise it to the power n. So this is also a very crucial property which you must remember. What does it say? Adjoint of A transpose is equal to transpose of adjoint of A. In the same fashion, I can write adjoint of A to the power m is equal to adjoint of A whole raised to the power m. So this is interchangeable, the way we could interchange transpose and adjoint. I hope you are remembering this. You are learning it. You are understanding all of this, what is being said here. Next property. That is again a very crucial property, and this single property will help you in solving a lot of questions in your examination. Another very crucial, very important property. What is it? Let's have a look at that. A and B are two square matrices of order n such that B is the adjoint of A. So what do we know? That B is the adjoint of A. So first of all, let me write it separately here. What are we told? That B is the adjoint of A, right? So I'm writing it like this. And K is a scalar quantity. Then always remember that determinant of A into B plus K into an identity matrix will be equal to determinant of A plus K to the power n. Why did it happen? Let's learn it from this proof. Have a look at this part. This can, even if you don't learn it, understand this derivation. If this particular result comes into a question, by applying this derivation, you can get the answer. What is that derivation? Have a look at that. We know that B is a matrix which is the adjoint of A. Yes, we know that. So, what will be AB? So, A will be A, but what is B? B is adjoint of A. So, if I were to write AB, can I not write it as A into adjoint of A? And what is the meaning of A into adjoint of A? As we have already learnt from the first property, A into adjoint of A is determinant of A into identity matrix. So here, in place of AB, I can write A into adjoint of A, which is determinant of A into the identity matrix. So the left hand side now becomes determinant of A into identity matrix plus K into identity matrix. What does it mean? This identity matrix comes common and you're left with determinant of A plus K, which is the scalar quantity. I hope you are able to understand this part here. If you are getting confused, I'll write it separately. We are dealing with determinant of A plus K whole times an identity matrix. Any confusions on that, students? I hope there is no confusion on that. Now let me come to the next part. What is it? This is a scalar. This is a matrix. So scalar comes out, but as raised to the power n, where n is the order of that matrix. So here I'll write this as determinant of A plus K whole raised to the power n times determinant of identity matrix. And what is the determinant of identity matrix? Well, that is 1. So 1 I need not write here. So that is the value I am mentioning here, determinant of A plus K to the power n. So always remember, if this result comes into picture, you should think of it like this. Will you remember it? Will you remember this as a result? If you haven't understood it, I'll explain it with an example so that you get more clarity on it. For example, let's say I give you a question. I'm just giving you an example so that you understand it better, so that you remember it as a result with this illustration. Let's say you have two matrices X and Y. We have two matrices X and Y of the same order where you're told that X is the adjoint of Y, right? And then I ask you to find the value of something where I give you that the value of the determinant X is 3, let's say, for a while. And then I ask you to find the value. The question is, this is all what you are given. And then I ask you to find the value of, then find, this is what you're given. If there are two matrices X and Y where X is the adjoint of Y and determinant of X is 3, then you need to find the value of determinant of let's say xy plus 3, yeah, or instead of 3, let's say I write, let's say 4 times the identity matrix of the same order. So x, y and I are the matrices of the same order, which I'm not mentioning here. What will be the value of it? I hope you must have understood. You can write the answer directly in the next step. What will be the answer here, students? You know the answer. Can you help me with the answer here? Can you help me with the answer here, students? Directly write your response in the chat box. What do you think would be the answer? I hope most of you must have cracked it, that determinant of AB plus K times identity matrix is equal to determinant of A plus K raised to the power n. That's it. So let's say if X, Y and these identity matrices of order 3, which means we knew the value of n, which was 3. So by using this formula, what will be the answer? The answer will be determinant of X. So determinant of X, what is the determinant of X? That is 3 plus K. What is K? K was 4. So 3 plus 4 raised to the power the value of n. What is the value of n? Which is 3. So what I need to find is 7 cube. And what will be 7 cube? 343. And that's the answer. That is the answer. Are you realizing? Some students may get stuck, sir, without knowing X, without knowing Y, without finding the adjoint, without dealing with this expression, how can we get the answer? But if you have understood this particular derivation over here, if you have understood this particular conclusion here, even if you don't, Even if you don't learn this property, if you have understood the derivation here, if you apply that same derivation or logic here, you can get this result and find the answer within 10 seconds. A question which may look impossible to a lot of students, which may consume a lot of time, can be done within 5 to 6 seconds if you just look at the details, if you just look at the certain things. Determinant of x, k, sum, power 3. That's the answer. Are you realizing? If you know the concepts, if you know the depth, if you have these properties, then you can get the answers with a lot of ease. That's exactly what I'm mentioning time and again. Understand the concepts, understand the nuances, get into the details. The more you understand it, the better you'll get at it. There's nothing as shortcut here. It is all the depth, in-depth concepts, the learnings, the nuances. Did you get this particular part? With that, let's move to the next part here. Next property, students, right? So next property is property number 9. What does it say? The property number 9 says adjoint of a diagonal matrix is a diagonal. A very important, a very crucial learning it is. What is it? It says if you have a diagonal matrix where A, B, C are the principal diagonal elements and the other entries are 0, 0, 0, then adjoint of it will be a very simple result. You find the product of these diagonal elements and then you can simply replace it. That product should be divided by these entries A, B and C, and that will give you the adjoint of A. What did I say here? Let's say ABC, the product is ABC. So when ABC is divided by A, you will get BC. When ABC is divided by B, you will get CA. When ABC is divided by C, you will get AB. So I repeat my statement. If you have a diagonal matrix, then its adjoint will also be a diagonal matrix. Learning number 1. Second learning, you can directly write the adjoint here, which means if I were to explain it with an example, I repeat my part here. For example, here you have 2, 3 and 1 as the diagonal elements. You have the 0 and 0 here, you have a 0, 0 here, and you have a 0, 0 here. That is a matrix, let's say X. And if I were to ask you, write the adjoint of X. So you need not put much efforts. First of all, you should understand that it will be a diagonal matrix. And the diagonal elements are also going to be very simple. First of all, find the product of C. For this position, you take the product of these two. That's it. So for this position, 3 into 1 will be 3. For this position, 2 into 1, that will be 2. For this position, 3 into 2, that will be 6. And then rest of the elements are going to be 0. That is it. That will be the adjoint of X. I hope you are understanding these properties. And along with that, remember this, that adjoint of an identity matrix is always an identity matrix. Any confusion so far, students? With that, let us solve this question. Look at this question. I hope you have read the details here. If you must have paused the video, you would have attempted it as well. So what are we given? A is a matrix of order 3 by 3. Determinant A is told to be 5. And then this expression has a certain value, which we'll explore later. Alpha, beta, gamma are natural numbers. Okay, that's fine. Alpha plus beta plus gamma is asked by JEE Mains in 2025. Okay. Let us explore this particular part where this question states something related to this. What is it? It says determinant of 2 times adjoint of 3 times A times adjoint of 2A, right? So this is what I am asked. I'll begin with this very simple property, students. Do we know that? Forget all this. Let us treat as a matrix. This will be a matrix. So 2 into a matrix and its determinant is needed to be brought into picture. What I know here is that this is going to be a matrix and this matrix is going to be a matrix of order 3 by 3. So this is going to be a matrix of order 3 by 3. I don't know its value, nor I'm interested in finding its value. But a scalar into a matrix and this determinant is needed to be taken. Do you not think that this property has its own application, that this should be k to the power n times determinant of A? So remember, this is a property I'll constantly keep on using in this particular question. Have a look at this. So 2 comes out. So when 2 comes out, it becomes 2 to the power 3 because that is the degree of this matrix or the order of the matrix, simply solves the degree. And here adjoint of 3 times A times adjoint of 2A is what I am supposed to do. So that is what I have written over here. I hope there is no confusion on it. Now let me get back to the next property. What is the next property? Do you remember this particular property which we have discussed previously here? Let me show it to you again so that you get more clarity on it. This particular property which we have, this one, I hope you can look at this one, and the previous one which we have discussed here, that determinant of adjoint of A is equal to determinant of A to the power n minus 1. As I have already mentioned, this has its own applications, and we'll remember this particular property, that determinant of adjoint of A is equal to determinant of A to the power n minus 1. This is what we'll use in this particular question. So let us use it here. Okay, now the other property I'm mentioning here. So here, determinant of adjoint of A is equal to determinant of A to the power n minus 1. So these are the two properties I'll use here very frequently in this question. How? Let's have a look at that. So here, 2 cube is there outside. Let's not bother about that. But then treat it as a matrix. We can treat it as a matrix. So adjoint of this matrix, and then its determinant is needed to be taken. So adjoint of a matrix is equal to determinant of adjoint of that matrix is equal to determinant of that matrix raised to the power n minus 1. So from here, I know that the order is 3. I know that the order is 3. So can I not say this adjoint can be removed and written as determinant of 3a times adjoint of 2a, and then this determinant raised to the power n minus 1. N is the order here, so 3 minus 1 is going to be 2. Tell me honestly, are you able to digest this much part, whatever I've done so far? Any confusions on this? I hope this part is very well understood. Now, let us focus further. Again, I'll go back to this property. Look at this particular portion here. Can I not say this 2 cube I'm keeping aside, this 3 into a matrix. So 3 is behaving like a scalar, comes out of the determinant and raised to the power n. So here, this 2 cube remains as it is, and then I'll have 3 scalar to the power order of the matrix, which is 3. But here, this determinant already had a power 2, so that power 2 should also be brought into the picture. Times the matrix which I am now left with. What is it? It is determinant of A times adjoint of 2A. Right, students? I hope there is no confusion on it. Whatever I've written so far, you have a complete clarity on it. Any confusion so far, students? Where did I get this 3 cube? 3, when being scalar, comes out of this determinant is raised to the power 3. But this already had a power 2, because of which I raised it to power 2 as well. Any confusions on that? Now, when I proceed further, I have some more conclusions or important derivations. Now, what is that conclusion? The second conclusion is that we know determinant of product of two matrices is equal to the product of their individual determinants. Well, why are we discussing that property? Because now here, determinant of A into adjoint of 2A. So this is a product of two matrices A and then adjoint of 2A. So can I write their individual determinants and take their product? Yes. So with that, I'll have the next conclusion, which is, first of all, I had this 2 cube. I hope you can see it very clearly. Then 3 cube whole raised to the power 2, which is 3 into 2, which is 6. So this is 3 to the power 6 here. Into, then if I were to write, I'll be writing it as determinant of A into determinant of adjoint of 2A. But all of that is needed to raise to the power 2. So here I'll have determinant of A square into determinant of, what was it? Adjoint of 2A, right? It should be adjoint of 2A raised to the power 2. I hope there is no confusions. There are no confusions on it. Now, what is the next property I'll be using? I'll reuse the same property. What I know from here is that determinant of A was given to be 5. So here I can replace it by 5. So here I'll have 2 cube, then 3 to the power 6, then I'll have a 5 square. Then what do I have next? See, again, adjoint of a matrix whole raised to the power 2, determinant of adjoint. Can I not again use this particular property, that determinant of an adjoint is basically determinant of that matrix raised to the power n minus 1. If I were to use that property here, I'll be saying that I should write determinant of 2A to the power n minus 1. So the order of A was 3, so 3 minus 2 is 2, and this is needed to be raised to the power 2. I hope there is no confusion on that. So in a simpler language, if I wish to write it as 2 into 2, that will be 4. So can I write directly it as 4? I hope there is no confusion on it. Now, The next property says, here you have 2 cube, then you have 3 to the power 6, then you have 5 square. What is next? Again, this particular property, students, that a determinant should be k to the power n times determinant of a. So here 2 being scalar comes out. So 2 comes out with power 3, which is order of a, whole raised to the power 4, because that 4 is also there, times determinant of a to the power 4. I hope there is no confusion on it. So 2 to the power 3 to the power 4. I hope I need not tell you it is 2 to the power 12. Right. So can I write a 2 to the power 12 directly here? I hope that won't bother you. So I'm writing a 2 to the power 12 here. So now if I look closely, 2 to the power 12, 2 cube. I think that leaves us with 2 to the power 15. Right, students? Then we have 3 to the power 6. What is next? What was determinant of a? We have discussed determinant of a was 5. So here I could have replaced determinant of a by 5. So this could have been written as 5 to the power 4. So 5 to the power 4 and 5 square will leave you with 5 to the power 6. Let me just cross check it. 2 to the power 15, 12 plus 3, 3 to the power 6. There is no other 3, and 5 to the power 6. Yes. Now if I compare it with 2, 3, 5, alpha, beta, gamma, right? So we were told that this is equal to 2 to the power alpha into 3 to the power beta into 5 to the power gamma. So I don't think that I need to do or solve it further. Alpha is going to be 15. I hope y, 6 is going to be beta, and 6 is going to be gamma. I hope we are going great. Yes. And by comparing this, alpha plus beta plus gamma can be found, and you can mark the correct answer, which is not a very difficult task, which you can do by yourself and mark the correct answer. All you need to do is 15 plus 6 plus 6, which you all are able to do. 15 plus 12, which is 27. So 27 would be the correct answer. My motive is not to make you understand the correct answer. My motive here is to make you understand how did we get it. Did you understand all the properties? So 3 things very widely we have been using, and JEE loves these 3 concepts, these 3 formulae. Which 3 formulae? First formula, this one. They are in love with this particular formula. They love it. Second one is this particular portion. This thing they keep on asking. You will see it by yourself. The more previous year's questions you will see, you will see them getting used. The next property which they love is this one, that determinant of product of 2 matrices is equal to product of their individual determinants. So remember it. This is something which they constantly keep on using. Well, after this, let us work on the next concept, which is called the inverse of a matrix. Now, we have already learned the inverse of a matrix while exploring the concept of the adjoint of a matrix. How do we use that? Let's have a look at that particular part here. So we have already discussed this portion previously while discussing the adjoint. Let me conclude it with this particular part, that A inverse is equal to adjoint of A upon determinant of A, provided that A should be a non-singular matrix. That means determinant of A should not be 0. This is what we have already learned, explored and discussed. I'm not going to explain this further again. Now, let us understand some very important properties of the inverse of a matrix. I hope I need not explain how do you find the inverse of a matrix. I hope that is something very simple. If you want, I can come up with an explanation to finding the inverse of a matrix which is of order 2. Let's say this is 2, 3, 1, and let's say 5. Its determinant is of course not zeros, which means its inverse can be found. So what do I do? To find its inverse, I need to find its adjoint. Do you remember the short technique for a 2 by 2 matrix adjoint? The short technique was that you interchange these 2 values of the principal diagonal. So 5 and 2, if are interchanged, will become 2, 5. Rather, 2, 5 when interchanged becomes 5, 2. And then you keep these values intact, 1 and 3, but you take their negatives. So this will be the adjoint of A. So I found the adjoint of A. Can I find the determinant of A? So determinant of A was 2 into 5, that's 10. 3 into 1 is 3. 10 minus 3 is 7. So can you write the inverse of A? I hope inverse of A is a cakewalk for you. Inverse of A is nothing but adjoint of A divided by determinant of A. What was adjoint of A? This was 5 minus 3, then minus 1, and then 2, and then you are supposed to divide it by a scalar quantity 7, or rather multiplied by 1 by 7. That's your A inverse. In a very simple language, in a more clear language, you can write A inverse as 5 by 7 here, then minus 3 by 7 here, then minus 1 by 7 here, and 2 by 7 here. What I'm trying to make you understand is, if you multiply A with A inverse, if you multiply A inverse with A, or vice versa, you are going to get an identity matrix. That is the meaning of A inverse. That is how you find the inverse of a matrix. A very simple process. Nothing is very much confusing at all, I believe so. This is what you must have prepared for 12th standard as well. While studying in 12th standard, I'm talking to the droppers, and if you're studying in 12th standard, you must have learned this particular part. This is not what they are asking. This is not what they might ask. What they will ask is questions based on the properties of inverse. The way we have learned the properties of adjoint, similarly there are properties of inverse, and they form questions on the properties of inverse. What are the properties? Let's learn them one after another. Let's begin with the first property. What is it? Uniqueness of inverse. So every invertible matrix possesses a unique inverse. For example, in a very simple language, if I say A has its inverse B, then B will have its inverse A. So they are unique in nature. A cannot have any other, any other inverse rather than B. If it has any other inverse rather than B, then that inverse in B will be same. So inverse are always unique. It's same as reciprocal, right? Now, reversal law. If A and B are invertible matrices of order n by n, then AB is invertible and AB inverse is B inverse A inverse. So inverse has this property same as transpose. Do you remember that? What did we used to do with transpose? So if I were to ask you transpose of AB, we used to write as B transpose into A transpose. The same goes true with AB inverse as well. So whenever I'm asking you to find the product of AB and then their inverse, don't do that. Rather find the inverse of B and the inverse of A, and then you can take the product, or vice versa as per the requirement of the question. Another property, same as transpose, I believe you will be able to remember it. Talk about the next property, or rather extension of it. So reversal law is very simple. All you need to do is reverse the order. So let's say ABC inverse. If I'm asking you the inverse of whole of ABC, then you can write it as C inverse into B inverse into A inverse. Did you get that part? Now let us proceed ahead towards the next property, the third property. If A is an invertible matrix of order n, then A transpose is also an invertible matrix of order n. And the way we could interchange the power with transpose, inverse can also be interchanged. I hope you must have remembered. We have learnt a property that if A to the power m transpose is needed to be taken, then we have learnt that you can take the transpose first and then you can take the inverse. Because of that reversal law, you change the order here. The same logic can be applied here, that if you want to take the transpose and then inverse, or if you take the inverse first and then you take the transpose, that will yield the same result. So remember this also as a conclusion, a very important property. Right now, next property. If you have A to be an invertible matrix, are you understanding the meaning of a matrix to be an invertible matrix? If it is an invertible matrix, which means its inverse can be found. And if its inverse can be found, which means the necessary and sufficient condition was determinant of A should not be 0, which means A should be non-singular. So whenever somebody says that this matrix is an invertible matrix, this thing should be there in your back of the mind, that that matrix is a non-singular matrix, which means its determinant is not 0. Getting it, everyone? Now, so if A is an invertible matrix of order n, and where I'm giving you another scalar quantity which is a natural number, then A to the power k inverse or A inverse to the power k or A to the power minus k will give you the same value, the way we do it with transpose. That's exactly what holds true for inverse as well. Now, the next property. If A is any matrix of order n, then A inverse of A inverse will be A. The way we have seen, transpose of A transpose is A. So if you take the inverse of inverse, it will give you the same matrix, because matrices are the uniqueness of the inverse in matrices. I hope that part is understood by you. So if you take the A inverse, which will be, let's say, B, and if you find the B inverse, that should be A, because A and B are inverse of each other. That will give you the same value. So inverse of A inverse will be A only. I hope you are able to digest this particular part. Well, with that, next property. This is something very crucial. They keep using this particular formula or expression rather. So remember this as a result. This has its own meaning. This has its own applications. So again, this is what they constantly keep on using. At a lot of places, this is very subtly used and utilized, and students forget this particular property. That's why I'm saying that if you are asked to find the value of the determinant of A inverse, see, we have learned that determinant of A and determinant of A transpose is equal. That is what we know. But when it comes to inverse, then determinant of A inverse is not equal to determinant of A. It is equal to 1 upon determinant of A. Will you remember that? Another conclusion, students. Now, there is another property. Remember it. We have learnt it that adjoint of diagonal matrix is the diagonal matrix itself. And if you use that property to the inverse of a matrix, I hope you're understanding. If I'm asking you the inverse of a diagonal matrix, so here A, B, C are the diagonal elements, other elements are 0 because A is a diagonal matrix. Its inverse will be very simple. What will be its determinant? Its determinant will be product of the diagonal elements, which will be ABC. And if ABC divides the diagonal, the adjoint of A, what will be the adjoint of A? I hope you remember BC, CA and AB. So if BC, CA and AB are divided by ABC, I'll be getting 1 upon A, 1 upon B and 1 upon C. So the very simple result which you must remember in the context of a diagonal matrix, for example, if I take the diagonal matrix as 2, 3 and 4, right, and the other elements are 0, I hope there is no confusion on it. And if I were to ask you, let's say this is a matrix, this is a diagonal matrix, and if I were to ask you the inverse of it, take the reciprocals of 2, 3 and 4 and keep the other entries to be 0. So keeping other entries intact, the reciprocal of 2 will be 1 by 2, reciprocal of 3 will be 1 by 3, reciprocal of 4 will be 1 by 4. Other entries will be 0 as it is, and that is the inverse of x. That's what you should understand. That's what I'm saying, that the inverse of a diagonal matrix is very simple to be found if you understood the concept of adjoint of the diagonal matrix, and if you know how to find the determinant of a diagonal matrix. If those two concepts are clubbed, because adjoint upon determinant is basically inverse of a matrix, and that's how you can find the inverse of a diagonal matrix as well. Now, there comes some more conclusions. What is that? The inverse of a non-singular square matrix A of order 2 is obtained by interchanging the diagonal elements and changing the signs of diagonal elements and dividing by determinant of A. Do you remember this? This is the short technique I have been constantly mentioning, and this is the formula which we have already discussed here in this particular part, a 2 by 2. So what we did was, we basically interchanged the principal diagonal elements and we put negative signs on the non-principal diagonal elements, and then we divided it by its determinant, and that's how we could find the inverse of this A, which was a 2 by 2 matrix. That's exactly what this property is trying to say or convey here. If that note is properties understood by you all, I hope you are able to digest this part. This part is already explained to you. Now, let me come to the next part where we solve another question based on the properties of the inverse. What is that? Have a look at this particular part. JEE Mains 2025 has asked it. What is the question? The question says that you have A, B and this, whatever it is, I'm not reading it, are non-singular matrices. Okay, which means their determinants will not be 0 and of the same order. Okay, which means the product is possible. Then the inverse of this, what are we given? Let me write that part. What are we asked? We are asked the inverse of A times adjoint of A inverse plus adjoint of B inverse times whole of B. So we are asked the inverse of this expression, right, students? We are asked to write the inverse of this expression. So let's say the inverse of this expression, I need to find this inverse here. So that is what I'm supposed to solve. Now, how do I do it? I'll use a very simple method here. We know inverse holds that reversal law. So if you have three matrices X, Y and Z, and if you are asked to write their inverse, you will write it as Z inverse, Y inverse and X inverse. I hope you remember this property. So I'll write B inverse first. So I'll be writing B inverse first into means I'll write a dot here. Inverse of this, what is the inverse of this? Inverse of adjoint of A inverse plus, I hope this is understood by you all, plus adjoint of B inverse. So inverse of this entire thing into A inverse. So I hope there is no confusion on it, there is no problem on it, and you are able to digest all what is said so far. I'm really sorry, I have made a mistake. I did not read this part. Let me highlight it. There was this -1 as well, so there was this inverse as well. So that minus sign I'm putting here. So this minus 1 was here. So this inverse sign was also there. This is not minus 1. This is basically inverse sign here. I hope you know the difference. So this minus 1 is here. So here you are taking the inverse of this inverse. I hope you're understanding. What did I do? I'll repeat this particular part. B inverse I'm supposed to take first. Then I'm supposed to take the inverse of this, which is already the inverse of inverse. And then A inverse is what I'm supposed to do. We have also learned this property as well, that inverse of an inverse nullifies it. It cancels the effect the way transpose does. So here I'll have the conclusion as, here I'll be having this B inverse over here. Then this inverse and inverse will get nullified. So I'll be left with adjoint of A inverse plus adjoint of B inverse. And then you have this A inverse. I hope there is no confusion on it. Now, what I do next is I will pre-multiply B inverse on both of these terms and I'll post-multiply A inverse on both of these terms. So what will I get as a result? Have a look at this. I will have B inverse into adjoint of A inverse into A inverse. I hope there is no confusion on it. Plus, this will get pre-multiplied by B inverse. So it will be B inverse times adjoint of B inverse times A inverse. I hope there is no confusion on it. Now, are you seeing something very simple and very interesting here? If you have started noticing, I hope most of you must have started noticing something very simple and very interesting, which will lead you towards the answer to this particular question. What is that? Let me bring that under your notice. But before that, do you remember, if I multiply a matrix, instead of writing A, let me write something else so that you don't get confused. Let's say if I have a matrix A and if I multiply it with its adjoint, what do I get? I get determinant of that. Sorry, it's not determinant of A. Determinant of that matrix times identity matrix of the same order. Do you remember this conclusion? Property number 1 related to adjoint, which we have learnt. Same property, if I were to use here in this particular question, how do I use it? Have a look at this part. Have a look at this particular part here. Adjoint of A inverse into A inverse. So let's say A inverse is X. So adjoint of X into X. Similarly, look at this part. B inverse into adjoint of B inverse. So this is Y, let's say, Y into adjoint of Y. I hope you're understanding what it should be. So with that, if I were to write the conclusion here, the conclusion will be B inverse will remain as it is. So I'll keep B inverse intact. So I will keep B inverse intact. So here I will write this B inverse as it is, but adjoint of A inverse into A inverse will leave me with determinant of A inverse into the identity matrix. So here I'm supposed to write determinant of A inverse into the identity matrix. That identity matrix into B inverse will leave me with B inverse, so I'm not writing that part. Plus here B inverse into adjoint of B inverse is going to be determinant of B inverse into identity matrix. So here I'm supposed to write determinant of B inverse into the identity matrix into A inverse. So any identity matrix into A inverse will give me A inverse here. Now my job boils down to finding the options now, because by looking at the options, I'll be in a better position to deduce what I need to bring here. So if I look closely, I think I am not getting what I am needing here as per the options, but I can frame it. See, first of all, one more property we have learned. What is that property? We have already understood that if I were to ask you the determinant of X inverse, it is 1 upon determinant of X. So from here, if I were to write, then one more thing I am able to write, B inverse I'll keep as it is, but this A inverse, determinant of A inverse can be written as 1 upon determinant of A. Similarly, A inverse I'll keep as it is, but here determinant of B inverse can be written as determinant of B. Now I'll work on this. I hope we already know that any matrix inverse is given by adjoint of that matrix divided by determinant of that matrix. So if I use this particular property, these two properties, if I'm using here, I think I'll get something relevant to the options. So B inverse can be written as adjoint of B divided by determinant B. So that will give me determinant of A into determinant of B, plus A inverse will become adjoint of A divided by determinant of A into determinant of B. We also know one more property, that determinant of A into determinant of B can be written as determinant of AB. So let me look at the options. Yes, I think we have gotten the answer because if I pay attention, the next part unfolds. See, determinant of AB, determinant of AB. So the LCM will be determinant of AB, right? And here, if I club this two, so this will be adjoint of A plus adjoint of B. And we know adjoint is not distributive over addition or subtraction. So I will not write it as adjoint of A plus B. No, that will be wrong. So mind you everyone, that is not what you'll do. So I think we have the answer as option D, which matches with what we have attained here. So did you understand how do they mingle or merge different concepts or properties of inverse, and they ask you questions based on that? That is the category of questions which IIT loves. So I hope you're understanding different properties we have discussed here in this particular part. So this one which they ask you a lot, and then these two properties and a lot of things related to adjoint also we have discussed in this particular part. This particular part of this video is something which is not something very crucial, because this is what we have already understood while discussing the chapter determinants, when we have had a discussion on Cramer's rule. That rule is the extension here. So let's say if I have system of equations, this I hope you must have remembered while we were discussing Cramer's rule. That's exactly is expanded here, elaborated here. So don't worry about that part. I'm directly skipping here and I'm just giving you the final results. This is what they do. So finally the conclusion is this. Now if the system is non-homogeneous, which means the constant terms are there, what are the conclusions which can be drawn? See, the variable is given by A inverse B. We'll not use this particular method. We'll use the Cramer's rule, which we have already discussed. Delta, delta 1, delta 2, delta 3. Do you remember that? Then delta 1 upon delta will be X. Delta 2 upon delta will be Y. Delta 3 upon delta will be Z. And then we have learned three cases. Delta is non-zero, unique solutions. Delta, delta 1, delta 2, delta 3, all of them are zero, infinite solutions. In these two cases, the system of equations are consistent. If delta is 0, but at least delta 1, delta 2, delta 3, at least one of them is non-zero, then we say no solutions and the system of equations become inconsistent. That's exactly what they're trying to say here, but in a different sense. I am not asking you to remember this or memorize this. If you remember the Cramer's rule, then only you will understand this part. So need not pay much attention to this part. Then again there comes this part where if the system of equations is homogeneous, do you remember 0, 0, 0, the constant terms are not there, they become 0, 0, 0. Then you have two choices, either trivial solution or non-trivial solution. Trivial solutions when delta is not 0, but if they ask you that it contains a non-trivial solution, then you used to have that delta is equal to 0. That's exactly what they are saying in a different sense. Something which you should remember is if the number of equations is less than number of unknowns, then it will have non-trivial solutions. I hope you will remember it. Now, let us move ahead with the next part of our video, which is called the matrix polynomial. The final topic from the chapter matrices. If you are still here with this particular part, with whatever you have learned so far, and if you have invested your complete time, dedication, and efforts in understanding this chapter so far, stick to it at this stage as well. This is that climax, that final culmination of this portion, where all what you have learned will be applied. This concept is not directly mentioned or described by JEE Mains and Advanced, but if this concept is learned, a lot of questions can be done with a lot of ease. So matrix polynomial, Cayley Hamilton, or this eigenvalues are not a part of your syllabus. But if this particular portion is learned, you will be able to solve a lot of questions with a lot of ease. As they say, there are short techniques or short methods. There's nothing like that. These are the concepts which, if are learned, can be applied and answers can be fetched with very less amount of efforts. That's exactly what we'll explore here in this part. Questions are asked on it, but students don't know this concept and they use the standard lengthy methods, and that's when this concept comes into picture, and it plays a very crucial role in decreasing the time. It actually enhances your efficiency. How? Let's learn it. First of all, let's understand what is a matrix polynomial. So the way we usually have polynomials, let's say x cubed plus 3x squared plus 2x plus 1, in the same fashion we have matrix polynomials as well. So if I am able to write a matrix, for example, there is a matrix A, and if I'm able to write it as, if I am able to write this matrix A, let's say as a cubed plus 2a square, right, plus let's say 3 is equal to 0. So this is the matrix polynomial. What is A here? A is not an ordinary variable like x or a y. Here A is behaving as a matrix. So this is called a matrix polynomial in your simple language, in your basic understanding. Now, why do we use matrix polynomial? What is the application of it? What is the application of it? That is what we'll understand or explain here. Let's say there is a matrix, and that matrix satisfies this particular equation. So here, this matrix satisfies this particular equation. So there is a matrix A, and that satisfies this equation. So how will we get this equation? We'll discuss it. We'll discuss or talk about the Cayley-Hamilton method. We'll discuss about the matrix polynomial in a more detailed format. We'll talk about all of that in the upcoming part of this video, later part of this video. But first of all, let us assume that somehow, what is that somehow? I'll explain that. Don't worry about it. But somehow, let's say if I am able to create a matrix polynomial, with that matrix polynomial also, you can find the inverse of a matrix. How? Let's say I take this a cube and 2a square on the other side. So what will I get by that? I'll have 3 is equal to minus a cube minus 2a square, right? What I do is I'll divide it by 3, let's say. So what will I have? Of course, this 3 will not be just 3. Let me make that correction here. I'm really sorry. This 3 should have had an identity matrix as well, because here you have a matrix, then you have a matrix, then you have this 3 over here, which is a constant term or a scalar quantity. It should be multiplied with an identity matrix so that all 3 matrices can be added. This confirmability for addition and subtraction is needed when you add or subtract matrices. I hope you know that. So when I do that here also, I will have 3 into an identity matrix. Now, what I do is I'll multiply both the sides by 3. So I'll divide both the sides by 3. So when you do that, you will have the identity matrix as minus a cube upon 3 and minus 2 by 3 times a square. The next thing which I do is I multiply both the sides by A inverse, pre or post, whatever you wish to do. So let's say I'm doing this pre-multiplication by A inverse on both the sides. So A inverse into identity matrix will be A inverse only. So that will be A inverse is equal to A inverse into A cube will leave me with A square. So that will be minus A square by 2. And there A inverse into A square will leave you with A. So that will be minus 2 by 3 times A. What I am trying to make you understand here is a very important conclusion, which is this, that if I had a matrix polynomial, sir, how are we going to get this matrix polynomial? There is a method for it. If that matrix polynomial is directly given to you, let's say I am given in the question that there is a matrix A which exists and which satisfies this polynomial equation. From here, I can write the characteristics roots of C as lambda 1 to the power 10 and lambda 2 to the power 10. Why am I saying this? Because we have already learned that if C is a to the power 10 and if A has characteristic roots as lambda 1 and lambda 2, C will have its roots as lambda 1 to the power 10 and lambda 2 to the power 10. So C will have its characteristic roots as lambda 1 to the power 10 and lambda 2 to the power 10. Now what I am told is to find the trace of C. Well, trace of C will be lambda 1 to the power 10 plus lambda 2 to the power 10, because we know that for a matrix that sum of its eigenvalues is equal to its trace. So I am asked the trace, but I'll find it with this method. Did you get that part? Now let me get back to this portion where I'm saying that in this part, if you look at this portion, can you say that this is a triangular matrix? Why am I saying that? First of all, I can write its characteristic equation. I have two methods. Either determinant of A minus lambda I should be 0, or I know A square minus trace of A into A plus determinant of A into identity matrix. Or the third method for this particular case, which is the special case here, because if this is a triangular matrix, either upper or a lower or a diagonal matrix, well in that case, the eigenvalues of that matrix is the principal diagonals elements. Did you get that part? I am saying here that from here, if I want to ask you the eigenvalues of A, which let's say are lambda 1 and lambda 2, well, they are nothing but the values, elements positioned at the principal diagonal, which are 1 by root 2 and 1. Did you get that part? Did you understand that part? And if you are able to understand that particular part, will it be a really difficult part for you to find the trace of C, which is lambda 1 to the power 10, which means 1 by root 2 to the power 10, plus lambda 2 to the power 10, which means 1 to the power 10. This will be 1 by 2 to the power 5, which means 1 by 32. And this is 1. So this should be 32 plus 1, which is 33 by 32. This I am told to be equal to m and m upon n, where m and n are co-primes. So 32 and 33, nothing is common. So I am asked the value of m plus n. 32 plus 33 is 65. Did you get that part? Did you understand how easy these questions are if you know these nuances, if you know these basics? This one shot, I hope, has given you a complete clarity on matrices, all the learnings, all the details, at absolutely no cost. We are providing all of these one shots at completely free of cost. Along with this, we are also providing you the notes and the DPPs for your practice. These things, the DPPs and the practice sheets and the notes, are available for you on our PW app, the amazing platform from where crores of students are preparing for different competitive exams and getting the desired results. The link to our app is given in the description. By clicking on it, you can access all of this. With that, I think we have covered everything related to matrices. You have gotten an excellent clarity on this particular chapter. Let us meet in the next video. Thank you so much. You have been a great audience.